Hey everyone, welcome to the channel. In today's video, we're covering the top 100 most frequently asked Python interview questions. Whether you are preparing for a Python interview or just want to brush up on your skills, this video has got you covered. We'll go over the most important concepts, common pitfalls, and tips to help you ace your next interview. So grab a notebook and let's dive into the key Python questions you need to know. Question 1. What are the key features of Python? Python is known for its simplicity with a clean syntax that makes it easy to learn and use. As an interpreted language, it executes code line by line, which simplifies debugging and accelerates development. Python is dynamically typed, meaning you don't have to declare variable types as they are determined at runtime. Its cross platform nature allows it to run seamlessly on various operating systems like Windows, macOS, and Linux without requiring changes. With a vast standard library, Python offers tools for web development, data analysis, and more. It supports object oriented programming, enabling features like classes and inheritance. Python is free, open source, and accessible for anyone to use and modify. As a high level language, it abstracts away low level complexities, making programming tasks easier. Python supports multiple paradigms such as procedural, object-oriented, and functional programming. Additionally, it features automatic memory management through a built-in garbage collector. Question 2. What is PEP 8 and why is it important? PEP 8, also known as Python Enhancement Proposal 8, is the official style guide for writing Python code. It provides a set of conventions and best practices that ensure code is clean, consistent, and easy to read. The importance of PEP 8 lies in its ability to standardize Python code, making it more maintainable and accessible to developers working in teams or across different projects. Why PEP 8 is important? PEP 8 plays a crucial role in maintaining code quality and professionalism within Python projects. One of its main advantages is consistency, ensuring that code looks uniform across different projects and developers, which enhances the overall readability. When code follows the same structure, it's easier for others to understand, reducing the learning curve when joining a new project. Readability is another key benefit, as PEP 8 encourages clear, understandable code, helping to minimize confusion or ambiguity in complex projects. For teams, collaboration becomes smoother as everyone adheres to the same coding conventions, making peer reviews and code maintenance more. From a professional standpoint, following PEP 8 demonstrates a developer's attention to detail and adherence to industry standards, which is important in effecting a professional upcoding. Additionally, PEP 8 aids ease of debugging by promoting clean, well-formatted code, making it easier to identify and correct errors or inconsistencies, ultimately leading to a more maintainable and scalable codebase. Key PEP 8 guides include PEP 8 provides several key guidelines that ensure Python code is structured in a clean, readable, and consistent manner. Indentation is one of the most critical guidelines where it specifies using 4 spaces per indentation level and avoiding the use of tabs. This consistent indentation style makes code visually clear and easy to follow. Another important aspect is line length, where PEP 8 recommends keeping lines to a maximum of 79 characters to ensure readability across different editors and screens. It also encourages adding blank lines between functions and classes to separate code logically, making it easier to navigate and understand. PEP 8 outlines naming conventions such as using snake underscore case for function and variable names and camel case for class names, creating a uniform and recognizable style across the codebase. Finally, comments and docstrings play an essential role in documenting the purpose and functionality of code. PEP 8 encourages developers to use comments to explain complex logic and to include docstrings in functions and classes, making it easier for others to understand and maintain the code. Together, these guidelines form the foundation for writing clean, maintainable, and professional Python code. Question 3. What is the pip command and how is it used? The pip command is a tool to install and manage Python package and making an essential utility for Python developers stack. Pip stands for Package Installer for Python and is used to download, install, update, and manage third-party libraries and modules from repositories like the Python Package Index. It simplifies the process of adding external libraries to your projects by handling the downloading and installation of packages as well as the dependencies. Important pip commands. The pip tool offers a variety of commands that simplify package management in Python. Here's a detailed explanation of the most important pip commands. Installing a package command pip install package underscore amis use install a Python package from the Python index ppf. This is the most common command to bring external libraries or tools into your project. Upgrading a package: when you need to update an installed package to its latest version, the command pip install upgrade package underscore name comes in handy. This ensures you're working with the latest features and fixes of a package. Uninstalling a package: if a package is no longer needed, you can remove it using pip uninstall package underscore name. This helps to clean up your environment and avoid unnecessary dependencies. Listing installed packages: to see all the Python packages currently installed in your environment, piplist provides an complete list of installed packages along with their versions. This is useful for managing and reviewing your project's dependencies. Checking for outdated packages: with pip list updated, you can identify any installed packages that have newer versions available. This allows you to keep your environment up to date with the latest features and security patches. Installing packages from a requirements file: if you're working on a team or deploying a project, you'll likely use a requirements.txt file to specify exact package versions. The command pip install air requirements.txt ensures that all the required packages are installed with the versions specified in that file. Freezing installed packages: to create a snapshot of all installed install the packages and their versions, the pip freeze requirements.txt. This writes the installed packages into a requirements.txt file, which is commonly used to share project dependencies with others or for deployment. These commands allow developers to easily manage major packages, ensuring consistency, compatibility, and efficiency in Python project environments. Question 4: what are Python's built-in data types? Python offers a variety of built-in data types, each designed to efficiently handle specific kinds of data. One of the fundamental data types is int, which represents integer numbers. These are whole numbers, both positive and negative, without any decimal point, such as 5, -3, or 0. Python can handle arbitrarily large integers constrained only by the memory available. For decimal numbers, Python uses the float type, which stores floating point numbers with decimal places such as 3.14 or -0.001. This type is essential when working with continuous data, financial calculations, or scientific measurements requiring precision. A string is a versatile data type used for storing text. It represents sequences of characters, including letters, numbers, symbols, and even escape characters like name for new lines. Strings are enclosed in single or double quotes and are immutable, meaning their contents cannot be changed once created. They are heavily used for input-output operations, parsing data, or creating human-readable messages. When working with logical conditions, Python provides the bool type. Boolean values can only be true or false, and they play a crucial role in controlling the flow of programs with conditionals and loops. One of Python's most flexible and widely used data types is the list. A list is an ordered mutable sequence that can hold elements of any teacher strings or the list odious. Lists are defined using square brackets, and you can access elements by their position index starting at 0. Lists support a variety of methods for modifying their contents, such as appending, removing, and sorting elements. For example, my underscore list 1 2 apple 3 4 contains integers, a string, and even another list as its elements. Lists are ideal when you need to store a collection of items in a specific order and frequently modify them. In contrast to lists, tuples are ordered but immutable sequences. Once a tuple is created, its elements cannot be changed. Tuples are used when you want to group data together in a fixed structure, such as coordinates x, y, or a collection of related values that shouldn't be altered. A set is another collection type but is unordered and contains only unique elements. Sets are useful for membership testing and removing duplicates from a dataset. Python also offers frozen set, an immutable version of a set for cases where you need the uniqueness of elements but don't want the data to change. The dictionary type is a powerful data structure that structures both the UPFs, clubs at the check. It allows for efficient lookup where each key maps to a specific value similar to a real world dictionary. For example, my underscore nickname Alice, age 25 pairs a string key like name with the value Alice. Dictionaries are perfect for scenarios where data needs to be labeled. Categorized carry review key. More specialized types include complex numbers, which are used in mathematical computations involving imaginary numbers. A complex number is represented in the form of Bij, where E is the real part and B is the imaginary part. Python's nulltype represents the absence of a value commonly used to signify a null or undefined state. The range type generates a sequence of numbers and is often used in OOPS, while bytes and byte represent sequences of binary data. Memory view allows you to work with the memory of objects like bytes or byte arrays without copying the data, useful in scenarios requiring high efficiency. Overall, Python's diverse set of built-in data types provides developers with tools to manage a wide range of data structures efficiently, each with its strengths tailored to specific user pattern. Question 5. What is the difference between list and tuple? Mutability. Mutability. Lists are mutable, meaning they can be modified after creation. You can add, remove, or change the elements in a list at any time. For example, using methods like append or remove, you can modify a list. Tuples are immutable, meaning once a tuple is created, it cannot be changed. You cannot modify the elements of a tuple after its creation. Syntax. Syntax. Lists are defined using square brackets. For example, my underscore list 1, 2, 3. Tuples are defined using parentheses. For example, my underscore tuple 1, 2, 3. Performance. Lists are slower in terms of performance because they allow modifications, and Python is to manage the additional overhead of dynamic resizing and modifications. Tuples are faster since they are immutable, allowing Python to optimize their performance due to their fixed nature. Methods. Lists support many methods that allow for modifications such as append, remove, pop, extend, etc. Tuples have limited methods due to immutability. They support methods like count and index, but they lack those for modification. Use case. Um, Lists are ideal for scenarios where data is expected to change, such dynamic data structures like to-do list or real-time data processing. Tuples are best suited for storing constant data where the values should not be changed, such as coordinates or fixed configurations. Summary usage. Lists generally use more memory because they are dynamic and need extra space to handle potential future modifications. Tuples use less memory compared to lists because they are fixed and do not need to account for modifications. Iteration. Iteration over a list can be slightly slower because of the flexibility and overhead of handling dynamic elements. Tuples are faster to iterate over due to their immutability, which allows Python to optimize the iteration process. Hashable, 9 less available. Lists are not hashable, meaning they cannot be used as keys in a dictionary or stored in a set because they are mutable and can change. Tuples are hashable provided all their elements are immutable, making them usable as dictionary keys or set elements. Copying. Lists can be shallow copied using methods like copy or through slicing my underscore list. Tuples, being immutable, cannot be copied directly, but you can create a new tuple through slicing or concatenation. Example. In Python, both lists and tuples are used to store collections of data, but that they differ in several important ways. A list is defined using square brackets and it is mutable, meaning you can modify its contents after creation. For example, you can create a list called my underscore list 1, 2, 3. If you want to add another element to this list, you can do so using the append method like my underscore list dot append 4, which will modify the list to 1, 2, 3, 4. Lists are flexible and suitable for cases where you need to change or update the data frequently. On the other hand, a tuple is defined using parentheses and is immutable, meaning once it is created, you cannot modify its contents. For example, a tuple can be defined as my underscore tuple 1, 2, 3. Since tuples cannot be modified, methods like append are not available. This immutability makes tuples useful for storing data that should remain constant throughout the program, such as coordinates or fixed settings. Question 6. What are Python dictionaries and how do you use them? A Python dictionary is a powerful data structure that stores key value pairs, allowing you to access values based on unique keys. It's like a real life dictionary where you look up a word key to find its meaning value. The keys in a Python dictionary must be immutable types like strings, numbers, or tuples, but the values can be any data type. Dictionaries are great for situations where you need fast lookups, as they allow you to retrieve values efficiently by referencing the keys instead of searching through the entire collection. Key features of dictionaries. Dictionaries in Python store data as key value pairs, making it easy to associate a unique key with a specific value. They are mutable, meaning you can modify, add, or remove key value pairs even after the dictionary is created. Starting from Python 3.7, dictionaries preserve the order in which items are added, but in earlier versions they were unordered. One of the key benefits is their speed. Retrieving a value by its key is highly efficient, usually taking constant time, which makes lookups fast and scalable. Practical implementation. In this example, we are working with Python dictionaries, which are our data structure that stores key value pairs. The my underscore dic dictionary is created with keys name, age, and city each mapped to their respective values, alias 25 and New York. The dictionary allows us to quickly access, modify, add, or remove data using the keys. To access a value, you can use the key directly, like my underscore dic name, which returns Alice. Alternatively, the get method provides a safer way to access values, as it returns none if the key is not found. Instead of found error, here it retrieves the age, returning 25. Adding new data to the dictionary is as simple as assigning a value to a new key. For example, my underscore dic email adds the email field to the dictionary. You can also update an existing value by assigning a new value to an existing key, as shown when we update the age to 26. Removing a key value pair can be done with the pop method, which both removes the key and returns the value. In this case, my underscore dic.popcity removes the city key and its associated value. Finally, the example demonstrates how to iterate through the dictionary. You can loop through the keys with for key in my underscore dict or retrieve all values using my underscore dict.values. To iterate over both keys and values, the items method is used, which returns key value pairs as tuples. This iteration allows you to display both the key and its corresponding value in a loop. Question 7. What are Python string methods? 1. Strut.upper converts all characters in the string to uppercase. It's useful when you need a string entirely in capital letters. In the example, hello.upper method converts all the characters in the string hello to uppercase, resulting in hello. This transformation is useful when you need to standardize text to uppercase for comparison or formatting. 2. Str.lower converts all characters in the string to lowercase, which can be useful for case insensitive comparisons or standardizing text. In the example hello.lower, the lower method converts all the characters in the string hello to lowercase, resulting in hello. This is useful when you want to make a string case insensitive or for consistent formatting. 3. Store.capitalize capitalizes only the first character of the string and makes all other characters lowercase, is useful when formatting a sentence. In the example hello world.capitalize, the capitalize method converts the first character of the string hello world to uppercase and the rest of the characters to lowercase. This is commonly used when formatting sentences to ensure proper capitalization. 4. String.title capitalizes the first letter of every word in the string, making it title case. In the example hello world.title, the title method capitalizes the first letter of every word in the string, resulting in hello world. This is useful for formatting text in title case where each word begins with a capital letter. 5. Store.strip removes any leading left and trailing right white space from the string. This is helpful for cleaning up user input. In the example hello.strip, the strip method removes the leading and trailing spaces from the string, resulting in hello. It is useful for cleaning up extra white space around the content. 6. Ester.liststrip removes only the leading left white square specified characters from the string. In the example hello dot strip, the strip method removes only the leading spaces on the left from the string, leaving the rest of the string unchanging. 7. Strip removes only the trailing right white space or specified characters from the string. In the example hello dot restrict, the strip method removes only the trailing spaces on the right from the string, resulting in hello. 8. Start dot replace old new replaces all occurrences of the old substring with the new substring. Is useful for replacing specific words or characters in a string. In the example hello world dot replace world python, the replace method replaces the substring world with python, resulting in the new string hello python. 9. Start dot split separates a string into a list of substrings based on the separator sep. It's useful for breaking a string into components. In the example a bc.split, the split method splits the string at each occurrence of the comma, resulting in a list a bc. Each element of the list is a substring from the original string separated by the specified delimiter. 10. Stir dot join iterable joins elements of an iterable like a list into a single string with the calling string as the separator. In the example dot join hello world, the join method combines the elements of the list hello world into a single string with a space as the separator between each element. The resulting string is hello world. 11. Start dot find sub returns the lowest index where the substring sub is found or -1 if it's not found. In the example hello.find e, the find method searches for the first occurrence of the substring e in the string hello. Since e is found at index 1, the method returns 1. 12 start.index sub similar to find but raises a value error if the substring sub is not found. In the example hello.index e, the index method searches for the first occurrence of the substring e in the string hello. Since e is found at index 1, the method returns 1. If the substring were not found, it would raise a value error. 13. Start dot starts with prefix returns true if the string starts with the specified prefix, otherwise false. In the example hello dot starts with he, the starts with method checks if the string hello begins with the substring he. Since it does, the method returns true. If the string has started with a different sequence, it will return false. 14. Dot ends with suffix returns true if the string ends with the specified suffix, otherwise false. In the example hello dot ends with low, the ends with method checks if the string hello ends with the substring low. Since it does, the method returns true. If the string had ended with a different sequence. 15. String.count sub returns the number of non-overlapping occurrences of the substring sub in the strings. In the example hello dot count l, the count of match checks how many times the letter l appears in the string hellos. Since the letter l appears twice, the method returns. 16. Start.isalpha returns true if all characters in the string are alphabetic letters, otherwise false. In the example hello.isalpha, the isalpha method checks if all characters in the string are alphabetic letters. Since the string hello contains only letters and no numbers or special characters, the method returns true. 17. Start.isDigit returns true if all characters in the string are digits, otherwise false. In the example 1234.isDigit, the isDigit method checks if all characters in the string are digits. Since the string 1234 consists entirely of numeric digits, the method returns true. 18. Store.isalnum returns true if all characters in the string a string are alphanumeric, leaded, or digits, otherwise false. In the example hello123.isalnum, the isalnum method checks if the string contains only alphanumeric characters, letters, and digits. Since the string hello123 has both letters and digits without any spaces or special characters, the method returns true. 19. Space returns true if the string contains only white characters, otherwise false. In the example dot space, the space method checks if the string consists entirely of white space characters. Since the string contains only spaces, the method returns true. 20. Start.swap case swaps the case of all characters in the string, converting lowercase to uppercase and vice versa. In the example hello.swap case, the swap case method converts all uppercase letters to lowercase and all lowercase letters to uppercase. So as a result, hello becomes hello. 21. Store dots fill width pads the string on the left with zeros until it reaches the specified width. It's often used for formatting numbers. In the example, 42 dots fill 5 this fill method pads the string with zeros on the left, making the total length of the string 5. As a result, 42 becomes 00002. Question 8. Explain the concept of list slicing. List slicing in Python is a way to extract a portion of a list using a specific range of indices. By specifying the start, stop, and step values, you can create a new list that contains only the elements you need without altering the original list. The start index indicates where the slice begins, the stop index tells Python where to end but doesn't include this index, and the step defines how many elements to skip. If any of these values are left out, Python uses defaults like starting from index 0, ending at the last element, or stepping by 1. This method offers flexibility in accessing just the right portion of a list or sequence. In this example, we are demonstrating different ways to slice a Python list using various slicing techniques. Slicing allows us to extract specific parts of a list, creating new sublists without modifying the original list. The my underscore list in this case contains numbers from 0 to 9. Basic slicing, such as my underscore list to 6, allows you to specify both a starting and stopping index. This returns a sublist that begins at index 2 and ends before index 6, giving the output 2, 3, 4, 5. You can also omit the start or stop index. When you omit the start my underscore list 4, it defaults to the beginning of the list, giving 0, 1, 2, 3. When you omit the stop my underscore list 4, it continues from the start index 4 in this case to the end of the list, resulting in 4, 5, 6, 7, 8, 9. Negative indices allow you to count from the end of the list. For example, my underscore list 4, one starts 4 elements from the end and stops before the last element, giving 6, 7, 8. Negative indices are useful for working with elements from the end of a list without needing to know the exact length of the list. Step slicing is another powerful feature that allows you to specify a step or increment between elements. My underscore list 2 returns every second element from the entire list, giving 0, 2, 4, 6, 8. You can also reverse the list using step slicing with a negative step. My underscore list 1 reverses the list, giving 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Question 9. What is the difference between is and equal to in Python? This operator in Python is an identity comparison tool. It checks whether two variables point to the same object in memory. This means that even if two variables have the same value, it will return true only if both variables refer to the exact same object. For example, two separate lists with identical content will not be considered the same object as ice, as they occupy different memory locations. This operator is typically used to check if two references refer to the same memory object, such as in cases involving singleton objects like none. On the other hand, the equal to operator is used for value comparison. It checks whether the values of two variables are the same, regardless of whether they are stored in the same submemory location. This means that if two variables have equivalent values, equal to will return true even if they are two separate objects in memory. This operator is commonly used for comparing data like numbers, strings, or the contents of collections such as list regardless of their identity. The key difference is that it is concerned with object identity while equal to is concerned with object values. For example, A is B checks if A and B refer to the same memory location, while A equal to B checks if the values stored in A and B are equal. Question 10. What is the difference between break, continue, and pass? The break statement in Python is used to terminate a loop entirely. When break is encountered inside a loop, Whether it's a for or while loop, the loop stops immediately and the control moves to the next statement following the loop. This is typically used when you want to exit a loop prematurely, for example, when a certain condition is met and continuing further iterations is no longer necessary. The continue statement, on the other hand, skips the current iteration of the loop. When continue is encountered, the code inside the loop that follows the continue statement is ignored and the loop proceeds with the next iteration. This is useful when you want to skip some specific iteration but still allow the loop to run for all other iterations, often based on a condition. The pass statement is a placeholder, does nothing executed. Unlike Bracken and Kinty, but the new questions affect the flower loop. It is often used as a placeholder in situations where code is syntactically required but hasn't been implemented yet, such as in empty loops, functions, classes, or conditional blocks. The code continues to execute normally after pass. In summary, break stops the loop entirely, continues skip the current iteration, and pass allows code execution to position out any action. Question 11. How do you reverse a list in Python? In Python, there are several ways to reverse a list. The reverse method reverses the list in place, directly modifying the original list. Another method is slicing, where one creates a new reversed list without altering the original. Lastly, the reversed function returns an iterator that yields elements in reverse, and you can convert this to a list using list. These methods provide flexibility depending on whether you want to modify the list in place or create a new reversed version. In this example, we explore three different ways to reverse a list in Python using the reverse method, slicing, and the reversed function. The first approach uses the reverse method, which directly modifies the original list by reversing the order of its elements in place. In the code my underscore list dot reverse, the original list 1, 2, 3, 4, 5 is reversed to become 5, 4, 3, 2, 1. This method does not create a new list. Instead, it modifies the existing list, making it efficient in terms of memory usage. The second approach uses slicing with the syntax my underscore list 1, where 1 represents a step of -1, meaning it starts from the end and moves backward through the list. Unlike the reverse method, this approach creates a new list that is the reverse of the original. The original list remains unchanged, while the new list, reversed underscore list, contains the reversed elements 5, 4, 3, 2, 1. Slicing is a concise and efficient way to reverse a list while preserving the original. The third approach involves using the built-in reversed function, which returns an iterator that iterates over the elements of the list in reverse order. Since reverse returns an iterator, we need to convert it back to a list using list reverse my underscore list. This approach, like slicing, creates a new list, leaving the original unchanged. The resulting reversed underscore list will be 5, 4, 3, 2, 1. Question 12. What is the difference between split and join in Python? Purpose. The split method is used to break a string into smaller parts, returning these parts in the form of a list of substring. The split is based on a delimiter, which can be white space or a specific character like a comma or semicolon. On the other hand, join does the reverse. It joins elements of an variable like a list or tuple into a tuple string. The items are combined with a specified separator placed between them. Operation. The split method works by breaking down a string wherever it encounters that delimiter and then returns those parts as a list. If no delimiter is provided, it defaults to splitting by white space, making it useful for breaking down sentences into words. Join, in contrast, takes the elements of an iterable like a list of strings and concatenates them into one string with the specified delimiter between each element. This can be useful for turning for a list of words back into a sentence. Return type. When you use split, it always returns a list of substrings. This is useful for manipulating data further. For example, if you split a sentence into words, you can process each word individually. Join, however, returns a string that merges elements into one cohesive one behind of text. Input with split. You provide the string to be split and an optional delimiter. If no delimiter is given, it defaults to splitting on white space. For join, you provide the iterable list, tuple, etc. that contains the elements to be joined and the string that will serve as the separator e space, comma, or even an empty string. Default behavior split uses white space as default delimiter where none is specified, making it ideal for splitting sentences into words. Join requires a separator, so you must explicitly define what to place between the elements when joining them. Use case, you use split when you want to break down a string, like splitting a comma separated itest of items or a sentence into words. For instance, splitting name age gender into Nazi gender. In contrast, join is while is used to combine elements into a string, so as when formatting a list of items into a sentence or combining parts of a URL. In this example, we are demonstrating two commonly used operations in Python for working with strings. Splitting a sentence into a list of words and joining a list of words back into a sentence. The first operation uses the split method, which breaks a string into a list of substrings or words, in this case based on a specified delimiter. If no delimiter is provided, the method defaults to splitting on whitespace spaces, tabs, or new line characters. In this case, the sentence Python is awesome is split into a list of words Python is awesome. This is useful when you need to process or manipulate individual words within a sentence. The second operation shows how to take a list of words and combine them back into a single string using the join method. Here, the list Python is awesome is joined back into the original sentence. The dot join words expression joins the list elements with a space as the separator between each word, producing the sentence Python is awesome. This method is helpful when you need to rebuild a sentence after manipulating or processing the words. Question 13. Explain the difference between shallow copy and deep copy. Definition: a shallow copy creates a new object, but it only copies the references to the nested objects contained within the original object. This means that while the outer object is duplicated, any changes made to the nested objects within the copy will reflect in the original object. In contrast, a deep copy creates a new object along with independent copies of all the objects nested inside it. This means both the outer and inner objects are fully duplicated, and changes made to the nested objects in the deep copy will not affect the original object. Copy type: in a shallow copy, only the top level structure of the object is copied and references to the original nested objects are maintained. This is why it's considered a surface level copy. For a deep copy, on the other hand, it goes beyond just copying the top level object and also duplicates it all objects nested within it, making it a completely independent copy. Changes to nested objects: when using a shallow copy, changes made to nested objects inside the copied object will affect the original object because both the original and copied objects reference the same nested objects. For example, if you modify a list inside a shallow copy, the same change will appear in the original list. With a deep copy, changes made to nested objects do not affect the original object because all objects, including those inside the copy, are fully independent. Performance: a shallow copy is faster and more memory efficient because it does not duplicate nested objects, it only creates new references to them. This makes it suitable for simple structures or when copying large objects where deep duplication isn't necessary. A deep copy, however, takes more time and consumes more memory because it duplicates the entire structure, including all nested objects. Use case: shallow copy is generally used when working with simple objects or objects that don't contain deeply nested structures, especially when you don't intend to modify the nested objects. Deep copy, on the other hand, is more suitable for complex, deeply nested objects where you want complete independence between the original and the copied objects. Models used in Python: you can perform a shallow copy using copy.copy, which is part of the copy module. To create a deep copy, you use copy.deepcopy, on which ensures that the entire structure of the object is copied. Example: for a shallow copy, you can create one by spelling shallow underscore copy copy.copy original underscore list. For a deep copy, you would use deep underscore copy copy dot deep copy original underscore list, ensuring that even nested objects are duplicated independently. Practical implementation for shallow copy. In this example, we are exploring the concept of a shallow copy in Python using the copy.copy function from the copy module. A shallow copy creates a new object, in this case a new list, but does not recursively copy the objects contained within the original object. This means that for a list of lists, a nested list structure, the shallow copy will copy the outer list, but the nested list inside it will still reference the same memory locations as in the original list. In the example, original underscore list contains two nested lists 1, 2, 3, 4, 5, 6. When we create a shallow copy of original underscore list using shallow underscore copy dot copy original underscore list, a new outer list is created, but the nested lists 1, 2, 3 and 4, 5, 6 are not copied. Instead, both original underscore list and shallow underscore copy share references to the same nested lists. When we modify the first element of the first nested list in the shallow copy, shallow underscore copy 0099, this change is also reflected in original underscore list. This happens because the nested list 123 is shared between both the original and shallow copy, meaning that modifying it in one location affects the other as well. As a result, printing original underscore list shows 9923456, indicating that the first nested list has been modified. This behavior illustrates the limitations of shallow copies in Python. While the outer structure is copied, the inner objects, in this case the nested list, remain shared between the original and the copied version. To fully separate the original and copied objects, a deep copy is required, which recursively copies all objects and nested objects, ensuring complete independence between the original and copied structures. Practical implementation for deep copy. In this example, we are demonstrating the concept of a deep copy using the copy.deepCopy function from Python's copy module. A deep copy is different from a shallow copy in that it creates a new object and recursively copies all objects within it, while uploading any nested structures. In the code, we have an original underscore list that contains two nested lists 1, 2, 3, 3, 4, 5, 6. By creating a deep copy with copy.deepCopy original underscore list, we make a completely independent copy of the original list, including the nested lists inside it. When we modify the deep copy, specifically the first element of the first nested list, deep underscore copy 0099, this change only affects the deep copy and does not impact the original underscore list. This happens because deep copying ensures that each element, including nested lists, is fully duplicated, so any modifications to the copy do not reflect back to file. This contrasts with a shallow copy, where only the outer structure is copied, but references to nest objects are shared between the original and the copy. In the case of a deep copy, each nested list is also duplicated, ensuring complete separation between the original and copied lists. When we print original underscore list, we see that it remains unchanged 1, 2, 3, 4, 5, 6, despite modifications made to the deep copy. This highlights the benefit of deep copying. It provides complete independence between the original and copied objects, making it a useful tool when working with complex data structures that include nested elements. Question 14. What is the list comprehensions in Python? List comprehension offers a neat and concise way to create lists by applying a specific expression to each item in an iterable like a list or tuple. You can also add an optional condition to filter out items that don't meet certain criteria. The syntax is simple. You define the expression that gets applied to each followed by the item itself and the iterable you are looping through. If needed, you can also include a condition to filter out unwanted items, making list comprehension a highly efficient tool for generating lists. Practical implementation. In this example, we are using list comprehensions in Python to efficiently generate lists based on certain conditions and operations. A list comprehension allows us to create a new list by iterating over a sequence like a range of numbers and optionally applying a condition or transformation to each element in the sequence. The first list comprehension x2 for x in range 6 generates a list of squares for numbers between 0 and 5. The range 6 function provides numbers from 0 to 5 and for each number x, the expression x2 calculates its square. This results in the list 0, 1, 4, 9, 16, 25. This approach is both concise and efficient as it generates the list in a single line of code without the need for a loop. The second list comprehension, x for x in range 10 if x% 20, generates a list of even numbers between 0 and 9. Here the range 10 function provides numbers from 0 to 9, and the condition x% 20 ensures that only even numbers, those divisible by 2, are included in the final list. As a result, we get the list 0 to 468. The conditional filtering in list comprehensions allows you to easily control which elements are included, making the code more readable and efficient compared to traditional looping methods. Practical implementation nested list comprehension. In this example, we are working with a nested list in Python, which is essentially a list of lists. The nested underscore list variable contains three sublists 1, 2, 3, 4, 5, 6, 7, 8, 9. Each sublist can be thought of as a row, making the structure similar to a 2D grid or matrix. Nested lists are often used when you need to store or work with multidimensional data. The first operation demonstrates how to access elements within a nested list. To access a specific element, we use two indices. The first index specifies the sublist and the second index specifies the element within that sublist. For example, nested underscore list 01 retrieves the second element 2 of the first sublist 1, 2, 3. This indexing technique allows precise access to individual elements within the nested structure. We then modify an element in the list by directly assigning a new value to a specific position. In the example, nested underscore list 1 to 10 changes the third element, 6 of the second sublist, 4, 5, 6 to 10. As a result, the list is updated to 1, 2, 3, 4, 5, 10, 7, 8, 9. This demonstrates how easily nested lists can be modified at any depth. Finally, we use a nested loop to iterate through the entire nested list. The outer loop goes through each sublist, the outer loop iterates through each element of the current. This allows us to print all the elements in the nested list in sequence, outputting 1, 2, 3, 4, 5, 1, 0, 7, 8, 9. This technique is particularly useful when working with matrices or multidimensional arrays, where each element needs to be processed individually. Question 15. What is the dictionary comprehensions in Python? Dictionary comprehensions in Python allow you to create dictionaries in a concise and readable way by generating both keys and values through an expression applied to an iterable. The basic syntax involves specifying the key value expressions inside curly braces followed by a loop to iterate over the iterable. You can also add a condition to filter elements. This method is efficient for transforming or filtering data into a dictionary or format schema code compact and clear. Practical implementation. In this example, we are using dictionary comprehensions in Python to create dictionaries in a concise and efficient way. A dictionary comprehension allows us to generate key value pairs in a single line of code by iterating over a sequence and applying any necessary transformations or content. The first example, squares underscore dict x x2 for x in range 5, generates a dictionary where the keys are numbers from 0 to 4 and the values are the squares of those numbers. The range 5 function produces numbers from 0 to 4, and for each number x, the key value pair xx2 is generated. This results in a dictionary where each number is associated with its square, producing the output 001, 124, 394, 16. This approach is both concise and easy to read, making it an efficient way to create dictionaries. In the second example, even underscore squares underscore dict x x2 for x in range 10 if x% 20, we add a condition to the comprehension. The comprehension iterates over numbers from 0 to 9 range 10 but only includes even numbers as keys x% 20. For each even number, the key is the number itself and the value is the square of the number x2. This results in a dictionary that contains only even numbers and their squares 002, 44, 16, 6, 36, 8, 64. Practical implementation nested dictionary comprehension. In this example, we are working with a nested dictionary, which is a dictionary where each value is another dictionary. This structure is useful for organizing hierarchical or structured data. In the example, the nested underscore dict contains two main keys, person 1 and person 2, and each of these keys is associated with a dictionary containing personal information such as name and age. This approach allows for a clean and logical way to group related data under one key. We demonstrate how to access elements within a nested dictionary by using multiple keys. For instance, nested underscore dict person 1 name first accesses the dictionary for person 1 and then retrieves the value associated with the name key, which returns Alice. This method of accessing elements is powerful for dealing with complex multi-level data. Next, we show how to modify values within a nested dictionary. Using nested underscore dict person 2 age 26, we update the age value for person 2 from 25 to 26. This showcases how easily individual elements within a nested structure can be changed even though data is stored hierarchically. Finally, we iterate through the nested dictionary using two loops. The outer loop iterates over the main dictionary, retrieving each key, e.g., person 1, person 2, and its associated nested dictionary. The inner loop then iterates through the nested dictionary, retrieving key value pairs such as name, Alice or age 30, and printing them in a formatted way. This iteration method is useful when working with multi-level data that needs to be processed or displayed. Question 16. What is the set comprehensions in Python? Set comprehension in Python is a compact way to create sets, similar to list comprehension but specifically designed for sets. The main difference is that sets are unordered and automatically remove duplicates. With set comprehension, you can apply an expression to each element in a table and optionally filter elements using a condition. The syntax is straightforward: expression for item in iterable if condition. This allows you to quickly generate sets while applying transformations or filtering out unwanted elements in a clean, readable manner. Practical implementation. In this example, we are using set comprehensions in Python to efficiently generate sets. A set is an unordered collection of unique elements, and set comprehensions allow us to build sets in a concise and readable way. The first example demonstrates how to create a set of squares for numbers from 0 to 5. The set comprehension x2 for x in range 6 iterates over the numbers from 0 to 5 and computes their squares x2. The result is a set containing the squares 0, 1, 4, 9, 16, 25. Since sets automatically eliminate duplicates and are unordered, each square is included only once, even in this case all values are unique. The second example shows how to use set comprehensions to create a set of even numbers. The expression x for x in range 10 if x% 20 iterates over the numbers from 0 to 9 and applies the condition x% 20 to filter out only the even numbers. The result is a set containing the even numbers 0 to 4, 6, 8. Set comprehensions allow you to combine iteration and filtering into a single clean expression. Like the first example, this set automatically stores each even number only once, emphasizing the uniqueness property of sets. Practical implementation: nested set comprehension. In this example, we are demonstrating the use of nested sets in Python by utilizing frozen set. Normally, sets in Python cannot contain mutable objects like lists or sets themselves, because sets rely on immutability to ensure that the elements are trimastered. Washable, however, by using frozen set, which is an immutable version of a set, we can create sets of sets, also known as nested sets. The nested underscore set is initialized with two frozen set objects, frozen set 1, 2 and frozen set 3, 4. Since frozen set is immutable, it can be used as an element within another set. This allows us to organize sets hierarchically or group sets together within a larger set. We then demonstrate how to add a new frozen set 5, 6, to the nested underscore set using the add method. This operation modifies the outer set by introducing a new frozen set element, and since sets only allow unique elements, the result ensures there are no duplicates. The addition does not affect the immutability of the inner frozen sets. Next, we use the in keyword to check membership, verifying if a specific frozen set, in this case frozen set 1, 2, is present within the nested underscore set. The output 2 confirms that this frozen set is indeed part of the set, demonstrating how membership checks work seamlessly with frozen sets. Finally, we iterate over the nested underscore set, treating each frozen set as an element in the outer set. Thread iteration retrieves each frozen set in the set, printing it. Since sets are unordered, the frozen sets may be printed in any order, but all elements are unique and immutable. Question 17. What is the difference between split and join in Python? In Python, split and join serve opposite purposes when working with strings. The split method is used to break a string into a list of substrings based on a delimiter. By default, it splits on white space. On the other hand, join takes an iterable like a list or tuple and combines its elements into a single string, inserting a specified delimiter between them. While split returns a list of smaller strings, join produces one large string from multiple parts. These functions are useful for tasks like separating words in a sentence or combining them back into a complete sentence. Practical implementation. In this example, we demonstrate two essential operations for working with strings in Python: splitting a sentence into a list of words and joining a list of words back into a sentence. The first operation uses the split method, which takes a string. In this case, Python is awesome. By default, split breaks the string based on white space, spaces, tabs, or new lines. In this example, it splits the sentence into Python is awesome, where each word from the sentence becomes an element of the list. This technique is helpful when you need to process or manipulate individual words from a string. The second operation uses the join method to combine a list of words back into a single sentence. The dot join words expression takes a list of words like Python is awesome and joins them into a single entry with a space separating each word. This reverses the split operation, reassembling the list back into Python is awesome. Question 18. What is a lambda function in Python? A lambda function in Python is a quick, anonymous way to create a small function using the lambda keyword. Unlike regular functions that use def, lambda functions are used for simple tasks with one expression and can take multiple arguments but return only one result. They are commonly used when a short function is needed for quick tasks without the need for a full function definition, making them useful in places like sorting, filtering, or mapping values. Practical implementation. In this example, we are using lambda functions in combination with Python's built-in map and filter functions to perform transformations and filtering on a list of numbers in a concise way. The first part demonstrates the use of a lambda function with map to square a list of numbers. A lambda function is an anonymous function that is defined in line and used for simple operations. In this case, lambda x2 is a lambda function that takes a number x and returns its square x2. The map function applies this lambda function to each element in the list numbers 1, 2, 3, 4, 5. The result of map is an iterable, so we convert it into a list using list. The final output is a new list containing the squares of the numbers 1, 4, 9, 16, 25. The map function is useful for applying a function to every item in a list without needing to write a loop explicitly. The second part shows the use of a lambda function with filter to extract only the even numbers from the list. The lambda function lambda x %2 equal to 0 checks if a number x is divisible by 2, i.e. whether it is even. The filter function applies this lambda function to each element in the list numbers and returns only those elements that satisfy the condition, i.e. where the lambda returns true. Like map, the result of filter is an iterable which is converted to a list using list. The output is a list of even numbers 2, 4. The filter function is useful for selecting elements from a list based on a condition. Question 19. What is a map? Functions in Python. The map function in Python is used to apply a given function to each item in a table such as a list arrival and returns a map object with the transpose found values. This function is useful when you want to apply the same operation to all elements like converting all strings in a list, uppercase or squaring all numbers in a list. The function works lazily, meaning the transformations are only calculated when the result is accessed. The map function simplifies repetitive tasks by applying a single function across multiple items in an efficient, easy to read way. Practical implementation. In this example, we use Python's map function in combination with a lambda function to efficiently transform a list of numbers by squaring each element. The numbers list contains the values 1, 2, 3, 4, 5, which serve as the input to the map function. The lambda function is defined in line as lambda x2, where x represents each number in the list and x2 calculates its square. The map function applies this lambda function to every element in the numbers list, creating a new iterator, the map object that holds the squared values. However, since map returns an iterator rather than a list, we need to convert this iterator into a list using the list function to view the results. Once converted, the output becomes 1, 4, 9, 16, 25, which are the squares of the original numbers. Question 20. What is a reduce functions in Python? The reduce function is used when you want to take an iterable like a list and reduce it to a single value by applying a function that combines two items at a time. This function keeps applying the operation cumulatively, first combining the first two items, then combining that result with the next item, and so on until you end up with just one final value. For example, you can use reduce to sum up all the numbers in a list or multiply them together. It's handy when you need to combine everything in a collection into a diagonal result, like calculating a total dot product. You can import it from the functools module and apply it to iterable using the syntax reduce function iterable. Practical implementation. In this example, we use Python's reduce function from the functools module combined with a lambda function to compute the sum of all the numbers in a list. The reduce function is designed to apply a given operation cumulatively to all elements in an iterable list, effectively reducing the iterable to a single value. Here we have a list numbers 1, 2, 3, 4, 5, and our goal is to sum all the elements. The lambda function lambda xyx plus y is used to specify the operation we want to perform. It takes two arguments x and y and returns their sum. The reduce function applies this lambda function to the first two numbers in the list 1 and 2, sums them to get 3, and then adds this result to the next number 3, continuing this process until all the numbers are summed. By the end of the operation, reduce has summed all the elements in the list, producing a final result of 15. Question 21. What is the filter functions in Python? The filter function is used to filter elements from an iterable based on a condition defined by a function. This function is applied to each element and only the items that return true are kept. The purpose of filter is to select certain elements from a collection that meet a specific requirement, such as keeping only even numbers or selecting strings that begin with a certain letter. It returns an iterator, meaning it processes items lazily, only evaluating them when needed. The function passed to filter must return true or false, and the result includes only the elements for which the function returns true. Use cases. The filter function in Python extracts elements from a collection based on a condition. It takes a function that defines the condition and an iterable returning only elements for which the condition is true. Commonly used with lists, tuples, or sets, filter helps filter data efficiently without manual loops. For example, you can use filter to keep only even numbers from a list or select strings that start with a specific letter. It's especially useful for tasks like data cleaning or selecting specific elements based on certain criteria. Syntax. Syntax. The syntax of the filter function in Python is filter function iterable. It applies the function to each element in the iterable and returns a new iterator containing only the elements for which the function returns true. The function should be a condition or lambda expression that evaluates to true or false. If the function is none, it simply returns the items in the iterable that are considered true based on Python's truthy and falsy evaluation. Practical implementation. In this example, we use Python's filter function in combination with a lambda function to extract only the even numbers from a list. The list numbers 1, 2, 3, 4, 5 contains both even and odd numbers, and the goal is to filter out the odd numbers, leaving only the even ones. The lambda function lambda x% 2 equal to 0 defines the condition that each element in the list must satisfy to be included in the result. This lambda checks whether each number x is divisible by 2x% 2 equal to 0, which is the definition of an even number. If the condition evaluates to true, the number is kept, otherwise it is excluded. The filter function applies this lambda to each element in the numbers list. It returns an iterator that contains only the elements that satisfy the condition, in this case only the even numbers. Since filter produces an iterator, we need to convert it to a list using list. The final output is 2, 4, which are the even numbers from the original list. Question 22. What is the difference between map and list comprehension? The map function and list comprehensions are both used to apply transformations to items in an interval, but they differ in several key aspects. Definition. The map function applies a given function to each item of an iterable like a list or tuple and returns a map object. On the other hand, list comprehension provides a more concise way to create lists by applying an expression directly to each item in an iterable. Syntax. The syntax for map is map function iterable, where a function is passed and applied to each element of the iterable. List comprehension uses the syntax expression for item in iterable, which allows for concise transformations without explicitly defining a function. Return type map returns a map object which is an iterator and requires conversion to a list if you want to access the results immediately. List comprehensions directly return a list, making them more straightforward when you want a list as the final result. Readability. For simple transformations, list comprehensions are typically more readable and intuitive compared to map, especially when lambda functions are used in map, which can make the code harder to understand. Function requirement. Map requires a function as its first argument, whether it's a built-in function, user-defined function, or a lambda expression. List comprehension, however, works directly with any expression without needing a separate function. Multiple iterables. A key advantage of map is its ability to handle multiple iterables at once. You can pass multiple iterables to map and apply a function to them in parallel. List comprehension, in contrast, does not natively support multiple iterables, though it can be combined with Z to achieve similar functionality. Performance. In terms of performance, map can be more efficient for large datasets because it returns an iterator and processes elements lazily. List comprehensions, on the other hand, generate the entire list in memory, which may be slower or more memory intensive for large datasets. Use case. Use map when you have an existing function that you need to apply to each item in an iterable. List comprehensions are best suited for simple readable transformations or when you need to apply expressions or filtering in a more concise manner. Practical implementation. In this example, we are using Python's map function in combination with a lambda function to efficiently square each element in a list of numbers. The list numbers 1, 2, 3, 4 serves as the input, and the goal is to square every number in the list. The lambda function lambda x, x2 is an inline, anonymous function that takes each number x as input and returns its square x2. The map function applies this lambda function to every element in the list numbers, producing a map object which is an iterator that generates the squared values. However, since the result is an iterator, we use list to convert it into a list so that we can view the squared numbers. The final output of this operation is 1, 4, 9, 16, which contains the squares of 1, 2, 3, and 4. This approach is efficient and concise, avoiding the need for explicit loops or multiple lines of code to square each element. By using map in combination with the lambda function, we can apply a transformation to all elements of an iterable in a clean and a clean way. This is a great example of how Python's functional programming tools simplify the process of applying a function to a list of elements. Practical implementation of list comprehension. In this example, we are using list comprehension in Python to square each element of a list. The list numbers 1, 2, 3, 4 contains the original numbers, and our goal is to create a new list where each number is squared. The list comprehension syntax x2 for x in numbers provides a concise way to achieve this. Here, x2 is the expression that calculates the square of each number x, and the loop-like structure for x in numbers iterates over each element in the numbers list. For each iteration, the value of x is squared, and the result is collected into a new list, which is stored in the variable squared. The resulting list 1, 4, 9, 16 contains the squares of the original numbers 1, 2, 3, and 4. This method is not only efficient but also very readable, as it allows the transformation of a list in a single line of code without the need for explicit loops. List comprehensions are a powerful feature in Python, providing a clear and Pythonic way to create new lists by applying operations to the elements of existing listing. They are commonly used when transforming, filtering, or generating lists based on some condition or operation. Question 23. What are args and quarks in Python? In Python, args and quarks are used to handle a variable number of arguments in function definitions, but they serve different purposes. Purpose: the args parameter allows a function to accept any number of position arguments, making it flexible when the number of arguments is not fixed. For example, if a function can receive a varying number of inputs, args collects these arguments into a tuple. On the other hand, quarks is used for keyword arguments, uh, allowing a function to accept any number of named arguments which are collected into a dictionary. Type: when you use args, the arguments passed to the function are stored in a tuple, whereas quark stores keyword arguments in a dictionary. This difference allows args to handle positional arguments and quarks to handle key value pairs as input. Use case: you would use args when you are unsure about the number of positional arguments the function will receive. This is useful for scenarios where the function's input varies but the arguments are ordered. Quarks is useful when the function needs to accept any number of keyword arguments without predefined parameter names. Syntax in function definitions: args is placed as a parameter to collect multiple positional arguments, while quarks collects multiple keyword arguments. For example, deffunc defines a function that can accept positional arguments, and deffunc defines one that can accept keyword arguments. Accessing values passed via args can be accessed by iterating over the tuple. In contrast, quarks allows you to access values by referring to the keys of the dictionary, making it easier to handle named inputs. This flexibility with args and quarks allows functions to accommodate a wide variety of inputs, making them more adaptable in different contexts. Practical implementation. In this example, we are using the args feature in Python, which allows a function to accept a variable number of arguments. The sum underscore numbers args function can handle any number of input values, as args collects all the arguments passed via to the function into a tuple. This is especially useful when the number of arguments is not fixed or can vary between function calls. Inside the function, we initialize a variable total to 0, which will store the sum of the arguments. We then iterate over the args tuple using a for loop. In each iteration, the current argument represented by num is added to the running total. Once all arguments have been processed, the final sum is returned by the function. The function is then called twice, first with three arguments 1, 2, 3, which returns 6, and second with four arguments 5, 10, 15, 20, which returns 50. This demonstrates the flexibility of ours as the function can dynamically handle different numbers of inputs without needing to explicitly specify them in the function definition. The args feature is a powerful tool in Python that makes functions more versatile, enabling them to process varying numbers of inputs. It simplifies situations where the number of arguments is unknown or where you want to allow for flexibility in the number of inputs provided by the user or another part of the program. Practical implementation of quads. In this example, we use Python's quads feature, which allows a function to accept an arbitrary number of keyword arguments. Keyword arguments are passed to the function as key value pairs, and quads collects all these arguments into a dictionary. In the function readQuartz, the Quartz syntax enables the function to receive any number of named arguments without explicitly defining them in the function signature. Inside the function, we use a for loop to iterate through the dictionary of keyword arguments. The quartz.items method provides access to both the key's argument names and values the corresponding data. The function prints each key and its associated value, producing a structured output. For example, when the function is called as greet name John, age 25, city New York, the keyword arguments name, age and city are passed into Quartz as a dictionary name, John, age 25, city New York. The function then iterates through this dictionary and prints the key value pairs as name, John, age 25, city New York. The quartz mechanism is useful when you need to handle a variable number of named arguments, especially in cases where the set of arguments may vary between different function calls. This provides flexibility and makes functions more adaptable as they can accept and process optional parameters or varying data without rigid definitions. Question 24. What are Python iterators and how do they work? In Python, iterators are objects that enable sequential traversal of a collection such as lists, tuples, or dictionaries without revealing the underlying data structure. They allow access to each element in a collection one at a time, which is particularly useful when working with large data sets or when only partial data is needed. Key components of iterators. An iterator is created using the iter function, which converts an iterable like a list or tuple into an iterator object. Once an object is converted into an iterator, it can be traversed using the next function, which reads elements one by one. If there are no more elements to return, the iterator raises a stop iteration exception, signaling the end of the data stream. How iterators work. In Python, iterable objects are any objects capable of returning an iterator. These objects include common data structures like lists, tuples, dictionaries, and sets. You can obtain an iterator from an iterable object by calling the iter function on it. Essentially, iterable objects can be looped through, but they themselves are not iterators until they are transformed into one using iter. Iterator is an object that implements two essential methods underscore underscore iter and underscore underscore next. The underscore underscore iter method is required to return the iterated object itself, making it iterable, while the underscore underscore next method retrieves the next element from the collection. When there are no more elements to retrieve, the underscore underscore next method raises a stop iteration exception, signaling the end of the iteration process. Unlike lists or other data types that can be indexed directly, iterators work by generating the next element on request. Iteration is the process of accessing elements in a sequence one at a time. This can be done using a for loop, which implicitly calls the underscore underscore next method on the iterator in each loop cycle, or manually by calling next on the iterator. This allows you to traverse through elements without needing to know the underlying data structure, making iterators both memory efficient and flexible, especially for large datasets or streams of data. Practical implementation. In this example, we demonstrate how to create and work with an iterator using Python's iter and next functions. An iterator allows you to traverse a collection, such as a list, one element at a time, without needing to load all the elements into memory at once. Here we have a list numbers 1, 2, 3, 4, 5, and we use iter numbers to create an iterator object that can traverse the list sequentially. The iter function returns an iterator for the given list, which stores the current position in the list and allows us to retrieve elements one by one. Once we have the iterator, we use the next function to access elements from the list. The first call to next iterator retrieves the first element, which is 1. When we call next again, it retrieves the next element, 2, and so on. The iterator remembers its position, so each call to next moves to the following element. This approach is beneficial when dealing with large datasets, as iterators allow you to process data incrementally without loading the entire dataset into memory. It also provides more control over the iteration process, enabling you to pause, resume, or manipulate the traversal as needed. The use of iter and next is fundamental to Python's iteration protocol and underpins many built-in operations such as loops and generators, making it a key concept in understanding how Python handles iteration efficiently. Question 25. How do you write a function in Python? In Python, writing a function involves defining a block of reusable code that performs a specific task. A function starts with the def keyword followed by the function name and parentheses. You can pass parameters inside the parentheses, allowing the function to receive input when called. The body of the function is indented and contains the code to be executed. A function can also return a value using the return statement, making it highly versatile. Functions help break code into smaller modular sections, improving organization, readability, and reusability by allowing you to invoke the function multiple times without duplicating code. Syntax for defining a function. In Python, defining a function begins with the def keyword followed by the function name, parentheses, and a column. Inside the parentheses, you can specify parameters that the function will accept as input. The body of the function, which contains the code that will execute when the function is called, is indented. If the function needs to return a value after execution, you can use the return statement. Otherwise, it will retain none by default. Functions are essential for modularizing and using code, making programs more organized and manageable. Practical implementation. In this example, we define a versatile function called order underscore summary that demonstrates the power of combining regular parameters, default values, args for handling variable length arguments, and quacks for processing keyword based arguments. The function is designed to generate a summary of a food order, allowing for flexible inputs that cater to various scenarios. The function accepts a mandatory name parameter which represents the customer's name and a main underscore item parameter which defaults to Berger if not explicitly provided. This allows the user to specify a different main item, but if no input is provided, the default will be used. The extras parameter is used to collect any additional items such as side dishes or drinks passed to the function. These are collected as a tuple and handled inside the function by checking if any extras were provided and printing them one by one. The quartz parameter is used to capture any keyword arguments that provide additional details about the order such as delivery time or payment method. The function processes these details by iterating over the dictionary created by Quarks and printing each key value pair, making it easy to handle a variety of extra information dynamically. The function returns a summary string that indicates how many extras were included in the order, giving feedback on the user's input. It can handle different use cases from a simple order with default values to more complex scenarios involving extras and additional details. By combining these elements, this function demonstrates how Python's args and quartz features allow for flexible function design, making it possible to handle varying numbers of inputs and optional details without overcomplicating the function signature. This approach is particularly useful for situations where the inputs may vary across different function calls, providing a clean and adaptable solution. Question 26. What are decorators in Python? In Python, decorators are a flexible and powerful tool that lets you modify or enhance the behavior of functions or methods without changing their original code. They act as wrappers, allowing additional functionality to be executed before or after the wrap function runs. Decorators are commonly used for tasks such as logging, authentication, timing, and caching, among others. You apply decorator by prefixing the function definition with the at decorator underscore name syntax, making it easy to reuse and maintain clean, modular code. This helps in improving the readability and functionality of functions without altering their code logic. Key concepts in Python, functions are considered first class objects, meaning they can be treated like any other object. This allows them to be passed as arguments to other functions, returned from functions, and assigned to variables, which is the foundation that makes decorators possible. Decorators are an example of higher order functions, which are functions that take other functions as arguments or return them. A decorator in particular takes a function and adds or modifies its behavior without changing the original function's code. This capability provides a flexible way to extend functionality, making the code more usable and maintainable. Syntax. In Python, decorators are applied to functions using the at decorator underscore name syntax, which is placed directly above the function definition. This is a shorthand way of applying a decorator to a function, making the code cleaner and easier to read. When a function is decorated, Python internally passes that function to the decorator, allowing it to modify or extend the function's behavior. That symbol is followed by the name of the decorator function, and this notation simplifies the process of applying decorators without needing to manually call the decorator each time. Practical implementation. In this example, we demonstrate the use of a Python decorator, which is a powerful feature that allows you to modify or enhance the behavior of a function without directly changing its code. The decorator function my underscore decorator takes another function as an argument, in this case say underscore hello, and returns a modified version of that function, adding additional behavior before and after the original function executes. The decorator works by defining a wrapper function inside my underscore decorator. This wrapper function adds custom behavior around the execution of the original function. When the wrapper is called, it first prints a message something before the function, then executes the original function, and finally prints another message something after the function. By returning the wrapper, the original function is replaced with this enhanced version that includes the additional behavior. The decorator is applied using the at my underscore decorator syntax, which is shorthand for applying the decorator to the function say underscore hello. This is equivalent to manually assigning say underscore hello my underscore decorator say underscore hello. As a result, when say underscore hello is called, it first runs the wrapper code printing the messages before and after, and then calls the original say underscore hello function, which prints hello. Decorators are useful for adding reusable functionality to functions without altering their internal logic. This is especially helpful for cross-cutting concerns like logging, authentication, or timing, where you want to augment many functions with similar behavior without repeating code. The decorator pattern promotes clean modular code and is a fundamental concept in Python programming. Question 27. What class-based decorator is in Python? A class-based decorator in Python works similarly to function-based decorators, but it's implemented using a class instead of a function. It allows you to modify or extend the behavior of functions or methods, offering more structure and flexibility. Why use class-based decorators? Class-based decorators are ideal when you need to maintain state across multiple function calls. Since instance variables can store data, class-based decorators provide more control and can handle more complex behaviors than function-based ones. They also enhance readability and structure, especially when the logic is complex or involves multiple methods. Steps to create a class-based decorator. 1. Define a class to act as the decorator. 2. In the classes underscore underscore init underscore underscore method, accept and store the function that will be decorated. 3. In the underscore underscore call underscore underscore method, handle the function call and modify its behavior, such as adding pre or post processing steps. This allows the class to behave like a function, making it work as a decorator. Practical implementation. In this example, we create a class-based decorator using Python's underscore underscore call underscore underscore method, which allows an instance of a class to be called like a function. The decorator class myDecorator is designed to wrap a function and add behavior before and after the function's execution. This is similar to how function-based decorators work, but using a class provides more flexibility and structure, especially if you need to maintain state or handle more complex logic. When we apply the decorator to a function using that myDecorator syntax, the underscore underscore init underscore underscore method is called, storing the original function in the instance variable self.func. This allows the decorator to remember the function it is wrapping. The key functionality of the class-based decorator is in the underscore underscore call method, which is automatically invoked when the decorated function is called. The underscore underscore call method allows us to inject behavior around the function call. In this case, it prints a message before and after calling the original function self.funcArgs, which handles the actual function execution. When we call the decorated function greetAlice, the class's underscore 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 method is executed. It prints before calling the function, then calls the original greet function, which prints hello, Alice, and finally it prints after calling the function. This demonstrates how decorators can modify the behavior of functions in a non-intrusive way, adding functionality before or after the main logic. Class-based decorators are especially useful in situations where you need more control or additional features, such as maintaining state across multiple calls or performing more complex operations. The ability to use a class for this purpose makes decorators not only more powerful but also easier to manage in larger codebases. Question 28. What is a Python closure? A closure in Python is a function that remembers variables from its surrounding scope even after the outer function has completed execution. This allows the inner function to retain access to those variables, enabling it to maintain and use the environment it was created in. Key features. A closure has three key features. First, it involves a nested function, meaning an inner function is defined inside an outer one. Second, it captures variables from the outer function and remembers them even after the outer function has finished executing. Lastly, closure is retain state, allowing the inner function to maintain access its state across multiple calls. When to use closures? Closures are useful when you need a function to maintain its own state across multiple calls without relying on global variables or creating a class. They provide a way to encapsulate both functionality and data, allowing you to create specialized functions that remember values within their own environment. This makes closures great for cases where you need to preserve specific data while keeping it hidden from the rest of the code. Practical implementation. In this example, we demonstrate the concept of closures in Python. A closure occurs when a nested function and inner function captures and remembers variables from its enclosing outer function scope, even after the outer function has finished executing. In this case, we define an outer underscore function that contains a local variable message with the value hello from the closure. Inside this outer function, we define an inner score function that prints the message variable. The key part of this example is that the outer underscore function returns the inner underscore function without executing it. This return function is then assigned to my underscore closure. When we call my underscore closure, it invokes the inner underscore function. Even though the outer underscore function has finished its execution, the inner underscore function still has access to the message variable thanks to the closure. This behavior demonstrates how closures allow inner functions to capture variables from their outer function's environment and retain access to them, even after the outer function has exited. The output of my underscore closure is hello from the closure, which illustrates that the inner function can still access the message variable. Closures are powerful because they enable functions to remember their environment, which can be useful in various scenarios such as function factories, callbacks, or when you need a function that maintains some state without using global variables. They allow for more modular, flexible code and are an essential part of functional programming in Python. Question 29. How do you create a generator in Python? In Python, generators are a special kind of iterable that generate values on the fly, yielding one value at a time when needed. This approach makes them highly memory efficient as they don't store the entire sequence in memory. Generators are easy to create using either generator functions, which use the yield keyword, or generator expressions, which are similar to list comprehensions but with parentheses. They are especially useful when working with large datasets or streams of data where generating all values at once would consume too much memory. 1. Using a generator function. A generator function works like a regular function, but instead of returning a single value, it yields multiple values one at a time using the yield keyword. Each time it yields, the function pauses, and when more values are needed, it resumes where it left off. This allows for efficient on-demand generation of values without holding everything in memory at once. Practical implementation. In this example, we demonstrate the concept of generators in Python, which allow for the efficient generation of values one at a time using the yield keyword. A generator function is defined using yield instead of return, enabling the function to produce a sequence of values lazily, that is, it generates values as they are requested rather than all at once. In this case, the function my underscore generator yields values from 0 to 4 using a for loop with range 5. Each time the yield statement is encountered, the generator pauses execution and returns control to the caller while maintaining its state. This allows the function to resume where it left off when the next value is requested. When the generator function is called genMy underscore generator, it doesn't execute the code immediately. Instead, it returns a generator object which can be iterated over. The actual execution of the generator happens when the next function is called, either explicitly or implicitly through a for loop. In this case, the for loop automatically retrieves the next yielded value from the generator during each iteration, printing the values 0, 1, 2, 3, and 4 sequentially. Generators are particularly useful in situations where we want to handle large datasets or streams of data without loading everything into memory at once. By yielding values one at a time, generators provide an efficient way to iterate over potentially infinite sequences or large amounts of data, making them an essential tool in Python for memory optimization and efficient data processing. 2. Using a generator expression. A generator expression is just like a list comprehension, but instead of using square brackets, it uses parentheses and creates a generator object. This means that unlike a list, it doesn't store all the values in memory at once. Instead, it generates each value on the fly as needed, making it more memory efficient for large datasets or infinite sequences. Practical implementation. In this example, we use a generator expression to create a sequence of squared numbers from 0 to 4. A generator expression is similar to a list comprehension, but instead of generating and storing all the values at once, it produces values lazily one at a time as they are needed. This makes it more memory efficient, especially when working with large datasets or streams of data, since it doesn't load all values into memory simultaneously. The generator expression gen underscore xp x2 for x in range 5 calculates the square of each number in the range from 0 to 4. The expression itself does not perform any calculations immediately. Instead, it returns a generator object which can be iterated over to produce the squared values. When the for loop begins, the generator expression yields each value one by one. In each iteration, the loop retrieves the next squared value from the generator, prints it, and then moves on to the next number. The output is the sequence of squares 0, 1, 4, 9, and 16. Generator expressions are highly efficient because they allow you to generate values on demand, making them particularly useful for handling large or infinite sequences. Instead of creating an entire list in memory, you get the values only when you need them, which is ideal for memory constrained environments or when you only need a portion of the generated values. This compact and efficient approach is one of the key features that make Python generators powerful for data processing tasks. Question 30. What is the purpose of yield in Python? The yield keyword in Python allows a function to pause its execution and return a value to the caller while maintaining the function state. This makes the function a generator, enabling it to produce a sequence of values over time rather than all at once. When the function is called again, it picks up where it left off, continuing from just after the yield statement. This makes yield ideal for creating iterators, managing memory efficiently, and handling large datasets or streams of data step by step. Key features of yield. Yield is a powerful feature in Python that transforms a regular function into a generator, allowing it to produce values one at a time instead of all at once. This makes it ideal for handling large datasets efficiently as it doesn't require loading everything into memory at once. Every time a generator is called, it resumes from where it left off, preserving the function's local variables and position. Since values are generated only when requested, yield supports lazy evaluation, which is perfect for working with large collections or data streams on demand. Practical implementation. In this example, we define a generator function called underscore up underscore to n that generates a sequence of numbers from 1 up to a specified number n. The key feature of a generator function is the use of the yield keyword, which allows the function to produce values one at a time rather than returning all the values at once. Each time the generator yields a value, it pauses execution and saves its state, allowing it to resume from where it left off when the next value is requested. The generator function starts with an initial count of 1 and continues to yield the current value of count as long as it is less than or equal to n. After each yield, the count is incremented by 1. This means that instead of generating all numbers in memory at once, the function produces each number only when requested, making it memory efficient, especially for larger ranges. When we call count underscore up underscore to 5, it returns a generator object. This object doesn't execute the function immediately but provides an iterator that can be used to retrieve the yielded values one by one. Using a for loop to iterate over the generator object, the loop automatically requests the next value by calling next on the generator, retrieving the numbers in sequence 1, 2, 3, 4, 5. This approach is particularly useful when dealing with large datasets or when we need to generate values on demand. Generators are more efficient than functions that return entire lists as they reduce memory usage by yielding values only as needed, making them ideal for handling sequences or streams of data in a more scalable manner. Question 31. How are arguments passed in Python, by reference or by value? In Python, arguments are passed using pass by object reference, which means the function gets a reference to the object, not the actual object itself. If the object is mutable like a list or dictionary, changes made inside the function will affect the original object. However, if the object is immutable like a string or tuple, any changes will create a new object, leaving the original unchanged. This provides flexibility in how objects are handled depending on their mutability. When mutable objects like lists, dictionaries, or sets are passed to a function, the function can modify the original object since the reference points to the same memory location. However, with immutable objects like integers, strings, or tuples, the function cannot modify the original object directly. Any changes result in the creation of a new object in memory, leaving the original object unchanged. This distinction is crucial for understanding how Python handles data inside functions. Object type-wise behavior when passed to a function. In Python, arguments are passed neither strictly by reference nor by value. Instead, Python uses a mechanism called pass by object reference or pass by assignment. The behavior depends on whether the object being passed is mutable or immutable. When mutable objects like lists, dictionaries, or sets are passed to a function, the function can modify the original object because the reference to the same memory location is passed. However, when immutable objects like integers, strings, or tuples are passed, the function cannot alter the original object. Any modification results in a new object being created in memory, leaving the original object unchanged. This distinction is important when working with functions that modify their inputs. Practical implementation. In this example, we demonstrate how lists in Python are mutable, meaning they can be modified after creation. The function modify underscore list my underscore list takes a list as an argument and appends the number 4 to it using the append method. When a list is passed to the function in Python, it is passed by reference, not by value. This means that the function operates directly on the original list object, not a copy of it. As a result, any changes made to the list within the function will affect the original list outside the function. In the example, we define the list 1, 2, 3 and pass it to the function modify underscore list. Inside the function, the append 4 operation adds the number 4 to the list. Since the list is passed by reference, this modification is applied directly to the original list last after calling the function. When we print else, the output is 1 2 3 4, showing that the function has successfully modified the original list by adding the number 4. This behavior highlights the mutable nature of lists in Python, allowing for efficient modifications to a list passed into a function. It also emphasizes how changes to mutable objects inside a function can persist outside the function, making it important to understand the implications of passing mutable objects like lists, dictionaries, and sets to functions. In next example, we demonstrate how immutable objects such as integers behave when passed to a function in Python. The function modify underscore number x takes an integer x as an argument and attempts to modify it by adding 10. However, integers in Python are immutable, meaning they cannot be changed once created. When the variable num is passed to the function, Python passes a copy of the value, not the actual variable itself. This is known as passing by value for immutable types. Inside the function, the operation extend adds 10 to the local copy of x, but since x is a separate copy, it doesn't affect the original variable num outside the function. As a result, when the function finishes executing, the original num remains unchanged. When we print num, it still holds the value 5, showing that the function's attempt to modify the number was only applied to a local copy of the value, and the original value remains intact. This behavior highlights an important aspect of Python. While mutable objects like lists can be changed inside functions and affect the original object, immutable objects like integers, strings, and tuples cannot be altered in the same way. Any modifications to immutable objects inside a function only affect local copies, leaving the original copies the fading the function. Understanding this distinction between mutable and immutable objects is crucial for writing functions that handle data properly in Python. Question 32. How do you create and work with context managers? Context managers in Python are a convenient way to handle resource management, ensuring that resources like files, network connections, or database connections are properly opened and closed. The most common way to create and use a context manager is through the with statement, which simplifies resource handling by automatically managing setup and cleanup tasks. When you use a with statement, it guarantees that the resource is cleaned up or released as soon as the block of code is exited, even if an error occurs during execution. Well, for example, when working with file handling, using a with open block ensures the file is automatically closed after the operations are completed, eliminating the need for manual closure and reducing potential errors or resource. Additionally, custom context managers can be created by defining a class with underscore underscore enter and underscore underscore exit methods, or using the contexted modules that contain decorator for more complex scenarios. Practical implementation. In this example, we create a custom context manager class file manager to handle the opening and closing of files in Python. Context managers are particularly useful for managing resources such as files, databases, or network connections because they ensure that resources are properly acquired and released even if an error occurs during their use. The context manager uses two special methods, underscore underscore enter and underscore underscore exit. The underscore underscore enter method is called when we enter the with block, and it opens the file using the parameters provided file name and mode. It then returns the file object, which can be used inside the with block. In this case, the file object is assigned to f. This allows us to write data to the file or perform other file operations. The real advantage of using a context manager comes from the underscore 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 exit method, which is automatically called when we exit the with block, regardless of whether the block finishes successfully or an exception is raised. This method ensures that the file is properly closed to avoid resource leakage. If an exception occurs, the underscore underscore exit method can capture and handle the exception, printing the error details and deciding whether to suppress or propagate the error. This approach simplifies file management and ensures safety, as the file is guaranteed to be closed properly without the need for manual close calls. The use of a custom context manager adds flexibility by allowing us to handle specific behaviors like exceptions when working with resources, making the code cleaner and more reliable. The context manager pattern is a powerful tool for writing resource-safe Python code. Question 33. What is the purpose of Python's with statement? The with statement in Python is designed to ensure that resources are properly managed. When dealing with resources like files, network connections, or logs, it is important to acquire and release them correctly to avoid resource leaks, which can lead to errors and inefficient use of memory or connections. The with statement simplifies this process by ensuring that resources are automatically acquired at the beginning of the block and released when the block is exited, regardless of whether an exception is raised or not. For example, when opening a file using the with statement, Python automatically closes the file once the code block inside the with statement is completed. This eliminates the need to explicitly close the file, reducing the risk of forgetting to release the resource. The with statement works with context managers, which define how resources are acquired and released through the underscore enter and underscore exit methods. Key features. Now, the with statement in Python offers several key features that make resource management easier and more efficient. One of its primary benefits is automatic resource management, which ensures that resources like files, networks, connections, or logs are automatically released after use, even in the event of an error or exception. This guarantees that resources are always properly cleaned up, reducing the risk of resource leaks or errors. Another important aspect is its simplified syntax, which replaces the need for more complex try finally blocks. By using the with statement, the code becomes more concise and easier to read, reducing the likelihood of forgetting to release resources explicitly. The with statement works closely with context managers, which implement the underscore enter and underscore exit methods. These methods handle the setup and cleanup of resources automatically, an effective way to manage resources in a consistent and safe manner. Benefits. Using the with statement in Python provides several key benefits that enhance code quality and reliability. One of the main advantages is that it results in cleaner code. By eliminating the need for manual resource management, such as explicitly opening and closing files or connections, the with statement simplifies the process, making the code more readable, concise, and easier to maintain. Another significant benefit is improved error handling. The with statement ensures that resources are properly released or cleaned up, even if an error occurs during the execution of the block. This automatic handling reduces the risk of resource lacks and helps prevent potential bugs that may arise from improper resource management, making the code more robust. Practical implementation. In this example, we demonstrate how to safely write to and read from a file using Python's with statement, which simplifies resource management by ensuring that files are properly opened and closed. The with statement is commonly used in file handling because it provides an easy and reliable way to work with files without manually closing them, even in cases where an error might occur during the file operation. In the first part of the code, we open the file example.txt in write mode using the with open syntax. This ensures that the file is open for writing, and if it doesn't exist, it will be created. Inside the with block, we use the file.write method to write a string to the file. Once the with block is exited, the file is automatically closed, ensuring that the changes are saved and the file resource is properly released. In the second part, we use another with open block to open the same file in read mode read. This allows us to read the contents of the file using the file.read method. The contents are stored in the content variable, which is then printed to the console. Again, the file is automatically closed once the with block is exited. By using the with statement, we avoid potential issues like forgetting to close the file or accidentally leaving a file open for too long, which can lead to resource leaks or file corruption. The with statement provides a clean, efficient, and error-resistant way to handle file input and output operations in Python. Question 34. What is the purpose of the global and non-local keywords? In Python, the global and non-local keywords are essential for managing variable scope, allowing developers to modify variables that exist outside of the current function or scope. The global keyword is used when you want to refer to a variable that is distinct the global top level scope from within a function. Without this keyword, any attempt to modify a global variable inside a function would create a new local variable instead. By declaring a variable as global, you can access and modify its value throughout the program. On the hand, the non-local keyword is used within nest functions to access variables from the enclosing non-global scope. This is particularly useful when you have a function inside another function and you need to modify a variable that is neither local to the inner function nor global. Non-local allows you to bridge this gap by enabling access to variables from the nearest enclosing scope that is not global, ensuring proper variable sharing between nested functions. Keywords play crucial roles in controlling how and where variables can be accessed or modified in Python. 1. Global keyword. The global keyword in Python is used when you want to refer to a variable that exists at the global scope from within a function. By default, any variable that you define inside a function is treated as a local variable, meaning that it is only accessible and modifiable within that function. If you try to modify a global variable inside a function without declaring it as global, Python will create a new local variable with the same name, leaving the global variable unchanged. To avoid this and explicitly tell Python that you intend to work with the globally defined variable, use the global keyword. This ensures that any changes made to the variable within the function will directly affect the global variable, making it accessible and modifiable throughout the entire program. This is useful when you need to share or update a value across multiple functions or scopes in a Python script. Key purpose. A. The key purpose of the global keyword in Python is to access and modify variables that are defined in the global scope from within a local function. Without using the global keyword, any assignment to a variable inside a function would create a new local variable, leaving the global variable unaffected. By declaring the variable as global within a function, you ensure that the function refers to the globally defined variable, allowing the function to read, modify, or update its value. This is especially useful in cases where the state or value of a variable needs to be shared and updated across different functions within a program. Practical implementation. In this example, we explored the concept of global variables in Python and how to modify them inside a function using the global keyword. A global variable like x equal to 10 is declared outside of any function and is accessible throughout the entire program. By default, if a function contains a variable with the same name as a global variable, Python treats it as a local variable, meaning it will only exist within the scope of that function and any changes to it will not affect the global variable. To modify a global variable inside a function, we must explicitly tell Python that we want to work with the global variable by using the global keyword. In this case, inside the modify underscore global function, the statement global x informs Python that we are referring to the global variable x rather than creating a new local variable. After that, the line x equal to 20 modifies the global variable x, changing its value from 10 to from t. The change persists after the function execution, which is why the updated value of x is printed as 20 both inside and outside the function. This behavior highlights the difference between local and global variables in Python. Local variables only exist within the scope of the function, while global variables exist throughout the program. By using the global keyword, we gain the ability to modify global variables within functions, but it's important to use this feature carefully, as it can lead to unintended side effects if multiple functions are modifying the same global variable. 2. Non-local keyword. The non-local keyword in Python is used to refer to a variable in the nearest enclosing scope, which is not the global scope but outer function's local scope. It is primarily used in nested functions to modify variables that belong to the outer enclosing function, ensuring that the inner function does not create its own local version of the variable. By using non-local, You allow the inner function to access and update the state of the variable in outer function scope, maintaining consistency across both scopes. This keyword is particularly useful when working with closures or when you need to preserve and update the state of a variable between nested functions. Key purpose. The key purpose of the non-local keyword is to modify a variable that is defined in the nearest enclosing scope, which is not the global scope. This is useful when dealing with nested functions, where the inner function needs to modify a variable from the outer function scope. By using non-local, the inner function can access and change the variable in the enclosing function without creating a new local instance of it. This allows the variable to maintain its state between function calls within the same enclosing scope. Practical implementation. In this example, we demonstrate how to use the non-local keyword in Python to modify variables in an enclosing scope within a nested function. The outer underscore function defines a local variable equal to 5, which is accessible inside the inner function because it is part of the enclosing scope. Normally, when variables are defined in an outer function, inner functions can read them but cannot modify them directly unless explicitly stated. This is where the non-local keyword comes into play. By declaring non-locally inside the inner underscore function, we are telling Python that we want to use and modify the y variable from the enclosing scope, specifically the one defined in outer underscore function. Without non-local, any assignment to inside inner underscore function would create a new local variable, leaving the y in outer underscore function unchanged. When inner underscore function is called, it changes the value of e from 5 to 10. This modification is reflected both inside the inner function and in the outer function after the inner function is executed. The print statements confirm this by displaying a 10 both inside inner underscore function and when printing an outer underscore function. The non-local keyword is useful in situations where you need to maintain or update state across multiple levels of nested functions without relying on global variables. It provides a middle ground between local and global scope, allowing functions to modify variables that are defined in an outer but non-global scope, enhancing flexibility in managing variable scope in more complex nested function structures. Question 35. How do you create a class in Python? To create a class in Python, you use the class keyword followed by the class name, typically written by skull case. Inside the class, you define the class's attributes, data, and methods, functions that define its behavior. The underscore underscore init method, known as the constructor, is a special method that initializes the object's attributes and in instance of class is created. The self parameter refers to the specific instance of the class and is used to access attributes and methods. Once a class is defined, you can create objects instances by calling the class, and these objects will have the attributes and behaviors specified by the class. Key components. Class definition. A class is defined using the class keyword followed by the class name. The convention is to write the class name in Pascal case, e.g. my class. This defines the blueprint for creating objects instances of the class. Underscore underscore init method. The underscore underscore init method is a special method called the class constructor or initializer. It is automatically invoked when a new object of the class is created. This method initializes instance variables and the first parameter it takes is self, which refers to the instance being created. Other parameters can be added to initialize specific attributes of the instance. Instance variables. These are variables unique to each instance of the class. They are typically initialized inside the underscore underscore init method using self. These instance variables store data specific to the individual object created from the class. Methods are functions that are defined within a class. They operate on the instance's attributes and define the behaviors or actions that the objects of the class can perform. Each method takes self as its first parameter, which allows it to access or modify the instance variables. A self parameter, this is a reference to the current instance of the class. It allows access to instance variables and other methods within the class. When calling methods or referring to instance variables, self ensures that the operation is being performed on the specific instance in question. Practical implementation. In this example, we define a simple class called dog, which serves as a blueprint for creating dog objects, each with its own specific attributes and behaviors. The underscore init method is the class's constructor, which is automatically called when a new instance or object of the dog class is created. It takes two parameters, name and breed, and assigns them to the instance variables self.name and self.breed. These instance variables store the specific name and breed for each dog object created from the class. For instance, when we create an object my underscore dog buddy golden retriever, the constructor initializes my underscore dog with buddy as the name and golden retriever as the breed. These values are stored in the instance variables self.name and self.breed, which are unique to the my underscore dog object. The class also has a method called display underscore info, which prints out the dog's name and breed using the instance variables. This method can be called on any dog object and it will display the specific data associated with that instance. When we call my underscore dog dot display underscore info, it prints my dog's name is Buddy and it is a golden retriever, showing that the instance variable self.name and self.breed hold the value specific to the my underscore dog object. Question 36. What is the difference between a class and an object in Python? Definition. A class is essentially a blueprint or template for creating objects. It defines the structure and behavior that each object will have. In contrast, an object is a specific instance of a class created from this blueprint, containing its own unique data. Purpose. The class serves the purpose of defining the shared attributes and behaviors that all objects of that class will have. On the other hand, an object represents a concrete realization of the class with its own individual data aligned interaction based on the class's blueprint. Memory. A class itself does not occupy memory until objects are instantiated from it. Once an object is created, it occupies memory and stores specific data. Objects have their own memory allocation for the attributes that the class defines. Attributes. In a class, attributes define general properties that will be shared among all objects created from that class. Own object, however, stores specific values for these attributes, making each object unique even if they come from the same class. Methods. Classes define methods that describe the behaviors or actions that all objects of that class can perform. Objects can then execute these methods using their own data to perform tasks. Creation. A class is defined using the class keyword and is structured out before objects can be created. Objects are created through instantiation by calling the class as if it were a function. Multiplicity. One class can serve as a template for creating multiple objects. Each object will be a distinct instance of the class with its own set of attributes. While a class defines the general rules, each object operates independently based on the class's structure. For example, class car defines the blueprint for creating car objects and car1 car. Toyota Camry creates a specific object from that class with unique data like brand and model. Practical implementation. In this example, we define a class called car, which represents a blueprint for creating individual car objects with specific attributes and behaviors. The class contains two important components, the underscore init constructor method and the start method. The underscore init method is the constructor that is automatically called when a new car object is created. It takes two parameters, brand and model, which represent the brand and model of the car. These values are stored in instance variables self.brand and self.model. Instance variables are specific to each object, meaning each car object will have its own unique brand and model. For example, if we create a car object with car Toyota Corolla, the brand will be Toyota and the model will be Corolla for that particular car object. The start method is a behavior defined within the car class that simulates starting the car. When this method is called on a specific car object, it prints a message indicating that the car is starting using the object's brand and model. The method accesses the instance variable self.brand and self.model, which hold the value specific to each car object. In this example, we create two objects instances from the car class, each representing a different car with its own brand and model. The first object, car1, is initialized with the brand Toyota and the model Camry, while the second object, car2, is initialized with the brand Honda and the model Civic. These objects are created using the constructor underscore underscore init method of the car class, which assigns the values to the instance variable self.brand and self.model. Each object holds its own unique data, which means car 1 and car 2 can represent two distinct cars. The start method is then called on both objects. When the method is called on car 1, it prints Toyota Camry starting by accessing the instance variables car1.brand and car1.model. Similarly, when the method is called on car 2, it prints Honda Civic is starting by accessing car 2's brand and model. This shows that the behavior method of the class is the same for both objects, but the data attributes are specific to each object. Question 37. What is the purpose of self in Python? In Python, the self parameter refers to the current instance of a class and allows access to the instance's attributes and methods. It acts as a reference to the object itself, helping to differentiate between instance-specific data and shared data across instances. While self must be explicitly defined as the first parameter in instance methods, it is automatically passed when the method is called. So you don't need to include it during the method invocation. This makes it easier to work with multiple objects of the same class without confusion. Key points. The self keyword represents the instance of the class and allows each method to refer to the object that invoked it. By using self, you can access the instance's attributes and methods, making it possible to interact with and modify the object state. It's always the first parameter in any instance method, providing a way to ensure each method can work with the specific object calling it, which is essential for object-oriented programming. Self ensures that all instance variables and methods are accessible throughout the class. Why is self important? The self keyword is essential because it differentiates between instance variables and local variables within a method. It ensures that methods can access and modify the object's attributes. By using self, each instance of a class can have its own unique attributes and methods operate on the correct instance, making object-oriented programming in Python more efficient and organized. Practical implementation. In this example, we define a class called myClass that demonstrates how instance variables and the self keyword work in Python. The class contains two methods, the constructor underscore underscore init and a custom method called display underscore value. The underscore underscore init method is the class constructor, which is automatically called when a new object or instance of the class is created. It takes a parameter value and assigns it to an instance variable self.value. The self keyword is crucial here. It refers to the specific instance of the class being created or modified. In this case, self.value ensures that each object of the class can store its own unique value. When an object is created, such as object myClass10, the value 10 is passed to the constructor and stored in self.value for that particular instance of myPlayer. The display underscore value method is a custom method that prints out the value of self.value. Inside this method, the self keyword refers to the current instance of the class, allowing the method to access the instance in its own value. When we call object.display underscore value, the method prints the instance self, which is the object object, and then it prints the value of self.value, which in this case is 10. This example highlights how self allows instance methods to refer to specific objects and access their attributes. It ensures that each instance of the class can maintain its own data, allowing multiple objects to coexist with their own unique states. The use of instance variables makes it possible to store information that is specific to each object, and methods like display underscore value can access and manipulate that data for individual objects. This is a fundamental concept in object-oriented programming (OOP), where objects encapsulate both their attributes and behavior methods. Question 38. What is the difference between a static method and class method in Python? The definition of a static method and class method highlights their primary differences. A static method is a method that does not take any implicit first argument, meaning it doesn't require self for instance methods or class for class methods. In contrast, at classmate takes class as its first parameter, allowing it to operate on the class itself rather than instance of the class. Regarding the first parameter, at static method does not have self or class as a parameter since it doesn't need to reference the class or instance. At class method, however, explicitly takes class as the first argument, allowing access to class level attributes and malacteric. In terms of usage, add static method is used when a method doesn't need to access or modify instance or class data. It's perfect for utility functions that perform a task in isolation. Meanwhile, a class method is useful when a method needs to work with class level data or modify class attributes, often used for factory methods or when class-wide modifications are needed. The binding of these methods also differs. Add static method is bound to the class but does not have access to any class or instance data, while add class method is bound to the class itself and can access class attributes but not instance specific data. Both decorators can be called using either the class name or an instance, but the key difference lies in how they access data. Its static method cannot directly access class or instance data, making it a true utility function, while a class method can access and modify class level data but remains disconnected from instance specific data. Finally, the typical use case for a static method is when a utility function is required that doesn't need any context from the class or instance, such as mathematical operations or other independent tasks. In contrast, add class method is commonly used when the class itself is a core part of the operation, like factory methods that create instances or methods adjust class-wide settings. Practical implementation. In this example, we define a class called myClass that demonstrates the three different types of methods available in Python classes: instance methods, class methods, and static methods. Each of these methods has a specific purpose and different access to the class and instance attributes. One instance method. The instance underscore method is a regular method that operates on an instance of the class. It takes self as its first argument, which refers to the instance calling the method. Instance methods can access both instance specific data, though none is present in this example, and class attributes like class underscore attribute. This method must be called through an instance as shown by object.instance underscore method, and it can interact with the specific instance that calls it. To class method, the class underscore method is defined using the add class method decorator and takes class as first argument, which refers to X rather than a specific instance. Class methods can only access class attributes such as class underscore attribute but cannot access any instance specific data. Class methods can be called either on the class itself, myClass.class underscore method, or through an instance object.class underscore method, though calling it on the class is more common. 3. Static method. The static underscore method is defined with the add static main decorator. Unlike instance and class methods, it does not take self or class as arguments, meaning it is completely independent of both instances and the class. Static methods do not access any class or instance attributes, making them ideal for utility functions that perform general operations. They can be called on the class myClass.stack underscore method or through an instance object.static underscore method. This example highlights the flexibility Python provides through different types of methods. Instance methods operate on specific objects and can access both class and instance data. Class methods operate on the class as a whole and can access class level data, while static methods are utility functions that are independent of the class or instance, useful for operations that don't require any internal state of the class or its objects. Each method type serves a unique purpose, allowing for more organized and efficient code in object-oriented programming. Question 39. What is the difference between underscore underscore new and underscore underscore init? The purpose of underscore underscore new and underscore underscore init sets the roles apart in object creation. Underscore underscore new is responsible for creating a new instance of a class, while underscore underscore init initializes the created instance with specific attributes. Essentially, underscore underscore new is in charge of constructing the object, whereas underscore underscore init prepares it for use by setting its properties. Regarding the method type, underscore underscore new is a static method that is called before the instance of the class is even created. On the other hand, underscore underscore init is an instance method, meaning it is called after the instance has been created, allowing it to set instance specific values. For the return value, Underscore new must return a new instance of the class. This is essential since it's the method that actually builds the instance. In contrast, underscore init does not return anything and is expected to return none, as its purpose is to initialize, not create. When considering when the call underscore new is invoked before underscore init, the instance creation happens first via underscore new, and once that instance is returned, underscore init is automatically called to initialize its attributes. In terms of usage, underscore new is mainly used in situations where control over object creation is required, such as when dealing with immutable objects like strings, tuples, or when implementing patterns like singletons. Meanwhile, underscore init is frequently used to instead attributes or configure objects after they are created. The arguments for each method also differ. Underscore new takes the class as first argument since it is responsible for the creation of the class instance. In contrast, underscore init takes the instance self as its first argument since it operates on the object that is on the object that are created. Finally, for common use cases, underscore new is rarely overridden, typically used in specialized scenarios like customizing object creation in singleton or meta class designs. On the other hand, underscore init is commonly used in almost every class to initialize the instance attributes and prepare the object for its intended use. Practical implementation. In this example, we demonstrate the difference between the underscore new and underscore init underscore methods in Python and how they work together in the process of object creation. The underscore new method is responsible for actually creating a new instance of the class. It is called before underscore init and is used to allocate memory for the object. In this code, we override underscore new to print a message, creating instance with underscore new, and use super dot underscore new class to call the parent class's underscore new method, which returns the newly created instance. This instance must be returned by underscore new or object creation will fail. After the instance is created by underscore new, the underscore init method is called to initialize the instance. The underscore init method takes the value argument passed during object creation and sets it as an instance attribute self dot value. In this case, the line initializing instance with underscore init is printed to indicate that the initialization process is taking place. The underscore init method is responsible for setting up the internal state of the object, but it doesn't actually create the object. This is why it follows underscore new. When we create an instance of custom class using object custom class 10, both methods are invoked. First, underscore new creates the instance and then underscore init initializes it with the value 10. Finally, we access the value attribute using object.value, which prints object value 10. In summary, underscore new is used to control the actual creation of the object, and underscore init is used to initialize the object after it has been created. While underscore init is commonly used in most classes, overriding underscore new is less common and is generally reserved for scenarios where you need to control object creation, such as when dealing with immutable types or singleton patterns. Question 40. How do you implement a singleton pattern in Python? The singleton pattern is used to ensure that only one instance of a class exists in the entire program. In Python, you can implement this by overriding the underscore new method, which controls object creation. Whenever a new instance is requested, the singleton class checks if an instance already exists. If it does, the existing instance is returned, otherwise a new one is created. This pattern is useful when you need a single object to manage shared resources such as database connections or logging. By controlling the instance creation process, the singleton pattern promotes consistency and coordination across your system. Key concepts. The singleton pattern makes sure that only one instance of a class is created and any future attempts to create another instance return the same object, ensuring consistency. The underscore new method is crucial here as it is overridden to check if an instance already exists, returning it if it does, and creating it only if it doesn't. A class attribute commonly underscore instance is used to store this single instance. So every time an instance is requested, the same one is returned, keeping object creation in check. Practical implementation. In this example, we implement the singleton design pattern using the singleton class. The singleton pattern is a common design pattern that ensures only one instance of a class is created, regardless of how many times a class is instantiated. This is particularly useful when a single shared resource is required, such as a database connection, a logger, or a configuration manager. The key to the singleton pattern lies in the underscore underscore new method, which is responsible for controlling the creation of the class instance. In the singleton class, we override the underscore underscore new method to check if an instance of the class already exists. The class attribute underscore instance is initially set to none, which indicates that no instance has been created. When the underscore underscore new method is called for the first time, it checks whether underscore instance is none. If it is, the super dot underscore underscore new class call creates a new instance, and we store that instance in underscore instance. For all subsequent calls to instantiate the class, the method returns the existing instance stored in underscore instance, ensuring that no new instance is created. In the usage section, we create two objects, obj1 and obj2, by calling singleton. However, due to the singleton implementation, both obj1 and obj2 point to the same instance of the class. The line print obj1 is obj2 prints true, indicating that both variables reference the same object in memory. This pattern ensures that only one instance of the singleton class exists throughout the application, making it an ideal choice for scenarios where you need centralized management of resources or configurations. The singleton pattern helps prevent resource duplication and ensures that all parts of the system interact with the same instance of the class. Question 41. How do you implement inheritance in Python? In Python, inheritance allows you to create a new class that inherits the attributes and methods from an existing class, promoting code reuse. You define the parent class first, then create the child class by passing the parent class as an argument in the child class definition. This way, the child class can inherit all the features of the parent while also adding or overriding specific methods or attributes. Inheritance simplifies code maintenance and promotes a hierarchical structure, making the code more organized and efficient. Syntax for inheritance. In Python, inheritance allows a child class to inherit properties and methods from a parent class, enabling code reuse and organization. To define a child class, you simply pass the parent class as an argument, creating the child class. For example, class child class plus parent class means that child class inherits all the functionality from parent class while still allowing you to add or override methods and attributes in the child class as needed. This makes inheritance a key feature for building scalable and maintainable code. Practical implementation. In this example, demonstrate the concept of inheritance and method in Python using a parent class animal and a child class dog. The animal class is the base class which defines a general structure for animals. It contains an underscore underscore init constructor method to initialize the name attribute and a method called speak that returns a generic message indicating that the animal makes a sound. The dog class is a child class that inherits from animal, meaning it automatically has access to the attributes and methods of the animal class. The dog class extends this functionality by introducing a new attribute breed be specific to dogs. The dog class also overrides the speak method from the parent class to provide a more specific message indicating that the dog barks and including the breed in the output. When we create an instance of the dog class, in this case dog, dog, buddy, golden retriever, the under TBO underscore underscore init method from the animal class is called to initialize the name attribute via super dot underscore underscore init name, while the dog classes constructor initializes the breed attribute. The dog classes speak method is then called, and since it overrides the parent class's speak method, it provides a more specific behavior, but in the golden retriever barks. This example illustrates the power of inheritance where child classes can inherit and reuse common functionality from parent classes and method override, where child classes can modify or extend the behavior of parent class methods to fit specific needs. In object-oriented programming, inheritance helps in reducing code duplication and promoting usability by creating a clear hierarchy and structure for related classes. Question 42. What is the purpose of the super function? The super function in Python is a way to access methods and properties from a parent class within a child class. It allows you to call a method from the parent class without explicitly naming it, which is especially helpful in inheritance hierarchies. This means you can reuse code from the parent class, like calling its underscore underscore init method to initialize properties. Super is even more useful in cases of multiple inheritance as it follows the method resolution order MRO to determine which class's method to call, ensuring that the correct class method is invoked in complex inheritance chains. Key features of super. Super is a handy tool in Python that allows you to access methods from a parent class with an ace oblivious without needing to explicitly reference the parent class by name. It's especially useful in multiple inheritance situations where Python follows a specific method resolution order MRO to ensure the correct method is called. By using super, you improve code reusability, avoiding duplication by leveraging methods already defined in the parent class. It also makes refactoring easier as changes to the parent class name require updates to references in the subclass. Common use cases for super. Using super helps ensure that the parent class is properly initialized when its constructor is called in a subclass. This is important when you want to extend or build upon the functionality of the parent class without rewriting everything. Additionally, super allows you to access methods in the parent class even after they've been overridden in the subclass. This ensures you can still use or modify inherited behavior while introducing new functionality in the subclass. Practical implementation. In this example, we explored the concepts of inheritance and method overriding in Python using a parent class animal and a child class dog. The animal class serves as a base class that defines a common structure for animals. It has a constructor underscore underscore init that initializes the name attribute which stores the name of the animal. It also includes a method called sound that returns a generic animal sound, some generic animal sound. This method is intended to be overridden by specific animal subclasses. The dog class is a child class that inherits from animal. In the dog class, we use the super function in the constructor to call the parent class's constructor and initialize the name attribute. Okay. This allows the dog class to reuse the functionality from the animal class for setting the name, while also introducing a new attribute breed which is specific to dogs. The dog class also overrides the sound method from the animal class to provide a more specific behavior for dogs, returning bark instead of the generic sound. 3. When we create an instance of the dog class such as dog dog buddy golden retriever, the constructor initializes both the name and breed attributes. By calling dog.name, we access the name attribute inherited from the animal class, which prints buddy. By calling dog.sound, we execute the overridden sound method, the dog class, which returns bark, providing behavior specific to dogs. Um, This example highlights the power of inheritance, allowing us to define shared functionality in a base class and then extend or customize it in child classes. Method overriding enables subclasses to provide specific implementations of methods that are initially defined in the parent class, making the design more flexible and allowing child classes to exhibit specialized behavior. This is a fundamental feature of object-oriented programming (OOP), promoting code reuse and modularity. Question 43. How do you implement multiple inheritance in Python? In Python, multiple inheritance allows a class to inherit from more than one parent class, combining functionality from multiple sources. This is done by specifying multiple parent classes in the class definition separated by commas. The right class can then access attributes and methods from all the parent classes. Python resolves conflicts in method names through a technique called resolution order MARO, which determines the order in which parent classes are checked for method and attributes. Multiple inheritance can be useful when you want to create a class that shares features from more than one base class without duplicating code. Practical implementation. In this example, we demonstrate the concept of multiple inheritance in Python, where a child class can inherit from more than one parent class. The being parent classes, parent class 1 and parent class 2, each define their own methods. Parent class 1 has a method called method 1 that prints method from parent class 1, while parent class 2 has a method called method that prints method from parent class 2. Who? Child class inherits from both parent class 1 and parent class 2. This means that child class automatically gains access to the methods from both parent classes. In addition to inheriting the method, child class also defines its own method, method 3, which prints method from child class. When an instance of child class is created, such as child class, the object child can call methods from both parent classes as well as its own methods. Specifically, when we call child.method 1, the method from parent class 1 is executed, printing method from parent class 1. Similarly, calling child.method 2 executes the method from parent class 2, printing method from parent class 2. Finally, calling child.method 3 invokes the method from child class, printing method from child class. This example highlights the power of multiple inheritance, which allows a child class to combine behaviors and attributes from multiple parent classes. It enables code reuse and flexibility as the child class can inherit functionality from multiple sources. However, in more complex scenarios, multiple inheritance can lead to issues like method resolution order, marrow, or method conflicts when parent classes have method the same name. Therefore, while multiple inheritance is a useful tool in object-oriented programming, it should be used with caution in more intricate designs. Question 44. What are properties in Python and how do you define them using a property? In Python, properties allow you to manage how attributes are accessed or modified, providing a layer of control without changing how users interact with them. By using the property decorator, you can define a getter method that behaves like an attribute but adds logic for tasks like validation or calculation. This approach helps encapsulate your class's attributes, letting you control access while maintaining a clean and intuitive interface for the class. For instance, users can access or update values as if they were simple attributes centrally. The scene's logic ensures the values are handled correctly. Why use properties? Properties in Python offer a way to control how attributes are accessed or modified. They provide encapsulation, allowing for validation or logging when an attribute is set or retrieved without exposing the internal details. This also ensures backwards compatibility, meaning you can change an attribute into a method into a without breaking existing code that accesses it like a variable. Additionally, properties enable data validation and that only valid data is accepted when attributes as their update is of maintained data integrity across your application. Practical implementation. In this example, we demonstrate how to use properties in Python to provide controlled access to an attribute. The employee class has two primary attributes, first underscore name and last underscore name, which are initialized using the underscore underscore init constructor. A key feature of this class is the full underscore name property, which is used to combine and return the employee's full name. This is done using that property decorator, which allows the method full underscore name to be accessed like an attribute without needing parentheses. The property decorator defines the getter for the full underscore name property, allowing you to retrieve the full name and in the format first last. For instance, when employee.full underscore name is called, it returns John Doe, combining the first and last names. In addition to the getter, we define a setter for the full underscore name property using the add full underscore name dot setter decorator. This setter allows us to update the first underscore name and last underscore name attributes by simply assigning a new full name string to the full underscore name property. When a new full name, such as N. Smith, is assigned to a dot full underscore name, the setter splits the string into two parts and omits the first underscore name and last underscore name attributes accordingly. The use of properties provides a clean and intuitive way to access and modify attributes while maintaining internal control over how the data is stored and processed. Instead of directly modifying first underscore name and last underscore name, you can use the full underscore name property to achieve the same result in a more readable and user-friendly manner. This example highlights the benefits of encapsulation in object-oriented programming (OP), where properties help manage how class attributes are accessed and modified, promoting cleaner and more maintainable. Question 45. What is method resolution order (MRO) in Python? Method resolution order (MRO) in Python determines the order in which Python searches for methods or attributes in a class hierarchy, especially when dealing with multiple inheritance. When a method is called, Python follows this sequence to check each class in the hierarchy to see where the method is defined. MRO helps ensure that the correct method is called without ambiguity following a specific linear order. This order is calculated using the C3 linearization algorithm, ensuring that child classes are checked before parent classes and siblings are handled in a consistent left to right manner. Key concepts. Search. The method resolution order (MRO) ensures Python searches for methods in a clear and defined sequence, avoiding ambiguity in class hierarchies. It follows a depth first, left to right approach using the more modern C3 linearization algorithm to ensure predictable method resolution, especially in complex class structures. In cases of single inheritance, Python first checks the class itself, then moves up to its parent class, continuing through the hierarchy. In multiple inheritance, the C3 algorithm makes sure methods are taken from the most specific class first, ensuring consistent behavior. Practical implementation. In this example, we explore the concept of multiple inheritance in Python, specifically focusing on how Python resolves method calls when a class inherits from multiple parent classes. We have four classes A, B, C, and D. The base class A contains a method called method that prints A. Both B and C inherit from A, but they each override the method to provide their own implementations, printing B and C respectively. The class D demonstrates multiple inheritance as it inherits from both B and C. However, class D does not override the method, meaning that when d.method is called, Python must decide which version of the method to use. This decision is made through Python's method resolution order (MRO). MRO determines the order in which Python looks through the inheritance hierarchy to find the appropriate method to call. In this case, since D inherits from B first and then C, Python will prioritize the method from B over C. As a result, calling d.method outputs B. This example demonstrates how Python resolves method conflicts in multiple inheritance using MRO. MRO ensures that there is a well-defined order to follow when searching for methods in a complex inheritance hierarchy. By following the inheritance chain from left to right, i.e. B before C, Python avoids ambiguity and ensures predictable behavior in class hierarchies with multiple parents. This is a powerful feature of Python's object-oriented design, allowing for flexible inheritance while maintaining clarity in how method is resolved. Question 46. What is the difference between overloading and overriding in Python? Overloading and overriding are two different concepts in object-oriented programming. Overloading allows multiple methods with the same name but different parameters, though it's not natively supported in Python. However, you can mimic it using techniques like default arguments or args and quarks to handle different parameter inputs. Overloading, on the other hand, is fully supported in Python. It enables a child class to modify or extend the behavior of a method inherited from the parent class. While overloading focuses on creating different versions of a method based on input, overriding is used when you want to change the behavior of an inherited method in a subclass. Overloading is helpful when you want a function to handle different tasks based on input parameters, but in Python you need to use alternatives. Overriding is typically used when you need to customize the inherited behavior in a subclass. Practical implementation for method overloading. In this example, we explore how method overloading can be mimicked in Python by using default arguments. Python does not natively support method overloading in the traditional sense, where you can define multiple methods with the same name but different numbers or types of parameters. Instead, Python achieves similar functionality by allowing you to define default values for function parameters. This way, a single method can handle different numbers of arguments by using default values when some parameters are not provided. The class calculator has a method called add that takes three parameters a, b, and c, with b and c having default values of 0. When the method is called, Python will assign the provided arguments to a, b, and c, and if fewer than three arguments are passed, the missing parameters will use their default values. This approach allows the method to behave differently depending on how many arguments are supplied during the call, mimicking the effect of method overloading. For example, when we call cal.add5, the method only receives one argument, so b and c default to 0, and the result is 5. When we call cal.add5, 2 arguments are provided and only c defaults to 0, resulting in 15. When we call call.add5, 10, 15, all arguments are provided and the result is 30. This allows the add method to handle a variable number of arguments without needing multiple method definitions. This technique demonstrates the flexibility of Python's function definitions and provides a way to handle different cases in a single method, which can simplify code and make it more maintainable. Practical implementation for method overridden. In this example, we illustrate the concept of method overriding in object-oriented programming using Python. The base class animal defines a generic method called sound, which returns a generic string some generic animal sound. This method represents the default behavior for any animal. However, in real-world scenarios, different animals make different sounds, so the method is overridden in the child classes. We have two child classes, dog and cat, both of which inherit from the animal class. In each child class, the sound method is overridden to provide more specific behavior. The dog class overrides the method to return bark, while the cat class overrides it to return meow. This way, although both dog and cat inherit from animal, they exhibit different behaviors when the sound method is called. This is a key feature of polymorphism, where the same method can behave differently depending on the object calling it. When we create instances of the dog and cat classes and call their sound methods, the overridden methods in the respective classes are executed, demonstrating the flexibility of method overriding. For the dog instance, calling dog.sound returns bark, while calling cat.sound on the cat instance returns meow. This behavior allows the program to differentiate between the sounds of different animals, even though they share the same method name. In summary, method overriding enables child classes to provide their own specific implementations of methods inherited from a parent class, allowing for customized behavior while maintaining a shared interface. This approach promotes code reuse, flexibility, and clarity in class hierarchies, making it a fundamental aspect of polymorphism in object-oriented programming. Question 47. How do you create a private attribute in Python? In Python, a private attribute is an attribute meant to be hidden from outside access, helping to protect the internal state of an object. Although Python doesn't have true private attributes, you can simulate this by using a naming convention called name mangling. By prefixing an attribute with two underscores, e.g. underscore underscore attribute, Python automatically changes its name, making it harder to access from outside the class. This promotes encapsulation, allowing you to safeguard sensitive data while still maintaining flexibility within the class. Creating a private attribute. In Python, private attributes are created by adding double underscores underscore underscore before the attribute name, signaling that it's meant to be accessed only within the class. This triggers a process called name mangling, where Python changes the name internally to prevent accidental access from outside the class. For example, if you define a private attribute like self dot underscore underscore private underscore attribute, it becomes harder for external code to access or modify directly, ensuring better encapsulation and data protection in your class design. Practical implementation. In this example, we explored the concepts of encapsulation and access control in Python using public and private attributes. The class car has two attributes underscore underscore brand, which is private, and model, which is public. Encapsulation is an important principle in object-oriented programming (OOP), and it ensures that the internal state of an object is protected from direct access or modification from outside the class. The underscore underscore brand attribute is defined with two leading underscores underscore underscore, making it private. This means it cannot be accessed directly from outside the class, as Python uses name mangling to change the attribute's name internally. Name mangling prevents external code from accidentally or intentionally accessing private attributes. However, we can still access underscore underscore brand using a method inside the class, such as get underscore brand. This method provides a controlled way to retrieve the value of the private attribute without exposing it directly. This is an example of encapsulation where we hide an attribute's details and provide controlled access through methods. The model attribute, on the other hand, is a public attribute and can be accessed and modified directly from outside the class. Public attributes are meant to be openly accessible without any restrictions. Although it's technically possible to access private attributes using name mangling, e.g. car underscore underscore brand, this is considered poor practice as it violates the principle of encapsulation. Name mangling is Python's way of preventing direct access to private attributes, but it does not provide absolute protection. It's a signal to developers that the attribute is intended to be private. Overall, this example highlights how encapsulation helps protect the integrity of an object's internal state by restricting access to its attributes and providing methods to access or modify them in a controlled manner. It shows the importance of using public and private attributes to differentiate between what should be accessible to external code and what should remain hidden for internal use only. Question 48. What is encapsulation and how is it achieved in Python? Encapsulation is a key concept in object-oriented programming where data and methods that act on that data are bundled together in a class. In Python, encapsulation allows you to protect internal object data by restricting access, ensuring that it can only be modified or accessed through controlled methods. This helps prevent unintended interference or changes to the data. Python achieves encapsulation through naming conventions. Prefixing an attribute with a single underscore underscore suggests it is intended for internal use, while double underscores underscore underscore make it harder to access or override from outside the class. How encapsulation is achieved in Python. In Python, encapsulation is achieved by defining public, protected, and private members in a class. Public members are accessible from anywhere, protected members are meant to be accessed only within the class and its subclasses, and private members are restricted to the class itself. Python enforces encapsulation through a mechanism called name mangling, where private attributes are prefixed with double underscores, making them harder to access from outside the class but still not entirely inaccessible. This helps in controlling access to sensitive data and ensuring internal class logic is protected. 1. Public members. Public members in Python are accessible from outside the class, meaning they can be used by any code that interacts with the class. By default, all class attributes and methods are public unless otherwise specified. Public members don't require any special notation, as no leading underscores are used to indicate their visibility. This makes them the default choice for most class interactions, providing flexibility and ease of use for developers when creating or accessing objects. Practical implementation. In this example, we define a simple car class with two public attributes, brand and model, and a method display that returns the car's details as a formatted string. Public attributes in Python are accessible directly from outside the class, allowing easy interaction with the object's data. When an instance of the car class is created, the underscore underscore init constructor method is called to initialize these two attributes, which are passed as arguments, in this case Toyota and Camry. The display method demonstrates how methods within the class can use the object's attributes. This method returns the car's brand and model in a single formatted string. In this example, when we call car.display, it outputs Toyota Camry combining the brand and model. Since both brand and model are public, we can directly access them outside the class. For example, car.brand will output Toyota, showing that public attributes can be easily retrieved and modified without needing special methods such as getters or setters. Second, public attributes are ideal when you want to allow external code to interact freely with an object's data. This example illustrates the use of public attributes in object-oriented programming, where attributes can be accessed directly without restrictions. It makes the class easy to use and maintain for scenarios where full access to the object's properties is acceptable. However, if stricter control over data access and modification is needed, private attributes and accessor methods like getters and setters and share would be used. 2. Protected members. Protected members are used for internal purposes within a class and its subclasses, but technically they can still be accessed from outside the class, although it's not recommended. They are indicated by a single leading underscore underscore to signal that they are not meant to be accessed directly from outside the client. This is more of a convention to inform developers that these members are intended for internal use only. Practical implementation. In this example, we explore the concept of protected attributes and methods in Python using the class car. The attribute underscore engine and the method underscore start underscore unmachine are marked as protected by using a single leading underscore underscore. In Python, the single underscore is a naming convention that signals to developers that these members are intended for internal use within the class or by subclasses. Even though Python does not enforce strict access control like some other programming languages, the underscore engine attribute holds the value V6, representing the car's engine type. Even though it is technically accessible from outside the class, the leading underscore conventionally indicates that it should not be accessed directly by external code. Similarly, the underscore start underscore engine method, which prints engine started, is marked as protected. This method is designed to simulate starting the car's engine, but again should be used internally rather than being invoked directly by code outside the class. While it's possible to access protected members like car.engine and car.start_engine from outside the class, doing so is discouraged because it violates the encapsulation principles of object-oriented programming. The use of the single underscore provides a soft warning to developers that these members are not part of the public interface and should be treated with care. Protected members are generally meant to be accessed or overridden by subclasses, but not by external code, but external the class interacts with the class. This approach to access control in Python is less restrictive compared to private members denoted with double underscores, but it still helps in promoting good coding practices by indicating which parts of the class are meant to be internal or subclass only. Therefore, while the code allows direct access to underscore engine and underscore start underscore up engine, doing so goes against the intended design and should be avoided in well-structured programs. 3. Private members. Private members in Python are attributes or methods that can't be accessed directly from outside the class. They are defined by a double leading underscore underscore underscore, which triggers name mangling, making it harder to access them externally. Private members are helpful when you want to protect internal details of a class, ensuring that data is secure and can't be modified unintentionally. They provide an extra layer of control and help maintain the integrity of the class's internal state. Practical implementation. In this example, we explore the concept of private attributes and methods in Python, which play a crucial role in encapsulation, a key principle of object-oriented programming (OOP). The car class demonstrates how to restrict access to certain parts of an object by marking attributes and methods as private using double underscores underscore underscore again. This signals that these members should only be accessed from within the class and not be required external code. The attribute underscore underscore engine is marked as private in the constructor. This means that it cannot be accessed or modified directly from outside the class. Attempting to access car dot underscore underscore engine would result in an attribute error because Python uses a feature called name mangling to change the name of the private attribute, making it harder to access from the outside. Similarly, the method underscore underscore start underscore engine is also private, meaning it cannot be called directly from outside the class. It is only accessible from within the class. To provide controlled access to the private method, the class defines a public method called start. This method can be called from outside the class and it internally calls the private underscore underscore start underscore engine method to start the car's engine. This approach allows us to protect the internal workings of the car class while still providing a way for external code to interact with the object in a controlled by. By using private members, we ensure that the internal state of the object and certain behaviors remain hidden and protected from external interference. This promotes data integrity and prevents unintended modifications. Encapsulation is a key feature of OP that helps create well-structured, maintainable, and secure code. In this case, the car class encapsulates its engine-related functionality, exposing only what is necessary while keeping sensitive parts hidden. 4. Name mangling. Name mangling in Python is a technique where private members of a class attributes or methods are renamed internally to include the class name. This prevents direct access to these private members from outside the class, ensuring better encapsulation. However, these private members can still be accessed indirectly by using the mangled name, which follows the pattern underscore class name underscore underscore website underscore member. Name mangling adds an extra layer of protection but doesn't make private members completely inaccessible. Practical implementation. In Python, attributes marked with double underscores e.g. underscore underscore engine are considered private, meaning they are not intended to be accessed directly from outside the class. However, Python uses a technique called name mangling to make it harder to access these private attributes, but it doesn't provide complete protection. Name mangling works by internally changing the name of the private attribute to include the class name as a prefix. In this example, the private attribute underscore underscore engine inside the car class is renamed internally to underscore car underscore underscore engine. By using printcar dot underscore car underscore underscore engine, you are bypassing Python's name mangling and directly accessing the private attribute. This line will print V8, the value of the underscore underscore engine attribute. While this is technically possible, it is considered bad practice because private attributes are intended to be used only within the class or through specific methods designed to provide controlled access. The purpose of private attributes is to enforce encapsulation, a core principle in object-oriented programming (OOP). Encapsulation allows you to hide the internal details of a class, ensuring that the class's internal state and implementation details are protected from external interference or accidental changes. Accessing private attributes directly via name mangling goes against this principle as it exposes the internal details that are meant to be hidden. Question 49. How do you implement polymorphism in Python? Polymorphism in Python is the ability to define a common interface that works across different data types or classes, making code more flexible and reusable. It allows objects of different types to be handled using the same method or function, enhancing consistency. One way to implement polymorphism is through method overriding, where subclasses provide specific implementations of inherited methods. Another way is through dunder methods such as underscore underscore stew or underscore 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 add, which enable built-in functions or operators to work with various object types, promoting ease of use and adaptability. Types of polymorphism in Python. In Python, polymorphism allows functions, methods, or operators to behave differently based on the types of objects they are working with. With polymorphism in functions, the same function can accept different types of objects and perform different actions depending on the object passed. In polymorphism with classes, also known as method overriding, child classes can provide their own version of methods inherited from parent classes, ensuring the right behavior for each class. Polymorphism with operators means that operators like or can perform different operations depending on the object type, like adding numbers or concatenating strings. Practical implementation: polymorphism with functions. In this example, we explored the concept of polymorphism in Python, specifically focusing on how a single function can handle different types of data and perform different operations based on the type of its arguments. Polymorphism is a key principle in object-oriented programming (OP), allowing objects or functions to take on multiple forms. In Python, functions are inherently polymorphic, meaning they can operate on different types of data without the need for multiple definitions or overloading. The add function in this example demonstrates polymorphism by accepting two arguments a and b. Depending on the type of these arguments, Python determines whether to perform an arithmetic addition or string concatenation. When integers are passed as arguments e.g. add 1, 2, the function returns their sum 3. When strings are passed e.g. add hello world, the function concatenates the two strings and returns hello world. This flexibility is one of the strengths of Python, as the language dynamically handles different data types at runtime. Unlike languages where you need to explicitly define multiple versions of a function to handle various data types, Python allows you to write a single function that can seamlessly operate on different types of inputs. This makes the code more concise, usable, and easier to maintain. Practical implementation: polymorphism with classes method overriding. In this example, we explore polymorphism through the concept of method overriding in object-oriented programming. The base class animal defines an abstract method sound which is intended to be implemented by subclasses. The animal class raises a not implemented error, signaling that subclasses must provide their own implementation of this method. This sets the foundation for creating flexible and usable code, as the animal class defines a common interface, the sound method, while allowing subclasses to implement it in their own way. Two subclasses, dog and cat, inherit from the animal class and override the sound method to provide their own specific behaviors. The dog class returns bark and the cat class returns meow, showing how method overriding works in practice. Each subclass defines its own version of the sound method, which replaces the abstract version in the parent class. The function make underscore sound demonstrates polymorphism by accepting any object that has a sound method regardless of its class. When a dog object is passed to the function, it prints bark, and when a cat object is passed, it prints meow. This is the essence of polymorphism. Different objects, in this case, dog and cat, can be treated the same way by calling the sound method, but they behave differently based on their individual implementations. Polymorphism through method overriding allows the same function make underscore sound to work seamlessly with different types of objects without next thou each class. This results in more flexible, maintainable, and reusable code. The function can interact with any future subclasses of animal as long as they implement the sound method, making it a powerful technique for handling different behaviors in a consistent way. This approach exemplifies one of the core principles of OP, where classes share a common interface but exhibit distinct behaviors. Practical implementation: polymorphism with dunder methods, operator overloading. In this example, we explore polymorphism with dunder methods, specifically focusing on operator overloading in Python. Operator overloading allows us to define custom behavior for built-in operators, like when they are used with user-defined objects. The class vector demonstrates how we can override the default behavior of operator by implementing the special method underscore 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 add. This method dictates how two vector objects should be added together. In the vector class, the underscore underscore add method is designed to add the x and y coordinates of two vectors. When we use v1, v2, Python automatically calls the underscore underscore add method of the vector class, which returns a new vector object with the sum of the respective coordinates. This makes the operator behave as expected for vector objects, just as it would for built-in types like integers or floats. By overriding this method, we make the operator more intuitive and applicable to custom objects without needing to explicitly write an addition method. Additionally, the underscore underscore repr method is overridden to provide a clear and informative string representation of the vector object when it is printed. This method is essential for debugging and understanding the state of an object, as it ensures that printing a vector displays it in a human readable format, such as vector 6. 8. Question 50. What is the purpose of the pass statement in Python? The pass statement in Python acts as a placeholder when you need to define code blocks like functions, loops, or conditionals but don't want to add any functionality yet. It allows you to write the structure of your code without causing syntax errors, making it useful when you're still planning or leaving space for future code. While the code block will do nothing when executed, pass ensures your program runs smoothly without breaking the flow. Key use cases of pass. The pass statement in Python is a simple placeholder used in various scenarios to avoid errors when no action is needed. In function or class stubs, it's useful when you're defining a function or class but haven't implemented the logic yet. Serving as a placeholder while the structure is being built. In empty control structures like loops or conditionals, it allows you to skip an action when nothing needs to be done at that point in the code. For prototypes or incomplete code, pass helps you outline your program during early development, letting you focus on structure before adding functionality. Practical implementation. In this example, we explored the use of the pass statement in Python, which serves as a placeholder when writing code. The pass statement is often used when defining functions, classes, or conditional blocks that are not yet implemented. It allows the programmer to create the necessary structures without causing syntax errors while indicating that the actual logic or implementation will be added later. For instance, the function my underscore function is defined but has no logic at the moment. The pass statement is placed inside the function to allow the code to run without error. Without pass, Python would expect some code in the function body and leaving it empty would raise a syntax error. Similarly, in the conditional block, if true, the pass statement is used because no action is required at the moment. This allows the code to be syntactically valid while signaling that logic might be added to this block in the future. Finally, the class myClass is defined with the pass statement, meaning that the class exists but has no attributes or methods yet. This is helpful when laying out the structure of a program and leaving space for future class functionality. Question 51. What is duck typing in Python? In Python, duck typing means that the type of an object is determined by how it behaves, not by what class it belongs to. This concept is captured by the saying, if it looks like a duck and quacks like a duck, it must be a duck essentially. As long as an object has the methods or attributes expected by the code, it can be used as that type. Python doesn't require the object to explicitly inherit from a specific class, making the code more flexible and adaptable. Key characteristics of duck typing. Duck typing in Python focuses on how an object behaves rather than its explicit type. If an object has the necessary methods or attributes, it can be used regardless of its type. This allows for more flexible and polymorphic code, enabling functions to work with various objects as long as they support the required operations. Python skips explicit type checking, making it easier to work with diverse object types, provided they behave as expected. This approach enhances flexibility and reduces the need for strict type enforcement, streamlining the coding process. Practical implementation. In this example, we explore the concept of duck typing in Python, which is a form of polymorphism. Duck typing is based on the principle of if it looks like a duck and quacks like a duck, it must be a duck. In Python, this means that an object's suitability for use is determined by the presence of certain methods or properties rather than by its actual type. The focus is on what an object can do its behavior rather than what it is its class. We define two classes, duck and dog. Both classes implement a method called quack. In the duck class, the quack method represents the natural behavior of a duck, outputting quack. In the dog class, although quacking is not a typical behavior of a dog, the method is still defined to print I'm a dog, but I can quack. This shows that even though the objects belong to different classes, they can both quack because they implement the same method. The function make underscore it underscore quack demonstrates duck typing by accepting any object as an argument and calling its quack method. The function does not care whether the object is a duck or a dog as long as the object has a quack method. The function will work. When make underscore it underscore quack is called with a duck object that prints quack, and when called with a dog object, it prints I'm a dog but I can quack. The type of the object is irrelevant. The function works because both objects implement the expected behavior. This flexibility makes Python highly dynamic and versatile. It allows developers to write code that can interact with different objects in a uniform way. as long as those objects provide the necessary methods or attributes. In this case, the ability to quack is the key criterion for using the object, demonstrating how behavior is prioritized over the object's type. Duck typing simplifies polymorphism in Python, enabling more usable and flexible code by focusing on what objects can do rather than their inheritance, hierarchy, or type. Question 52. What is strong typing in Python? Strong typing in Python means that the language strictly enforces rules about data types and doesn't automatically convert one type to another during operations. For example, Python won't let you add a string and an integer without explicitly converting one of the types, ensuring that operations between incompatible types don't happen by accident. This approach helps catch errors and makes the code more predictable and reliable since you always know what type of data. Key characteristics. Python enforces type safety by preventing automatic conversion between incompatible types. For instance, you can't add a string and an integer without converting one of them explicitly. If you try something like 510, Python will raise a type error. This ensures that operations between incompatible types are caught early. Python is also strongly typed, meaning variables are tightly bound to their assigned type. You can change the type dynamically, but Python will still maintain strict type checks during operations. For example, equal to 5 can be later assigned as a string, a hello, but if you try to combine them in a way that doesn't make sense, like adding a string and integer, you'll get an error. To work with incompatible types, you must use explicit conversion casting. Python provides casting functions like int, text, and float to handle type conversions. For example, you can convert a string to an integer with int510 and Python will return 15. Python also supports type annotations, allowing you to specify expected types in functions and variables starting from version 3.5. These annotations don't enforce types at runtime but can help with static analysis. So, while Python doesn't check types during execution, it's a useful feature for catching type mismatches early in development. Practical implementation. In this example, we explored the concept of strong typing in Python, which ensures that operations between incompatible data types result in an error rather than automatic type conversion. Python enforces strict rules about how values of different types can be used in operations. Here we attempt to add a string x5 and an integer e10. Since Python is strongly typed, it does not allow the implicit addition of a string and an integer, and doing so raises a type error. This behavior prevents unexpected results that might occur if the language automatically converted types without the programmer's intent. To handle this error, we use a try except block, which is a mechanism for error handling in Python. When the code tries to perform the operation xy, the type error is raised because Python does not know how to add a string and an integer together. The except block catches the error and prints an error message indicating the type mismatch. This prevents the program from crashing and gives the programmer a chance to understand the mistake. The correct way to handle this situation is by explicitly converting the string to an integer before performing the addition. This is done using the int function, which converts the string 5 into the integer 5. Once the types are compatible, Python allows the addition to proceed and the result is correctly calculated as 15. Question 53. What is monkey patching in Python? Monkey patching in Python refers to the ability to modify or extend the behavior of a class or module dynamically at runtime without altering the original source code. It's often used to fix bugs, add features, or extend functionality in third-party libraries. In testing, monkey patching helps override methods for mocking purposes. While it offers flexibility, it's important to use monkey patching carefully, as it can lead to unexpected behavior if not managed properly, especially when modifying external libraries. How monkey patching works. Monkey patching involves modifying or extending the behavior of a class or module at runtime by dynamically assigning new methods or attributes. This technique allows you to override the original functionality without altering the source code, giving you full control over how the class or module behaves. By directly modifying the behavior at runtime, monkey patching provides a quick and flexible way to adapt code. But it should be used carefully to avoid unintended side effects or conflicts in larger systems. Practical implementation. In this example, we explored the concept of monkey patching in Python, which allows for the dynamic modification of a class or object's behavior at runtime. Initially, we define a dog class with a method bark that returns woof, representing the typical sound a dog makes. When we create an instance of the dog class and call the bark method, the original behavior is observed with the output woof. However, through monkey patching, we can change the behavior of this method without altering the original class definition. A new function new underscore bark is created, which returns meow, simulating a dog that now meows like a cat. We then assign this new function to dog.bark, effectively replacing the original bark method with the new one. As a result, when the bark method is called again on the dog instance, it now returns mew instead of woof. Monkey patching is a useful technique in scenarios where you need to modify or extend the behavior of a class or object dynamically, especially in testing or when integrating with third party libraries. It allows you to alter the behavior of existing code without modifying the original source. However, it should be used with caution as it can make the codebase harder to understand and debug, especially if patches are applied in multiple places, leading to unexpected or conflicting behaviors. Question 54. What is the purpose of the global and non-local keywords? In Python, the global and non-local keywords help manage variable scope, enabling you to access or modify variables from different scopes. The global keyword allows you to reference or change a variable defined at the global module level from within a function. On the other hand, non-local is used within nested functions to access or modify variables in the nearest enclosing scope that is not global. Both keywords help you control where and how variables can be used, ensuring that your code can modify variables across different levels of scope when needed. 1. Global keyword. The global keyword in Python allows you to modify a variable that exists in the global scope from within a function. Normally, variables inside functions are treated as local, meaning any changes to them don't affect variables outside the function. By using global, you're telling Python to use and modify the variable defined globally, ensuring that changes within the function impact the variable outside the function as well. Key purpose. The key purpose of this concept is to allow functions to access and modify variables that are defined outside their local scope, typically in the global scope. This enables functions to interact with and change global variables, providing flexibility in managing data that exists beyond the function's immediate environment. Practical implementation. In this example, we explored the use of the global keyword in Python, which allows a function to modify a variable that exists in the global scope. Normally, variables defined inside a function are local to that function, meaning changes to those variables do not affect variables outside the function. However, by using the global keyword, we can explicitly state that we are referring to and modifying a global variable from within the function. Initially, the global variable x is set to 10. Inside the function modify underscore global, we use global x to tell Python that we are referring to the global x, not creating a local one. The function then changes the value of x to 20. This change is reflected globally, so after the function is called, x remains 20 even outside the function. The program demonstrates this by printing the value of x both inside and outside the function, showing the updated value of 20 in both cases. This example illustrates the potential of the global keyword to modify variables that are outside the local function scope, impacting the entire program. While this can be useful for managing shared state, it should be used sparingly and with caution. Relying too heavily on global variables can make a program harder to debug and maintain because changes to global state in one part of the code can have unintended consequences elsewhere. Therefore, it's important to carefully manage when and how global variables are modified to avoid introducing side effects that are difficult to track. 2. Non-local keyword. The non-local keyword in Python allows you to refer to a variable in the nearest enclosing but not global scope. This is especially useful in nested functions when you want to modify a variable from the outer function. Without non-local, variables inside nested functions are treated as local to that function. By using non-local, you ensure that changes in the inner function are reflected in the outer function's variable, enabling more flexible and dynamic behavior in your code. Key purpose. The key purpose of this approach is to modify a variable in the nearest enclosing scope, ensuring that changes affect the local context but without impacting the global scope. This allows for more controlled and isolated variable updates within specific functions or blocks of code, preserving the integrity of the broader program state. Practical implementation. In this example, we explored the use of the non-local keyword in Python, which allows a nested function to modify a variable from its enclosing non-global scope. Here we define two functions, outer underscore function and inner underscore function. The variable is initially set to 5 inside outer underscore function. This variable exists in the enclosing scope, meaning it is local to outer underscore function but can be accessed by any inner functions defined within it, such as inner underscore function. Inside inner underscore function, we use the non-local keyword to specify that we are referring to the y variable from the outer function scope, rather than creating a new local variable. By doing this, inner underscore function can modify the value of y from 5 to 10. The modified value of y is printed both inside inner underscore function and later in outer underscore function, demonstrating that the change persists across both scopes. The non-local keyword is essential in scenarios involving nested functions where the inner function needs to modify or interact with variables from its enclosing function. Without non-local, the inner function would create a new local variable leaving the originally from the outer function unchanged. This mechanism is especially useful for managing state within closures or nested function calls, allowing for more flexible control over variable access and modification in nested scopes. In summary, this example shows how non-local allows an inner function to modify a variable from its enclosing scope, making it a powerful tool in Python for working with closures and nested functions. It provides a way to manage and maintain state across multiple levels of function scope without resorting to global variables. Question 55. How does the abstract base class module work in Python? The apps module in Python allows you to define abstract base classes ABCs which act as blueprints for other classes. These abstract classes cannot be instantiated directly and must be inherited by subclasses that implement the abstract methods. This ensures that any subclass defines the required methods, helping to enforce a consistent structure across different classes. By using ABCs, you can create a framework where all subclasses follow a specific design, providing a way to ensure key methods are implemented. Key features of ABC. Abstract base classes ABC are used to define a blueprint for other classes. They contain abstract methods, which are methods without implementation, and any class inheriting from the ABC must provide concrete implementations of these methods. ABCs can be instantiated directly, meaning you can't create objects from them until all abstract methods are implemented in a subclass. This ensures that any child class follows the structure and rules set by the abstract class, promoting consistency and clear design. Practical implementation. In this example, we explore the concept of abstract base classes, ABCs, and method overriding in Python. An abstract base class defines a blueprint for other classes by specifying methods that must be implemented in any subclass. In Python, this is done using the app module where the abstract method decorator is used to define methods that do not contain an implementation in the base class. These methods act as placeholders, enforcing that any subclass provides its own implementation. Abstract-based classes cannot be instantiated directly. They are used to ensure that subclasses follow a specific interface. Here, the animal class is an abstract base class with an abstract method sound. This method doesn't have a body in the animal class, meaning it must be implemented by any class that inherits from animal. The subclasses dog and cat both inherit from animal and override the sound method to provide their own implementation. Dog returns woof and cat returns meow. Since these subclasses provide the required method, they can be instantiated and used without any issues. On the other hand, the subclass bird inherits from animal but does not implement the sound method. Because of this, attempting to instantiate bird will raise a type error, as Python enforces the rule that all abstract methods must be implemented before an instance can be created. This behavior ensures that every subclass of animal provides the necessary behavior defined in the abstract base class. This design pattern is particularly useful when you want to enforce a certain structure or set of behaviors across multiple subclasses. By using abstract base classes, you ensure consistency and prevent incomplete or improperly structured classes from being used. This leads to more reliable and maintainable code as it guarantees that certain methods will always be available in the subclasses, making the program's design more robust. Question 46. What is the difference between overloading and overriding in Python? Overloading and overriding are two different concepts in object-oriented programming. Overloading allows multiple methods with the same name but different parameters, though it's not natively supported in Python. However, you can mimic it using techniques like default arguments or args and quarks to handle different parameter inputs. Overriding, on the other hand, is fully supported in Python. It enables a child class to modify or extend the behavior of a method inherited from the parent class. While overloading focuses on creating different versions of a method based on input, overriding is used when you want to change the behavior of an inherited method in a subclass. Overloading is helpful when you want a function to handle different tasks based on input parameters, but in Python you need to use alternatives. Overriding is typically used when you need to customize the inherited behavior in a subclass. Practical implementation for method overloading. In this example, we explore how method overloading can be mimicked in Python by using default arguments. Python does not natively support method overloading in the traditional sense, where you can define multiple methods with the same name but different numbers or types of parameters. Instead, Python achieves similar functionality by allowing you to define default values for function parameters. This way, a single method can handle different numbers of arguments by using default values when some parameters are not provided. The class calculator has a method called add that takes three parameters a, b, and c, with b and c having default values of 0. When the method is called, Python will assign the provided arguments to a, b, and c, and if fewer than three arguments are passed, the missing parameters will use their default values. This approach allows the method to behave differently depending on how many arguments are supplied during the call, mimicking the effect of method overloading. For example, when we call cal.add5, the method only receives one argument, so b and c default to 0, and the result is 5. When we call cal.add5, 10 two arguments are provided and only c defaults to 0, resulting in 15. When we call call.add5, 10, 15 all arguments are provided and the result is 30. This allows the add method to handle a variable number of arguments without needing multiple method definitions. This technique demonstrates the flexibility of Python's function definitions and provides a way to handle different cases in a single method, which can simplify code and make it more maintainable. Practical implementation for method overridden. In this example, we illustrate the concept of method overriding in object-oriented programming using Python. The base class animal defines a generic method called sound, which returns a generic string some generic animal sound. This method represents the default behavior for any animal. However, in real-world scenarios, different animals make different sounds, so the method is overridden in the child classes. We have two child classes, dog and cat, both of which inherit from the animal class. In each child class, the sound method is overridden to provide more specific behavior. The dog class overrides the method to return bark, while the cat class overrides it to return meow. This way, although both dog and cat inherit from animal, they exhibit different behaviors when the sound method is called. This is a key feature of polymorphism, where the same method can behave differently depending on the object calling it. When we create instances of the dog and cat classes and call their sound methods, the overridden methods in the respective classes are executed, demonstrating the flexibility of method overriding. For the dog instance, calling dog.sound returns bark, while calling cat.sound on the cat instance returns meow. This behavior allows the program to differentiate between the sounds of different animals, even though they share the same method name. In summary, method overriding enables child classes to provide their own specific implementations of methods inherited from a parent class, allowing for customized behavior while maintaining a shared interface. This approach promotes code reuse, flexibility, and clarity in class hierarchies, making it a fundamental aspect of polymorphism in object-oriented programming. Question 47. How do you create a private attribute in Python? In Python, a private attribute is an attribute meant to be hidden from outside access, helping to protect the internal state of an object. Although Python doesn't have true private attributes, you can simulate this by using a naming convention called name mangling. By prefixing an attribute with two underscores, e.g. underscore underscore attribute, Python automatically changes its name, making it harder to access from outside the class. This promotes encapsulation, allowing you to safeguard sensitive data while still maintaining flexibility within the class. Creating a private attribute. In Python, private attributes are created by adding double underscores underscore underscore before the attribute name, signaling that it's meant to be accessed only within the class. This triggers a process called name mangling, where Python changes the name internally to prevent accidental access from outside the class. For example, if you define a private attribute like self dot underscore underscore private underscore attribute, it becomes harder for external code to access or modify directly, ensuring better encapsulation and data protection in your class design. Practical implementation. In this example, we explored the concepts of encapsulation and access control in Python using public and private attributes. The class car has two attributes, underscore underscore brand, which is private, and model, which is public. Encapsulation is an important principle in object-oriented programming (OOP), and it ensures that the internal state of an object is protected from direct access or modification from outside the class. The underscore underscore brand attribute is defined with two leading underscores, underscore underscore, making it private. This means it cannot be accessed directly from outside the class, as Python uses name mangling to change the attribute's name internally. Name mangling prevents external code from accidentally or intentionally accessing private attributes. However, we can still access underscore underscore brand using a method inside the class, such as get underscore brand. This method provides a controlled way to retrieve the value of the private attribute without exposing it directly. This is an example of encapsulation where we hide an attribute's details and provide controlled access through methods. The model attribute, on the other hand, is a public attribute and can be accessed and modified directly from outside the class. Public attributes are meant to be openly accessible without any restrictions. Although it's technically possible to access private attributes using name mangling, e.g. car underscore underscore brand, this is considered poor practice as it violates the principle of encapsulation. Name mangling is Python's way of preventing direct access to private attributes, but it does not provide absolute protection. It's a signal to developers that the attribute is intended to be private. Overall, this example highlights how encapsulation helps protect the integrity of an object's internal state by restricting access to its attributes and providing methods to access or modify them in a controlled manner. It shows the importance of using public and private attributes to differentiate between what should be accessible to external code and what should remain hidden for internal use only. Question 48. What is encapsulation and how is it achieved in Python? Encapsulation is a key concept in object-oriented programming where data and methods that act on that data are bundled together in a class. In Python, encapsulation allows you to protect internal object data by restricting access, ensuring that it can only be modified or accessed through controlled methods. This helps prevent unintended interference or changes to the data. Python achieves encapsulation through naming conventions. Prefixing an attribute with a single underscore underscore suggests it is intended for internal use, while double underscores underscore underscore make it harder to access or override from outside the class. How encapsulation is achieved in Python. In Python, encapsulation is achieved by defining public, protected, and private members in a class. Public members are accessible from anywhere, protected members are meant to be accessed only within the class and its subclasses, and private members are restricted to the class itself. Python enforces encapsulation through a mechanism called name mangling, where private attributes are prefixed with double underscores, making them harder to access from outside the class but still not entirely inaccessible. This helps in controlling access to sensitive data and ensuring internal class logic is protected. 1. Public members. Public members in Python are accessible from outside the class, meaning they can be used by any code that interacts with the class. By default, all class attributes and methods are public unless otherwise specified. Public members don't require any special notation as no leading underscores are used to indicate their visibility. This makes them the default choice for most class interactions, providing flexibility and ease of use for developers when creating or accessing objects. Practical implementation. In this example, we define a simple car class with two public attributes, brand and model, and a method display that returns the car's details as a formatted string. Public attributes in Python are accessible directly from outside the class, allowing easy interaction with the object's data. When an instance of the car class is created, the underscore underscore init constructor method is called to initialize these two attributes, which are passed as arguments, in this case Toyota and Camry. The display method demonstrates how methods within the class can use the object's attributes. This method returns the car's brand and model in a single formatted string. In this example, when we call car.display, it outputs Toyota Camry combining the brand and model. Since both brand and model are public, we can directly access them outside the class. For example, car.brand will output Toyota, showing that public attributes can be easily retrieved and modified without needing special methods such as getters or setters. Second, public attributes are ideal when you want to allow external code to interact freely with an object's data. This example illustrates the use of public attributes in object-oriented programming, where attributes can be accessed directly without restrictions. It makes the class easy to use and maintain for scenarios where full access to the object's properties is acceptable. However, if stricter control over data access and modification is needed, private attributes and accessor methods like getters and setters and share would be used. To protected members. Protected members are used for internal purposes within a class and its subclasses, but technically they can still be accessed from outside the class, although it's not recommended. They are indicated by a single leading underscore underscore to signal that they are not meant to be accessed directly from outside the client. This is more of a convention to inform developers that these members are intended for internal use only. Practical implementation. In this example, we explore the concept of protected attributes and methods in Python using the class car. The attribute underscore engine and the method underscore start underscore unmachine are marked as protected by using a single leading underscore underscore. In Python, the single underscore is a naming convention that signals to developers that these members are intended for internal use within the class or by subclasses. Even though Python does not enforce strict access control like some other programming languages, the underscore engine attribute holds the value V6, representing the car's engine type. Even though it is technically accessible from outside the class, the leading underscore conventionally indicates that it should not be accessed directly by external code. Similarly, the underscore start underscore engine method, which prints engine started, is marked as protected. This method is designed to simulate starting the car's engine, but again should be used internally rather than being invoked directly by code outside the class. While it's possible to access protected members like car.engine and car.start underscore engine from outside the class, doing so is discouraged because it violates the encapsulation principles of object-oriented programming. The use of the single underscore provides a soft warning to developers that these members are not part of the public interface and should be treated with care. Protected members are generally meant to be accessed or overridden by subclasses, but not by external code, but external the class interacts with the class. This approach to access control in Python is less restrictive compared to private members denoted with double underscores, but it still helps in promoting good coding practices by indicating which parts of the class are meant to be internal or subclass only. Therefore, while the code allows direct access to underscore engine and underscore start underscore up engine, doing so goes against the intended design and should be avoided in well-structured programs. 3. Private members. Private members in Python are attributes or methods that can't be accessed directly from outside the class. They are defined by a double leading underscore underscore underscore, which triggers name mangling, making it harder to access them externally. Private members are helpful when you want to protect internal details of a class, ensuring that data is secure and can't be modified unintentionally. They provide an extra layer of control and help maintain the integrity of the class's internal state. Practical implementation. In this example, we explore the concept of private attributes and methods in Python, which play a crucial role in encapsulation, a key principle of object-oriented programming (OOP). The car class demonstrates how to restrict access to certain parts of an object by marking attributes and methods as private using double underscores underscore underscore again. This signals that these members should only be accessed from within the class and not be entire external code. The attribute underscore underscore engine is marked as private in the constructor. This means that it cannot be accessed or modified directly from outside the class. Attempting to access car dot underscore underscore engine would result in an attribute error because Python uses a feature called name mangling to change the name of the private attribute, making it harder to access from the outside. Similarly, the method underscore underscore start underscore engine is also private, meaning it cannot be called directly from outside the class. It is only accessible from within the class. To provide controlled access to the private method, the class defines a public method called start. This method can be called from outside the class and it internally calls the private underscore underscore start underscore engine method to start the car's engine. This approach allows us to protect the internal workings of the car class while still providing a way for external code to interact with the object in a controlled by. By using private members, we ensure that the internal state of the object and certain behaviors remain hidden and protected from external interference. This promotes data integrity and prevents unintended modifications. Encapsulation is a key feature of OP that helps create well-structured, maintainable, and secure code. In this case, the car class encapsulates its engine-related functionality, exposing only what is necessary while keeping sensitive parts hidden. 4. Name mangling. Name mangling in Python is a technique where private members of a class attributes or methods are renamed internally to include the class name. This prevents direct access to these private members from outside the class, ensuring better encapsulation. However, these private members can still be accessed indirectly by using the mangled name, which follows the pattern underscore class name underscore underscore website underscore member. Name mangling adds an extra layer of protection but doesn't make private members completely inaccessible. Practical implementation. In Python, attributes marked with double underscores e.g. underscore underscore engine are considered private, meaning they are not intended to be accessed directly from outside the class. However, Python uses a technique called name mangling to make it harder to access these private attributes, but it doesn't provide complete protection. Name mangling works by internally changing the name of the private attribute to include the class name as a prefix. In this example, the private attribute underscore underscore engine inside the car class is renamed internally to underscore car underscore underscore engine. By using printcar dot underscore car underscore underscore engine, you are bypassing Python's name mangling and directly accessing the private attribute. This line will print V8, the value of the underscore underscore engine attribute. While this is technically possible, it is considered bad practice because private attributes are intended to be used only within the class or through specific methods designed to provide controlled access. The purpose of private attributes is to enforce encapsulation, a core principle in object-oriented programming (OOP). Encapsulation allows you to hide the internal details of a class, ensuring that the class's internal state and implementation details are protected from external interference or accidental changes. Accessing private attributes directly via name mangling goes against this principle as it exposes the internal details that are meant to be hidden. Question 49. How do you implement polymorphism in Python? Polymorphism in Python is the ability to define a common interface that works across different data types or classes, making code more flexible and reusable. It allows objects of different types to be handled using the same method or function, enhancing consistency. One way to implement polymorphism is through method overriding, where subclasses provide specific implementations of inherited methods. Another way is through dunder methods such as underscore underscore stew or underscore 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 add, which enable built-in functions or operators to work with various object types, promoting ease of use and adaptability. Types of polymorphism in Python. In Python, polymorphism allows functions, methods, or operators to behave differently based on the types of objects they are working with. With polymorphism in functions, the same function can accept different types of objects and perform different actions depending on the object passed. In polymorphism with classes, also known as method overriding, child classes can provide their own version of methods inherited from parent classes, ensuring the right behavior for each class. Polymorphism with operators means that operators like or can perform different operations depending on the object type, like adding numbers or concatenating strings. Practical implementation polymorphism with functions. In this example, we explored the concept of polymorphism in Python, specifically focusing on how a single function can handle different types of data and perform different operations based on the type of its arguments. Polymorphism is a key principle in object-oriented programming (OP), allowing objects or functions to take on multiple forms. In Python, functions are inherently polymorphic, meaning they can operate on different types of data without the need for multiple definitions or overloading. The add function in this example demonstrates polymorphism by accepting two arguments a and b. Depending on the type of these arguments, Python determines whether to perform an arithmetic addition or string concatenation. When integers are passed as arguments e.g. add 1, 2, the function returns their sum 3. When strings are passed e.g. add hello world, the function concatenates the two strings and returns hello world. This flexibility is one of the strengths of Python, as the language dynamically handles different data types at runtime. Unlike languages where you need to explicitly define multiple versions of a function to handle various data types, Python allows you to write a single function that can seamlessly operate on different types of inputs. This makes the code more concise, usable, and easier to maintain. Practical implementation, polymorphism with classes method overriding. In this example, we explore polymorphism through the concept of method overriding in object-oriented programming. The base class animal defines an abstract method sound which is intended to be implemented by subclasses. The animal class raises a not implemented error, signaling that subclasses must provide their own implementation of this method. This sets the foundation for creating flexible and usable code, as the animal class defines a common interface, the sound method, while allowing subclasses to implement it in their own way. Two subclasses dog and cat inherit from the animal class and override the sound method to provide their own specific behaviors. The dog class returns bark and the cat class returns meow, showing how method overriding works in practice. Each subclass defines its own version of the sound method, which replaces the abstract version in the parent class. The function make underscore sound demonstrates polymorphism by accepting any object that has a sound method regardless of its class. When a dog object is passed to the function, it prints bark, and when a cat object is passed, it prints meow. This is the essence of polymorphism. Different objects, in this case, dog and cat, can be treated the same way by calling the sound method, but they behave differently based on their individual implementations. Polymorphism through method overriding allows the same function make underscore sound to work seamlessly with different types of objects without next thou each class. This results in more flexible, maintainable, and reusable code. The function can interact with any future subclasses of animal as long as they implement the sound method, making it a powerful technique for handling different behaviors in a consistent way. This approach exemplifies one of the core principles of OP, where classes share a common interface but exhibit distinct behaviors. Practical implementation polymorphism with dunder methods operator overloading. In this example, we explore polymorphism with dunder methods, specifically focusing on operator overloading in Python. Operator overloading allows us to define custom behavior for built-in operators, like when they are used with user-defined objects. The class vector demonstrates how we can override the default behavior of operator by implementing the special method underscore 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 add. This method dictates how two vector objects should be added together. In the vector class, the underscore underscore add method is designed to add the x and y coordinates of two vectors. When we use v1, v2, Python automatically calls the underscore underscore add method of the vector class, which returns a new vector object with the sum of the respective coordinates. This makes the operator behave as expected for vector objects, just as it would for built-in types like integers or floats. By overriding this method, we make the operator more intuitive and applicable to custom objects without needing to explicitly write an addition methods. Additionally, the underscore underscore repr method is overridden to provide a clear and informative string representation of the vector object when it is printed. This method is essential for debugging and understanding the state of an object as it ensures that printing a vector displays it in a human readable format such as vector 6. 8. Question 50. What is the purpose of the pass statement in Python? The pass statement in Python acts as a placeholder when you need to define code blocks like functions, loops, or conditionals but don't want to add any functionality yet. It allows you to write the structure of your code without causing syntax errors, making it useful when you're still planning or leaving space for future code. While the code block will do nothing when executed, pass ensures your program runs smoothly without breaking the flow. Key use cases of pass. The pass statement in Python is a simple placeholder used in various scenarios to avoid errors when no action is needed. In function or class stubs, it's useful when you're defining a function or class but haven't implemented the logic yet. Serving as a placeholder while the structure is being built. In empty control structures like loops or conditionals, it allows you to skip an action when nothing needs to be done at that point in the code. For prototypes or incomplete code, pass helps you outline your program during early development, letting you focus on structure before adding functionality. Practical implementation. In this example, we explored the use of the pass statement in Python, which serves as a placeholder when writing code. The pass statement is often used when defining functions, classes, or conditional blocks that are not yet implemented. It allows the programmer to create the necessary structures without causing syntax errors while indicating that the actual logic or implementation will be added later. For instance, the function my underscore function is defined but has no logic at the moment. The pass statement is placed inside the function to allow the code to run without error. Without pass, Python would expect some code in the function body and leaving it empty would raise a syntax error. Similarly, in the conditional block, if true, the pass statement is used because no action is required at the moment. This allows the code to be syntactically valid while signaling that logic might be added to this block in the future. Finally, the class myClass is defined with the pass statement, meaning that the class exists but has no attributes or methods yet. This is helpful when laying out the structure of a program and leaving space for future class functionality. Question 51. What is duck typing in Python? In Python, duck typing means that the type of an object is determined by how it behaves, not by what class it belongs to. This concept is captured by the saying, if it looks like a duck and quacks like a duck, it must be a duck essentially. As long as an object has the methods or attributes expected by the code, it can be used as that type. Python doesn't require the object to explicitly inherit from a specific class, making the code more flexible and adaptable. Key characteristics of duck typing. Duck typing in Python focuses on how an object behaves rather than its explicit type. If an object has the necessary methods or attributes, it can be used regardless of its type. This allows for more flexible and polymorphic code, enabling functions to work with various objects as long as they support the required operations. Python skips explicit type checking, making it easier to work with diverse object types, provided they behave as expected. This approach enhances flexibility and reduces the need for strict type enforcement, streamlining the coding process. Practical implementation. In this example, we explore the concept of duck typing in Python, which is a form of polymorphism. Duck typing is based on the principle of if it looks like a duck and quacks like a duck, it must be a duck. In Python, this means that an object's suitability for use is determined by the presence of certain methods or properties rather than by its actual type. The focus is on what an object can do its behavior rather than what it is its class. We define two classes, duck and dog. Both classes implement a method called quack. In the duck class, the quack method represents the natural behavior of a duck, outputting quack. In the dog class, although quacking is not a typical behavior of a dog, the method is still defined to print I'm a dog, but I can quack. This shows that even though the objects belong to different classes, they can both quack because they implement the same method. The function make underscore it underscore quack demonstrates duck typing by accepting any object as an argument and calling its quack method. The function does not care whether the object is a duck or a dog as long as the object has a quack method. The function will work. When make underscore it underscore quack is called with the duck object, it prints quack, and when called with the dog object, it prints I'm a dog but I can quack. The type of the object is irrelevant, the function works because both objects implement the expected behavior. This flexibility makes Python highly dynamic and versatile. It allows developers to write code that can interact with different objects in a uniform way, as long as those objects provide the necessary methods or attributes. In this case, the ability to quack is the key criterion for using the object, demonstrating how behavior is prioritized over the object's type. Duck typing simplifies polymorphism in Python, enabling more usable and flexible code by focusing on what objects can do rather than their inheritance, hierarchy, or type. Question 52. What is strong typing in Python? Strong typing in Python means that the language strictly enforces rules about data types and doesn't automatically convert one type to another during operations. For example, Python won't let you add a string and an integer without explicitly converting one of the types, ensuring that operations between incompatible types don't happen by accident. This approach helps catch errors and makes the code more predictable and reliable since you always know what type of data. Key characteristics. Python enforces type safety by preventing automatic conversion between incompatible types. For instance, you can't add a string and an integer without converting one of them explicitly. If you try something like 510, Python will raise a type error. This ensures that operations between incompatible types are caught early. Python is also strongly typed, meaning variables are tightly bound to their assigned type. You can change the type dynamically, but Python will still maintain strict type checks during operations. For example, equal to 5 can be later assigned as a string, a hello, but if you try to combine them in a way that doesn't make sense, like adding a string and integer, you'll get an error. To work with incompatible types, you must use explicit conversion casting. Python provides casting functions like int, text, and float to handle type conversions. For example, you can convert a string to an integer with int510 and Python will return 15. Python also supports type annotations, allowing you to specify expected types in functions and variables starting from version 3.5. These annotations don't enforce types at runtime but can help with static analysis. So, while Python doesn't check types during execution, it's a useful feature for catching type mismatches early in development. Practical implementation. In this example, we explored the concept of strong typing in Python, which ensures that operations between incompatible data types result in an error rather than automatic type conversion. Python enforces strict rules about how values of different types can be used in operations. Here we attempt to add a string x5 and an integer e10. Since Python is strongly typed, it does not allow the implicit addition of a string and an integer, and doing so raises a type error. This behavior prevents unexpected results that might occur if the language automatically converted types without the programmer's intent. To handle this error, we use a try except block, which is a mechanism for error handling in Python. When the code tries to perform the operation xy, the type error is raised because Python does not know how to add a string and an integer together. The except block catches the error and prints an error message indicating the type mismatch. This prevents the program from crashing and gives the programmer a chance to understand the mistake. The correct way to handle this situation is by explicitly converting the string to an integer before performing the addition. This is done using the int function, which converts the string 5 into the integer 5. Once the types are compatible, Python allows the addition to proceed and the result is correctly calculated as 15. Question 53. What is monkey patching in Python? Monkey patching in Python refers to the ability to modify or extend the behavior of a class or module dynamically at runtime without altering the original source code. It's often used to fix bugs, add features, or extend functionality in third-party libraries. In testing, monkey patching helps override methods for mocking purposes. While it offers flexibility, it's important to use monkey patching carefully, as it can lead to unexpected behavior if not managed properly, especially when modifying external libraries. How monkey patching works. Monkey patching involves modifying or extending the behavior of a class or module at runtime by dynamically assigning new methods or attributes. This technique allows you to override the original functionality without altering the source code, giving you full control over how the class or module behaves. By directly modifying the behavior at runtime, monkey patching provides a quick and flexible way to adapt code. But it should be used carefully to avoid unintended side effects or conflicts in larger systems. Practical implementation. In this example, we explored the concept of monkey patching in Python, which allows for the dynamic modification of a class or object's behavior at runtime. Initially, we define a dog class with a method bark that returns woof, representing the typical sound a dog makes. When we create an instance of the dog class and call the bark method, the original behavior is observed with the output woof. However, through monkey patching, we can change the behavior of this method without altering the original class definition. A new function new underscore bark is created, which returns meow, simulating a dog that now meows like a cat. We then assign this new function to dog.bark, effectively replacing the original bark method with the new one. As a result, when the bark method is called again on the dog instance, it now returns mew instead of woof. Monkey patching is a useful technique in scenarios where you need to modify or extend the behavior of a class or object dynamically, especially in testing or when integrating with third-party libraries. It allows you to alter the behavior of existing code without modifying the original source. However, it should be used with caution as it can make the codebase harder to understand and debug, especially if patches are applied in multiple places, leading to unexpected or conflicting behaviors. Question 54. What is the purpose of the global and non-local keywords? In Python, the global and non-local keywords help manage variable scope, enabling you to access or modify variables from different scopes. The global keyword allows you to reference or change a variable defined at the global module level from within a function. On the other hand, non-local is used within nested functions to access or modify variables in the nearest enclosing scope that is not global. Both keywords help you control where and how variables can be used, ensuring that your code can modify variables across different levels of scope when needed. 1. Global keyword. The global keyword in Python allows you to modify a variable that exists in the global scope from within a function. Normally, variables inside functions are treated as local, meaning any changes to them don't affect variables outside the function. By using global, you're telling Python to use and modify the variable defined globally, ensuring that changes within the function impact the variable outside the function as well. Key purpose. The key purpose of this concept is to allow functions to access and modify variables that are defined outside their local scope, typically in the global scope. This enables functions to interact with and change global variables, providing flexibility in managing data that exists beyond the function's immediate environment. Practical implementation. In this example, we explored the use of the global keyword in Python, which allows a function to modify a variable that exists in the global scope. Normally, variables defined inside a function are local to that function, meaning changes to those variables do not affect variables outside the function. However, by using the global keyword, we can explicitly state that we are referring to and modifying a global variable from within the function. Initially, the global variable x is set to 10. Inside the function modify underscore global, we use global x to tell Python that we are referring to the global x, not creating a local one. The function then changes the value of x to 20. This change is reflected globally, so after the function is called, x remains 20 even outside the function. The program demonstrates this by printing the value of x both inside and outside the function, showing the updated value of 20 in both cases. This example illustrates the potential of the global keyword to modify variables that are outside the local function scope, impacting the entire program. While this can be useful for managing shared state, it should be used sparingly and with caution. Relying too heavily on global variables can make a program harder to debug and maintain because changes to global state in one part of the code can have unintended consequences elsewhere. Therefore, it's important to carefully manage when and how global variables are modified to avoid introducing side effects that are difficult to track. To non-local keyword. The non-local keyword in Python allows you to refer to a variable in the nearest enclosing but not global scope. This is especially useful in nested functions when you want to modify a variable from the outer function. Without non-local, variables inside nested functions are treated as local to that function. By using non-local, you ensure that changes in the inner function are reflected in the outer function's variable, enabling more flexible and dynamic behavior in your code. Key purpose. The key purpose of this approach is to modify a variable in the nearest enclosing scope, ensuring that changes affect the local context but without impacting the global scope. This allows for more controlled and isolated variable updates within specific functions or blocks of code, preserving the integrity of the broader program state. Practical implementation. In this example, we explored the use of the non-local keyword in Python, which allows a nested function to modify a variable from its enclosing non-global scope. Here we define two functions, outer underscore function and inner underscore function. The variable is initially set to 5 inside outer underscore function. This variable exists in the enclosing scope, meaning it is local to outer underscore function but can be accessed by any inner functions defined within it, such as inner underscore function. Inside inner underscore function, we use the non-local keyword to specify that we are referring to the y variable from the outer function scope, rather than creating a new local variable. By doing this, inner underscore function can modify the value of y from 5 to 10. The modified value of y is printed both inside inner underscore function and later in outer underscore function, demonstrating that the change persists across both scopes. The non-local keyword is essential in scenarios involving nested functions where the inner function needs to modify or interact with variables from its enclosing function. Without non-local, the inner function would create a new local variable, leaving the originally from the outer function unchanged. This mechanism is especially useful for managing state within closures or nested function calls, allowing for more flexible control over variable access and modification in nested scopes. In summary, this example shows how non-local allows an inner function to modify a variable from its enclosing scope, making it a powerful tool in Python for working with closures and nested functions. It provides a way to manage and maintain state across multiple levels of function scope without resorting to global variables. Question 55. How does the abstract base class module work in Python? The apps module in Python allows you to define abstract base classes ABCs which act as blueprints for other classes. These abstract classes cannot be instantiated directly and must be inherited by subclasses that implement the abstract methods. This ensures that any subclass defines the required methods, helping to enforce a consistent structure across different classes. By using ABCs, you can create a framework where all subclasses follow a specific design, providing a way to ensure key methods are implemented. Key features of ABC. Abstract base classes ABC are used to define a blueprint for other classes. They contain abstract methods, which are methods without implementation, and any class inheriting from the ABC must provide concrete implementations of these methods. ABCs can be instantiated directly, meaning you can't create objects from them until all abstract methods are implemented in a subclass. This ensures that any child class follows the structure and rules set by the abstract class, promoting consistency and clear design. Practical implementation. In this example, we explore the concept of abstract base classes, ABCs, and method overriding in Python. An abstract base class defines a blueprint for other classes by specifying methods that must be implemented in any subclass. In Python, this is done using the app module where the abstract method decorator is used to define methods that do not contain an implementation in the base class. These methods act as placeholders, enforcing that any subclass provides its own implementation. Abstract-based classes cannot be instantiated directly. They are used to ensure that subclasses follow a specific interface. Here, the animal class is an abstract base class with an abstract method sound. This method doesn't have a body in the animal class, meaning it must be implemented by any class that inherits from animal. The subclasses dog and cat both inherit from animal and override the sound method to provide their own implementation. Dog returns woof and cat returns meow. Since these subclasses provide the required method, they can be instantiated and used without any issues. On the other hand, the subclass bird inherits from animal but does not implement the sound method. Because of this, attempting to instantiate bird will raise a type error, as Python enforces the rule that all abstract methods must be implemented before an instance can be created. This behavior ensures that every subclass of animal provides the necessary behavior defined in the abstract base class. This design pattern is particularly useful when you want to enforce a certain structure or set of behaviors across multiple subclasses. By using abstract base classes, you ensure consistency and prevent incomplete or improperly structured classes from being used. This leads to more reliable and maintainable code, as it guarantees that certain methods will always be available in the subclasses, making the program's design more robust. Question 56. What is the difference between underscore underscore t and underscore underscore repr? In Python, both underscore underscore t and underscore underscore repr are special methods that return string representations of an object, but they serve different purposes. The underscore underscore star method is designed to provide a user-friendly or readable string that makes sense to an end user or for general display. It's the kind of output you'd want to show when printing or logging an object. On the other hand, underscore underscore rep is meant for developers and debugging. It returns a more detailed, unambiguous string that could ideally recreate the object if passed to eval. While underscore underscore star is focused on simplicity and readability, underscore underscore rep aims for accuracy and precision, which is useful for inspecting objects during development. If underscore underscore star is not defined, Python falls back to using underscore underscore rep in some context, and if neither is defined, Python defaults to its own basic object representation. For example, if you call underscore underscore star, you might get username John, a format that's clear to their user. If you call underscore underscore repre, the output might be user John, which is more useful for developers working on the code. In summary, underscore underscore star is for readability and general use, while underscore underscore rep is for accuracy and debugging. Question 57. What are magic methods, dunder methods in Python? Magic methods, also known as dunder methods short for double underscore, are special methods in Python that start and end with double underscores like underscore underscore init and underscore underscore tree. These methods allow developers to define or customize the behavior of their objects in Python, making it possible to perform actions like initializing a class, printing objects in a user-friendly format, or enabling iteration through custom objects. For instance, underscore underscore init is used to initialize variables when an object is created, while underscore underscore star defines how the object should be displayed in a readable format. Similarly, methods like underscore underscore getItem and underscore underscore setItem enable square bracket syntax for accessing and setting items in custom collections, just like lists or dictionaries. Magic methods play a crucial role in making Python objects behave in more intuitive ways. For example, underscore underscore len returns the length of custom objects, while underscore underscore utter and underscore 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 next allow objects to be used in loops. Operators like and can also be overridden using underscore underscore add, underscore 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 IQ, and underscore underscore else, allowing custom objects like complex numbers or vectors to be compared or added together naturally. In addition, Python provides context management magic methods such as underscore underscore enter and underscore underscore exit, which are used with statements to manage resources like file handling or database connections, ensuring that cleanup is performed automatically. Each of these methods gives developers the ability to create flexible, powerful classes that integrate seamlessly with Python's built-in functionalities, making code easier to write, read, and maintain. Practical implementation. This example demonstrates the power of operator overloading in Python, where special methods, often called dunder methods short for double underscore, allow objects to behave more like built-in types. These methods enable you to customize how objects interact with built-in functions and operators, making them more intuitive and flexible to work with. The myClass class provides several dunder methods that mimic behaviors typical of built-in Python objects. For instance, the underscore underscore star and underscore underscore refer methods define how an object is represented as a string. Underscore underscore is used for a user-friendly, human-readable format for display, while underscore underscore rep is designed for debugging, showing a more formal, detailed representation of the object. The underscore add method allows instances of my class to be added together using the operator, combining both their name and value attributes. This is an example of overloading the addition operator to provide a custom behavior for objects. The class also includes methods for handling list-like behaviors. The underscore len method allows instances of my class to return the length of the items list when passed to len, and underscore gettype enables accessing elements in the list using index notation, e.g. obj1. Additionally, underscore setitem allows modifying list elements via indexing, while underscore deletem facilitates deleting items from the list in the same manner. These methods make instances of my class act like containers, providing familiar functionality that users expect from lists. Overall, this example showcases how dunder methods allow you to define custom behaviors for objects, enabling them to interact seamlessly with built-in functions and operators. This approach makes objects more flexible, natural to use, and aligned with Python's philosophy of making everything as intuitive as possible. By overloading operators and customizing object behavior, you can create classes that integrate smoothly with Python's syntax and functionality, enhancing both usability and readability. Question 58. How do you handle exceptions in Python? In Python, exceptions are handled using try, except, else, and finally blocks. You place the code that might raise an exception inside the try block. If an error occurs, the program jumps to the except block where you define how to handle the error. The else block runs if no exception is raised, allowing you to execute code that should only run when everything goes smoothly. The finally block always executes regardless of whether an exception was raised or not, making it perfect for cleanup tasks like closing files or releasing resources. Key components of exception handling. Exception handling in Python is a way to manage errors gracefully. The try block contains the code that might cause an error, and if something goes wrong, Python skips the rest of the block and moves to the except block, where the error is caught and handled. You can either catch specific exceptions or use a general except to handle any error. The else block is optional and runs only if no exceptions are raised in the try block, while the finally block always runs, regardless of whether an exception occurred or not, often used for cleanup tasks like closing files. Practical implementation. This example demonstrates Python's exception handling using the try except else finally structure, which allows you to manage person. The code inside the try block is where potential exceptions might occur. In this case, the user is prompted to input a number and then a division operation is performed. However, this operation can fail for two main reasons. The user might enter an invalid input such as a string instead of a number, or they might enter 0, leading to a division by 0 error. Both of these scenarios are handled by specific except blocks. The value error is raised when the user input cannot be converted to an integer, and the except value error block catches this error and prints a user-friendly message. Similarly, the zero division error is raised when an attempt is made to divide by 0, and the corresponding except zero division error block handles this case, informing the user that division by 0 is not allowed. If no exceptions are raised, the else block is executed and the result of the division is displayed. The else block provides a way to handle the successful execution of code after ensuring that no errors occurred. Finally, the finally block is executed regardless of whether an exception was raised or not. It is commonly used for cleanup actions like closing files or releasing resources, ensuring that certain tasks are always performed even if an error occurs. In this example, it prints execution completed to indicate that the program has finished executing. Overall, this structure ensures that the program does not crash unexpectedly and provides clear messages to the user when errors occur. It also guarantees that certain operations, such as cleanup, are always performed, making the code more robust and maintainable. By handling specific exceptions, the program can respond to different error conditions in a controlled manner, ensuring a smoother user experience and better error management. Question 59. What is the assert statement used for in Python? In Python, the assert statement is a tool used to check if a certain condition holds true during execution. It's mainly used for debugging, where you expect a specific condition to be true. If the condition evaluates to false, an assertion error is raised, signaling that something is wrong with the assumption made in the code. This helps catch bugs early, ensuring that certain expectations in your code are met during runtime. Key characteristics of assert. The assert statement is a useful tool for checking whether a certain condition is true. If the condition turns out to be false, it raises an assertion error, helping catch issues early. It's commonly used in the development phase for debugging as it allows you to test assumptions and ensure logical consistency in your code. You can also include an optional error message with the assert statement to make it clear why the check failed, which is helpful when tracking down bugs. Importantly, assert statements are ignored when Python is run in optimized mode Python O, meaning they won't impact performance in production environment. Syntax of assert J. The assert statement is a simple way to check if a condition is true in Python. If the condition evaluates to true, the program continues running as normal. However, if the condition is false, assert raises an associator optionally showing a custom error message. It's often used for debugging and ensuring that critical assumptions in the code are met. The basic syntax is assert condition optional error message where the condition is what you're checking and the message gives additional digs when the message. So, practical implementation. In this example, we use an assertion to enforce a condition before performing division. The divide function takes two parameters, a numerator and b denominator, and attempts to divide a by b. Before the division is carried out, the assert statement checks whether b is 0. The assertion acts as a safeguard by ensuring that b 0e, the divisor is not 0. If this condition is violated, an assertion error is raised accompanied by the message b cannot be 0, division by 0 is undefined. This stops the execution and prevents an undefined mathematical operation from taking place. Assertions are a powerful tool for catching logical errors early in the code execution process. They help verify that critical assumptions such as the divisor should never be 0 hold true. If the assertion fails, the program immediately raises an error, preventing further execution and allowing developers to handle the issue right away. In this case, dividing by 0 is mathematically undefined and would cause a runtime error, so the assertion ensures the program doesn't proceed with an invalid operation. Invalid cases such as divide 10 to the assertion passes because b is not 0, allowing the division to proceed normally and returning the correct result. In invalid cases like divide 10 0, the assertion catches the error condition, raises an error, and provides a clear error message. This makes the code more robust by preventing runtime errors and providing early error detection. Question 60. How do you handle circular imports in Python? Circular imports in Python happen when two or more modules depend on each other, creating an import loop. For example, module A imports module B and module B imports module A, which can lead to an import error or cause incomplete imports. Python executes code during the import process, which can cause issues when dependencies are cyclical. To resolve this, you can break the import chain by refactoring your code, such as moving imports into functions or using a shared third module to manage common functionality. This helps to avoid circular dependencies and ensure smoother imports. Common causes of circular imports. Circular imports often occur when two modules depend on each other to function, leading to an import loop. This happens when both modules try to import each other simultaneously, creating a conflict. As projects grow larger, it's common for different classes or functions across modules to become interdependent, which can inadvertently lead to these circular import issues. Understanding these dependencies early on can help prevent circular imports by organizing code more modularly and breaking down large interdependent modules into smaller, self-contained ones. Techniques to handle circular imports. To handle circular imports effectively, one technique is to rearrange the imports, moving them inside functions or methods that need them instead of placing them at the top of the file. Another solution is to use import locally, which means importing modules only when required, delaying the import until the function is called. You can also refactor the code by breaking apart tightly coupled modules and creating a shared module to handle common functionality. For more dynamic needs, you can use importlib for dynamic imports, allowing you to import modules at runtime using importlib.import underscore module. Practical implementation. This example highlights a common issue in Python known as circular import, where two or more modules depend on each other. In the original version of the problem, module underscore A imports func underscore B from module underscore B, while module underscore B imports func underscore A from module underscore R. This creates a circular dependency because each module is trying to load the other before it is fully available. When Python encounters this situation, it fails to resolve the imports, leading to an import error or attribute error. This happens because Python loads modules sequentially, and in this case, each module is waiting for the other to finish loading, causing an infinite loop. The solution provided involves rearranging the imports to break the circular dependency. Instead of importing the other module at the top level, which happens when the module is first loaded, the imports are moved inside the functions themselves. This is known as local import. By delaying the import until the function is actually called, the circular dependency is avoided because Python only attempts to load Amzilla module when it is needed. And by that time, both modules have already been fully loaded. In this revised version, func underscore a in module underscore a imports func underscore b from module underscore b only when func underscore a is called. Func underscore b in module underscore b imports func underscore a from module underscore a only when func underscore b is called. By moving the imports inside the function bodies, Python can safely load both modules without running into the circular import problem. This technique of using local imports is a common and effective solution when two modules depend on each other. It ensures that the modules remain independent during the loading phase while still allowing them to reference each other at runtime. This solution preserves the necessary functionality without causing import errors, leading to a cleaner and more reliable code structure. Question 61. How does Python data class module work? The data class module in Python, introduced in Python 3.7, makes it easier to create classes that are primarily used for holding data by automatically generating common methods like underscore 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 init, underscore underscore repr, and underscore underscore akik. By using that data class decorator, you can define attributes and Python will take care of the boilerplate code for initialization and comparisons. This simplifies your class definition and helps you focus on the logic while reducing repetitive code. Key features of data class. The data class in Python simplifies class creation by automatically generating methods like underscore 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 init underscore underscore retrieve and underscore underscore ekik for you, so you don't have to write them manually. This makes it easier to define classes with minimal boilerplate code. For example, the underscore underscore init method is automatically created based on the fields you define. And underscore underscore repr gives a clean string representation of the object, which is really useful for debugging. Additionally, data class can generate comparison methods like underscore underscore and underscore underscore by setting the order true option. You can define class attributes as fields of the data class, and you can control their behavior using the field function. For example, you can specify default values for fields or set more complex options. If you want to make the class immutable, setting frozen true ensures that once the object is created, its attributes can't be changed, providing a layer of safety if you need the object to stay constant after initialization. Practical implementation. In this example, we use Python's data class to simplify the creation and management of class objects. That data class decorator imported from the data classes module allows us to define a class with minimal code by automatically generating several useful methods, such as underscore underscore init for initializing objects and underscore underscore repr for providing a human readable string representation of the object. Here we define a class person with three attributes: name, age, and city. The name and age fields are required when creating an instance of the class, while city has a default value of unknown, making it optional during object creation. The use of default values is one of the convenient features of data classes, allowing attributes to have predefined values if none are provided by the user. When we create an instance of person with just a name and age, in this case Alice and 30, the city field is automatically set to because it wasn't specified. The auto-generated underscore underscore repr method provides a string representation of the object when it is printed, showing the values of the attributes in a structured format. This makes debugging and inspecting objects easier. Additionally, accessing individual fields like name, age, and city is straightforward using dot notation. Data classes offer a powerful way to create simple classes that primarily store data without having to manually write boilerplate code for constructors, representations, or comparisons. Um, this feature enhances both code readability and maintainability. making it a preferred approach for data-centric classes in Python. Question 62. How is memory managed in Python? Memory management in Python is handled automatically by the Python Memory Manager. It allocates and deallocates memory as needed using techniques like reference counting and garbage collection to free up memory when objects are no longer bit. Python also uses memory pooling to optimize memory usage for small objects, ensuring that memory is managed efficiently without the developer needing to intervene. This makes memory management in Python both powerful and easy to work with as the process happens behind the scenes. Key aspects of memory management in Python. Python manages memory through several key mechanisms to optimize performance and ensure efficient memory usage. All Python objects and data structures are stored in private heap space, meaning the memory used is managed internally by Python and is not accessible directly to programmers. The Python memory manager takes care of allocating and organizing memory into areas specific to each object and also caches memory to optimize performance. Python uses reference counting to track how many references exist for an object. When this count reaches 0, Python automatically frees up the memory. Additionally, garbage collection is used to handle cases where objects reference each other, preventing memory from being freed. For smaller objects, Python uses memory pools managed by pmalloc to efficiently handle memory allocation and reduce overhead. Memory is dynamically allocated during runtime and reclaimed as needed either through reference counting or the garbage collector. However, developers can still accidentally create memory leaks by holding unnecessary references. In such cases, Python allows the garbage collector to be manually triggered to help manage memory better. Practical implementation. In this example, we explored two important aspects of Python's memory management system: reference counting and garbage collection (GC). Python uses reference counting as a primary method for tracking the number of references to an object. Each time a reference is made to an object, its reference count increases, and when a reference is removed, the count decreases. When the reference count drops to 0, the object is considered unreachable and becomes eligible for garbage collection. The sys.getRefCount function is used here to demonstrate how reference counting works by showing how the count changes when references are created and deleted. When we create a list and assign it to my underscore list, it has an initial reference count. As we assign the list to another variable, another underscore ref, the reference count increases. When we delete the reference, the count decreases accordingly. In addition to reference counting, Python uses garbage collection to manage objects that may be part of circular references, i.e., where two or more objects refer to each other, preventing their reference counts from reaching 0. In the second part of the example, we use the GIS module to control the behavior of Python's garbage collector. We demonstrate how to check whether garbage collection is enabled gc.is enabled, manually disable it gc.disable, and re-enable it gc.enable. Disabling garbage collection can be useful in scenarios where you want to control when objects are cleaned up, especially in performance critical applications or when managing large amounts of data. This example provides insight into how Python manages memory under the hood. Reference counting handles the immediate release of memory when objects are no longer needed, while garbage collection is used to handle more complex cases, ensuring that memory is efficiently freed even in the presence of circular references. Together, these mechanisms work to optimize memory usage and prevent memory leaks in Python applications. Question 63. How does Python's garbage collection work? Python's garbage collection works by automatically freeing up memory that is no longer being used by the program, helping manage memory efficiently without manual intervention. It relies on two main mechanisms: reference counting and a cyclic garbage collector. Reference counting tracks how many references an object has, and when the count reaches 0, the object is immediately deleted. The cyclic garbage collector is used to detect and remove reference cycles when two or more objects reference each other, preventing them from being cleaned up by reference counting alone. Together, these mechanisms ensure Python manages memory smoothly, making it easier for developers to focus on coding without worrying about memory management. 1. Reference counting. In Python, every object keeps track of how many references point to it, known as reference counting. When an object's reference count drops to 0, meaning no references are left, Python automatically frees up the memory occupied by that object. This system ensures efficient memory management by cleaning up objects that are no longer in use without needing explicit intervention from the programmer. 2. Garbage collection for circular references. Circular references happen when two or more objects reference each other, creating a cycle that prevents their reference counts from reaching zero, which could lead to memory leaks. To solve this, Python uses a cyclic garbage collector that detects and cleans up objects involved in these cycles. This garbage collector uses a three-generation system where newer objects are checked more often, and objects that survive multiple collection cycles are promoted to older generations for less frequent checks. Key points. Python uses reference counting to manage memory, meaning objects are automatically deallocated when their reference count drops to zero. In cases where objects have circular references, Python cyclic garbage collector steps in to clean them up. Additionally, Python employs a generational collection system where objects are grouped into three generations, with younger objects being collected more frequently since they are more likely to become unreachable quickly. This approach helps optimize memory management while maintaining efficiency. Practical implementation. In this example, we explored Python's garbage collection mechanism, specifically focusing on how it deals with circular references. Python uses automatic garbage collection to manage memory, freeing up objects that are no longer needed by the program. However, when two or more objects reference each other, forming a circular reference, their reference count never drops to zero, even if there are no external references to them. This can result in memory leaks if not handled properly. Python's garbage collector can detect and clean up these circular references, but sometimes it needs to be manually triggered, especially in more complex scenarios. We start by enabling garbage collection and defining a class myObject, which has a constructor underscore underscore unit to initialize the object and a destructor underscore 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 del to print a message when the object is destroyed. Two instances of myObject obj1 and obj2 are created. A circular reference is introduced by assigning obj1.other obj2 and obj2.other obj1, meaning both objects reference each other. Even when the external references obj1 and obj2 are deleted, the objects themselves are not immediately destroyed because they are still referenced by each other. To break this circular reference and allow Python to reclaim the memory, we manually trigger the garbage collector using d.collect. This forces Python to inspect the object graph, detect the circular references, and clean up the objects that are no longer accessible. Once the garbage collector runs, the destructors of both objects are called, indicating that the objects have been destroyed and their memory has been freed. The final message garbage collection complete confirms that the garbage collection process has successfully finished. This example illustrates the importance of understanding how Python manages memory and the role of garbage collection in handling complex situations like circular references. By using the GIS module, developers can control memory management more explicitly, ensuring that resources are properly freed even in tricky scenarios. Question 64. What is memoization in Python? Memoization in Python is a way to optimize functions by storing the results of expensive computations and using them when the same inputs appear again. Instead of recalculating the result every time, the function retrieves the previously computed result from a cache, saving time and resources. This technique is especially helpful in recursive functions or dynamic programming problems where the same calculations are done multiple times. By catching these results, memoization speeds up the overall process and makes the function more efficient. Key characteristics of memoization. Memoization is a technique that caches the results of function calls in a dictionary using the function's arguments as keys and the computed results as values. By storing these results, memoization helps avoid repeated calculations by returning cache values for the same inputs, which significantly improves performance. It is often used in dynamic programming to optimize solving overlapping subproblems, like in the Fibonacci sequence where the same calculations are performed multiple times. This approach enhances efficiency and reduces the time complexity of certain algorithms. Syntax of memoization. In Python, you can easily implement memoization using the functools.drew underscore cache decorator, which helps speed up expensive function calls by caching the results. By adding a drew underscore cache to a function, Python automatically stores the results of previous calls and reuses them when the same arguments are passed again. This helps avoid recalculating the same saying multiple times. You can set maximize none to allow unlimited catching, ensuring all results are stored for future use, making your function more efficient without changing its logic. Practical implementation. In this example, we are using Python's row underscore cache decorator from the functools module to optimize the computation of Fibonacci numbers. The Fibonacci sequence is a classic problem that can be solved using recursion, but a naive recursive solution has poor performance due to repeated calculations of the same values. For example, in the basic recursive approach, Fibonacci n is called multiple times for the same n, leading to an exponential time complexity. To address this inefficiency, memoization is used, where previously computed values are stored and reused, avoiding redundant computations. The addRew underscore cache decorator automatically stores the results of function calls in memory, so when the function is called again with the same argument, it returns the cached result instead of recalculating it. In this case, the Fibonacci function benefits greatly from memoization because it reuses the results of previously computed Fibonacci numbers. The maxize none argument allows the cache to store an unlimited number of results, meaning there's no restriction on how many previous results can be reused. When we compute Fibonacci 10, the decorator caches all intermediate results from Fibonacci 0 to Fibonacci 10. When we later call Fibonacci 50, many of the Fibonacci numbers from Fibonacci 0 to Fibonacci 10 are already cached, allowing the function to skip recomputing them and speeding up the process dramatically. This reduces the time complexity from O to n exponential to On linear because each Fibonacci number is computed only once. In short, row underscore cache optimizes recursive algorithms like Fibonacci by catching and reusing previously computed results. This makes the function much more efficient, especially for larger input values, turning a potentially slow recursive function into a highly performant one. Question 65. How can you achieve multithreading in Python? In Python, multithreading can be achieved by using the threading module, which enables multiple threads to run concurrently within a program. This is particularly useful for I/O bound tasks, such as reading from files or making network requests, where one thread can continue executing while another is waiting. Threads share the same memory space, making them lightweight compared to creating new processes. By using multithreading, Python can handle tasks more efficiently, especially when there is a lot of waiting time involved, allowing programs to perform faster in specific scenarios. Steps to achieve multithreading. To achieve multithreading in Python, start by importing the threading module, which provides the necessary tools to manage thread. Then, create a thread either by passing a function to a thread object or by creating a class that inherits from threading. Thread and overriding the run method. Once your thread is ready, start it using the start method, which will initiate its execution. Finally, use the join method to ensure the main program waits for the thread to finish before proceeding, ensuring proper synchronization in your program. Key functions in threading module. The threading module in Python provides essential functions to manage threads. The thread function allows you to create a new thread, which is like a separate path of execution in your program. Once a thread is created, use start to begin its execution, allowing the thread to run in the background. If you need to ensure that one thread completes before the next one starts, you can use the join function, which blocks the calling thread until the join thread issues its task. To avoid race conditions where two threads try to access shared resources simultaneously, Python offers lock and unlock. These are used to synchronize threads, ensuring only one thread can access a resource at a time. Practical implementation. In this example, we explore the concept of multi-threading in Python using the threading module, which enables concurrent execution of code. The program defines a function print underscore numbers that prints numbers from 0 to 4, pausing for 1 second between each print statement, simulate a team statement to zoom in task. This function is designed to be executed by multiple threads simultaneously. Two thread objects, thread 1 and thread 2, are created, both set to run the print underscore numbers function. When the start method is called on each thread, the Python interpreter begins executing these threads concurrently. This means that while one thread is printing a number and sleeping for 1 second, the other thread can also be performing the same actions. The precise order in which numbers are printed can vary due to the nature of thread scheduling, which is managed by the operating system. The use of thread 1.join and thread 2.join ensures that the main program waits for both threads to finish their execution before proceeding to the next line of code. This is crucial in multi-thread programs to main synchronization. Without calling join, the main program could terminate before the threads have completed their tasks, leading to incomplete output or inconsistent states. This example demonstrates the efficiency of multithreading for tasks that can run independently and in parallel, such as printing numbers with a delay. It effectively showcases how Python handles concurrent execution, making it a powerful tool for improving performance in applications that require simultaneous operations, such as web servers or data processing pipelines. Overall, this code serves as a basic introduction to threading, illustrating both its capabilities and the need for careful management of concurrent operations. Question 66. How does Python implement multiprocessing? Python implements multiprocessing by creating multiple processes that run concurrently, each with its own memory space. This approach enables true parallelism, which is especially beneficial for CPU-bound tasks. The multiprocessing module allows you to spawn separate processes, effectively bypassing the global interpreter log guiltel. As a result, CPU-bound tasks like heavy computations can run in parallel, enhancing performance. Each process operates independently, which means that memory and resources are not shared between them. This isolation is useful for applications that require significant processing power, making Python's multiprocessing a powerful tool for efficient execution. Key features. Each process in this model operates with its own independent memory space. This design prevents issues related to shared state, ensuring that processes do not interfere with each other's data. It's especially suitable for CPU-bound tasks, making it ideal for computationally intensive operations that can leverage parallelism effectively. This approach allows for true parallelism as it bypasses the global interpreter lock-GIL. As a result, multiple processes can run simultaneously on different CPU cores, maximizing resource utilization and enhancing performance. Practical implementation. This code demonstrates the use of Python's multipasses module to perform parallel computation by squaring a list of numbers. The primary benefit of using the multiprocessing module is its ability to bypass the global interpreter lock GIL, allowing CPU-bound tasks to run simultaneously across multiple CPU cores, thereby enhancing performance for compute-intensive applications. The program defines a function square underscore number n which takes a number as input and returns a square. The if underscore underscore name underscore main guard ensures that the subsequent code block runs only when the script is executed directly, preventing unintended behavior when the module is imported elsewhere, especially on Windows systems where it helps avoid recursive process spawning. A list of numbers from 1 to 5 is defined. A process pool is created with multiprocessing.pool, 2 indicating that two worker processes will be used for executing tasks concurrently. This is an efficient way to manage multiple processes as the pool handles the allocation of tasks to the available workers. The pool.map method is employed to distribute the task of squaring each number in the list to the worker processes. This function applies the square underscore number function to each element of the numbers list in parallel, allowing for simultaneous computation. Once all tasks are completed, the results are collected and returned as a list. Finally, the program prints the output which displays the squares of the numbers, confirming that the computations were carried out successfully. The expected output is 149, 16, 25. Overall, this example effectively illustrates the practicality of using the multiprocessing module for achieving parallelism in Python, enabling faster execution of time-consuming tasks by distributing the workload across multiple processes. Question 67. What is the underscore underscore name equal to underscore underscore main construct in Python? The underscore underscore name UL equal to underscore underscore main construct is a widely used Python idiom that helps control the flow of execution in your code. When a Python file is executed, the interpreter assigns the string underscore underscore main to the special variable underscore underscore underscore. This indicates that the file is being run directly as a script. If the file is imported into another module, the underscore underscore name scores variable will hold the name of the module instead. By using this construct, you can write code that only executes when the file is run directly, preventing it from running when the module is imported. This feature is particularly useful for organizing code and ensuring that certain parts are only executed in specific contexts. For example, you might have functions or classes defined in a file and you want to include some test code or main function that only when the script is executed directly. This helps keep your code modular and reusable, enhancing its overall functionality. How it works? It works. Every Python module has a special built-in attribute called underscore underscore name. When you run a Python file directly as a script, the value of underscore underscore name is set to underscore underscore main. However, if the file is imported as a module into another script, the value of underscore underscore name changes to the module's name, which is essentially the file name without the extension. The statement if underscore underscore name underscore 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 main is significant because it allows you to execute code only when the file is run directly. This means that any code within this block will not run if the module is imported elsewhere. This functionality is especially useful when you want to combine executable code with reusable functions or classes in the same script. It helps maintain clean code and promotes better organization within your Python projects. Practical implementation. This Python script my underscore script.py demonstrates a fundamental design pattern used in Python, the main guard. Script defines a simple function, greet, which when called prints a greeting message. The significance of the structure becomes evident with the inclusion of the conditional statement of underscore underscore name underscore 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 unnamed. This condition checks the context in which the script is executed. When the script is run directly, Python sets the special variable underscore underscore unnamed to underscore underscore unnamed, allowing the code within this block to execute. However, if the script is imported as a module in another Python file, the value of underscore underscore name will be the name of the script itself, preventing the block from executing. This behavior allows the script to contain both reusable functions and executable code without causing unintended execution when imported elsewhere. In this case, the print running the script directly statement serves as a clear indicator that the script is being executed in isolation, while the subsequent call to greet triggers the function to display its greeting message. This design pattern is crucial for creating modular and maintainable code in Python, facilitating the reuse of functions across multiple scripts while also allowing for testing and execution in a standalone manner. Overall, the structure exemplifies a common and effective approach to Python scripting, enhancing the flexibility and of the code. Question 68. How do you perform unit testing in Python? Unit testing is a vital practice in software development that focuses on verifying that individual units of code, such as functions or classes, behave as expected. In Python, you can utilize the built-in unit test module, which offers a comprehensive framework for creating and executing tests. To start, you define test cases by subclassing unittest.testCase, where you can specify methods to test your code. Each test method should start with the word test so that the test runner can recognize it. Within these methods, you can use various association methods such as assert equal, assert true, or assert traces to validate the outcomes of arrays. After reading your test cases, you can run them using the command line or directly within your IDE. The unit test framework provides clear output indicating which tests passed or failed along with any error messages. This systematic approach ensures that your code is robust and maintains its intended functionality as you make changes or add features. Key steps for unit testing in Python. To begin unit testing in Python, the first step is to import the unit test module. This module provides the necessary tools for creating and running tests. Next, You create a test class that inherits from unitest.testCase. This inheritance gives your test class access to various assertion methods that will be used to check conditions in your tests. Inside this test class, define your test methods. Each of these methods should start with the prefix test underscore so that the test runner can automatically recognize them as test cases. In these test methods, utilize assertions to verify that the output or behavior of your functions is correct. For example, you can use assert equal to check if two values are the same. Assert true to verify that a condition is true, and assert false to ensure a condition is false. Finally, to run the test, call the test runner using unitest.main. This will execute all the test methods in just manner and report of the response. Following these steps ensures a structured and effective approach to unit testing in Python. Practical implementation. The code provided defines a simple Python module named my underscore module.py that contains two functions, add and subtract. The primary purpose of this module is to encapsulate basic arithmetic operations, making it usable in other parts of a Python program or in different modules. The add function accepts two parameters, a and b, which are expected to be numeric values. It performs the addition operation and returns the sum. This function can handle integers and floats, providing flexibility in its usage. For example, calling add 23 would return 5, while add 2.5 3.5 would yield 6.0. Similarly, the subtract function takes two parameters, a and b, and returns the result of subtracting b from a. This function also operates on both integers and floats, allowing it to handle a variety of arithmetic scenarios. For instance, subtract 10.4 would return 6, whereas subtract 10.04.5 would return 5.5. Writing unit test classes. This code represents a basic unit testing setup in Python using the unit test framework specifically designed to test the functionalities of two arithmetic functions, add and subtract, defined in a separate module called my underscore module. The unit test framework is a built-in Python module that provides a structured way to create and run tests, ensuring that code behaves as expected. Test module class inherits from unitest.testCase, allowing to leverage assertion via ipathu provenistue. Inside this class, two methods test underscore add and test underscore subtract are defined to test the respective functions. The test underscore add method contains multiple assertions that verify the correctness of the add function with different sets of input values, such positive integers, negative integers, and zeros. Each assertion uses self data set equal to check if the actual output from that function matches the expected result. Similarly, test underscore subtract checks the subtract function against various tests to ensure it handles different scenarios correctly, such as subtracting negative numbers and zero. The use of descriptive names for the test methods helps convey the purpose of each test clearly, making it easier for developers to understand which aspects of the functionality are being verified. The final block, if underscore underscore name underscore main, allows the test to be executed when the script is run directly. Trigger on it is .main, which automatically finds and runs all test methods defined in the test module class. This organization facilitates efficient testing and debugging, enabling developers to quickly identify issues in their code by running automated tests. Overall, this setup serves a foundation for ensuring the reliability and correctness of the functions within my underscore module, highlighting the importance of unit testing in software development practices. Question 69. What is the difference between thread and process in Python's multiprocessing module? In Python, threads and processes are both used to achieve parallelism, but they differ in how they handle tasks and resources. A thread runs within the same memory space and shares data with other threads, making it lightweight but prone to race conditions. In contrast, a process runs in its own memory space, independent of others, which stores data but requires more resources. Threads are ideal for I/O bound tasks, while processes are better suited for CPU bound tasks due to Python to Python interpreter lock, GIL, which limits the performance of threads in CPU intensive tasks. Key differences between threads and processes. Threads and processes are two different ways to achieve multitasking in programming, each with distinct characteristics. Threads share the same memory space within a process, meaning they can easily communicate via shared variables, but they are limited by the global interpreter lock (GIL), which restricts true parallel execution for CPU-bound tasks. Threads are lightweight, consuming fewer resources, and are best suited for I/O-bound tasks like file I/O or network requests. On the other hand, processes have separate memory spaces. Memory require explicit inter-process communication. It sync like pipes or queues to share data. Processes are heavier in terms of resource consumption, but allow true parallelism since they are not affected by the GIL. This makes them ideal for CPU-bound tasks such as data processing and computation, where full parallel execution is required. Understanding these differences helps developers choose the right approach depending on the task's specific needs. Practical implementation. This Python code demonstrates the fundamental concepts of multithreading using the threading module, allowing a function to be executed concurrently in a separate thread. The code begins by importing the threading module, which provides the necessary classes and functions for thread creation and management. A function named print underscore numbers is defined to print the numbers from 0 to 4, with each number outputted in sequence when called. To initiate the multi-threading process, a thread object named teat is created using threading.thread, specifying print underscore numbers as the target function to run. This allows the thread to execute a defined function when it starts. The start method is called on the thread object t, which signals the Python interpreter to begin executing the print underscore numbers function in a separate thread. This allows the main program to remain responsive when operators independent occur concurrently. After starting the thread, the join method is invoked, which blocks the main thread's execution until 3 completes its task. This is crucial for synchronization, ensuring that the main program does not proceed to any subsequent code until the thread has finished printing the numbers. The combination of start and join allows for control execution of concurrent tasks, making it easier to handle scenarios where multiple operations need to run simultaneously operate interfering with each other. Overall, this example illustrates the basic use of multithreading in Python, highlighting how to create and manage threads effectively. It showcases the potential for concurrent execution, which can lead to more efficient and responsive applications, particularly when dealing with I/O bound or long running tasks. By understanding and utilizing these concepts, developers can build applications that leverage the power of parallelism, enhancing performance and user experience. Practical implementation for multiprocessing. This Python code snippet illustrates tools of the multiprocessing module tool to perform parallel executing a function in acceptable. The primary advantage of using the multiprocessing modulo over traditional threading is its ability to bypass the global interpreter lock (GIL), allowing true parallel execution of CPU-bound tasks. Script defines a function named print underscore numbers that iterates through a range of a. This function serves as the target for the process that will be created. To create a new process, an instance of multiprocessing, a process is instantiated with the target parameter set to the print underscore numbers function. This tells the multiprocessing framework which function to run in the new process. Once the process object is created, the start method is invoked on the process instance. This method initiates the execution of the print underscore numbers function in a separate process, allowing it to run concurrently with the main program. After starting the process, the join method is called, which ensures that the main program waits for the process to finish its execution before moving on. This is essential for maintaining synchronization in multiprocess applications, preventing the main program from terminating prematurely while the child process is still running. The use of multiprocessing is particularly beneficial for tasks that require intensive computations or that can be executed independently, as it can significantly enhance performance by utilizing multiple CPU cores. This example succinctly demonstrates the basic principles of creating and managing processes in Python, providing a foundation for building more complex applications that leverage parallelism to improve efficiency and responsiveness. Overall, it showcases how to effectively utilize the multipresence capabilities of Python to achieve concurrent execution of functions. Question 70. What is the global interpreter lock GIL in Python? The global interpreter lock kill is a mechanism in CPython that ensures only one thread executes Python code at a time, even in a multi-threaded. This lock is in place to make Python's memory management threads safe, preventing conflicts between threads. However, it also limits the performance of CPU-bound programs by allowing only one thread to run at once, which can be a bottleneck for applications requiring heavy computation. While this makes memory management safer, it can affect multi-threaded performance in CPU intensive tasks. Key points. The global interpreter lock GIL in Python ensures that only one thread executes Python bytecode at a time, limiting the performance of multi-threaded CPU-bound tasks. However, I/O-bound tasks like file handling or network operations are less impacted since these operations release the GIL, allowing other threads to run concurrently. For CPU-bound tasks, the GIL prevents true parallel execution, even on multi-core systems, which can hinder performance in multi-threaded scenarios. Some libraries such as SciJumpy can release the GIL during non-Python operations, boosting multi-threaded performance for heavy computations. Workarounds. When dealing with Python's global interpreter lock GIL, you can work out its limitations using multiprocessing, which creates separate steps, each with its own GIL, allowing true parallelism. Another approach is to use external libraries like NumPy or Number that release the GIL during CPU-bound tasks, enabling more efficient execution of computationally intensive operations. These workarounds help you bypass the GIL and make better use of multi-core processors. Practical implementation. This Python code demonstrates the creation of multiple threads to execute a CPU-bound task, specifically calculating Fibonacci numbers using the threading module. The primary function pp underscore task in calculates the nth Fibonacci number through iteration, a computation that requires significant CPU resources for large values of n. The code further defines a function run underscore threads which spawns multiple threads, each tasked with for performing this Fibonacci calculation concurrently. When running a CPU bound task like this, the expectation is often that multi-threading will speed up the process by distributing the workload across multiple threads. However, in Python, due to the global interpreter lock, GIL threads do not execute CPU-bound operations truly in parallel. The GIL ensures that only one thread executes Python bytecode at a time, meaning that even though multiple threads are created, they do not significantly improve performance for CPU-intensive tasks. As a result, the threads run sequentially at the Python bytecode level, which limits their effectiveness in tasks like Fibonacci, where the CPU is heavily engaged. In the run underscore threads function, multiple threads are created using the threading.thread class, and each thread is tasked with running the chew underscore betas function for a given number of iterations in. After starting all the threads, the join method ensures that the main program waits for each task to finish before calculating and printing the total time being taken for the task. The start underscore time is recorded before the threads begin, and the duration is calculated once all threads have completed execution. The key takeaway from this example is that while threads can be beneficial for I/O bound tasks, they are less effective for CPU-bound tasks in pipe due to the GIL. For true parallelism in CPU-bound operations, Python's multiprocessing module, which creates separate processes that run independently of the GIL, would be a better choice. This example serves as a demonstration of how threading works in Python and highlights the limitations imposed by the GIL in multi-threaded CPU-bound tasks. Question 71. What is a Python module and package? A Python module is essentially a single file containing Python code such as functions, variables, and classes that can be imported and used in other Python programs. It helps organize your code logically, making it easier to maintain and reuse. Any Python file with the .py extension qualifies as a module, and you can easily import it into your program using the import statement to access contents like functions or variables. This modular approach enhances code efficiency and readability across multiple projects. Practical implementation. This code defines a simple Python module named math_operations.py, which contains two basic arithmetic functions, add and subtract. These functions are designed to encapsulate two common mathematical operations, addition and subtraction, making them usable across different parts of a recursive. The add b function takes two parameters a and b representing numbers and returns the sum. This function is useful in a variety of situations where adding two numbers is required, whether they are integers, floating point numbers, or even other types that support the operator. Similarly, the subtract b function takes the same parameters but performs a subtraction operation, returning the result of subtracting b from a. This can be used to calculate differences between numbers in a wide range of contexts. By abstracting the operations into functions, the code allows for cleaner, more modular development. Instead of repeating addition or subtraction logic through a program, developers can simply call these functions when needed. Additionally, having these operations encapsulated in a module makes it easy to maintain and test a functionality in isolation. If future enhancements or changes are needed, they can be implemented in one place, the module, without affecting the rest of the codebase. This design pattern not only promotes usability and maintainability, but also helps keep the overall code structure clear of feedback. Use of Python module. This Python code demonstrates the process of inputting a custom module and utilizing its functions in a separate script. In this example, the custom module math_operations is imported, which contains the arithmetic functions of Once the module is imported, the script that uses the add function from math_operations to add two numbers 5 and 3. By calling math_operations dot add 5 3, the script passes the numbers as arguments to the add function, which calculates the sum and returns the result. The result of this operation 8 is stored in the variable result and related to the console using the print function. The comment output 8 confirms that the correct result is expected. This approach of breaking functionality into separate modules has several advantages. First, it allows for greater modularity in the code. Instead of having all the functions defined in a single file, the arithmetic functions are encapsulated within their own module, math_operations, which can be reused across different parts of the program or even in other projects. Second, it improves code readability and maintainability in organizing related functions logically in separate files, making it easier for developers to locate and modify them when needed. In summary, this code exemplifies how Python's import system allows the separation of functionality in different modules, promoting cleaner, reusable, and more organized Python package. Um, a Python package is a way to organize large codebases by grouping related modules into directories. Each package is essentially a directory that contains multiple modules along with a special file named _init_dot py. This file, even if empty, tells Python to treat the directory as a package, allowing to import modules from it easily. Packages help structure your code, making it more manageable and modular. The directory structure of a package allows related functionalities to be grouped together, improving code readability and reuse. In this package structure, my package acts as a collection of related modules aligned to organize your code for better maintainability. The underscore init.p file makes my package a Python package, enabling it to be imported and used in other parts of your application. Inside the package, you have two modules, math underscore operations.py, which likely contains functions related to mathematical calculations, and string underscore operations.py, which holds functions that work with string manipulation. This structure keeps your code modular and easy to navigate, making it simple to use specific functions from each module further without cluttering the main code base. This Python code demonstrates how to import a specific module from a custom package and use its functions. In this example, the math underscore operations module is part of a custom package named repackage. The import statement from repackage import math underscore operations allows us to access only the math underscore operations module from the package, which contains function prints like add and subtract. By importing just this module, we optimize the code by avoiding unnecessary imports, making it clear and efficient. After importing the module, the script calls the add function from math underscore operations, passing 5 and 3 as arguments. The function collects the sum of these two numbers and returns the result, which is tied as a in the variable result. Finally, the result it is printed to the console using print, demonstrating how the function works. This code structure highlights the importance of organizing code into packages and modules. By placing related functionality like arithmetic operations but in overlay within a package, we promote modularity where we promote modularity and reusability. This structure is particularly useful for larger projects where different modules or functions can be neatly separated into packages for easier maintenance and scalability. The use of custom packages and modules also makes the code more readable, allowing developers to quickly understand which functionalities are being used without reading the main script. Question 72. What are Python's built-in modules? OS module. One of Python's built-in modules is the OS module, which runs functions for interacting with the operating system. It allows Python programs to perform various system-level tasks like creating, removing, and modifying fields and directories, as well as interacting with the environment variable. For example, the os.lister function retrieves the list of files and directories in a specified path, making it easy to explore file systems programmatically. The module also provides methods to execute shell commands, manage fileFs with os.path, and even get detailed information about system processes. With this extensive set of tools, the OS module enables Python developers to build cross-platform applications that interact directly with the underlying operating system, simplifying tasks that otherwise require manual command line interaction. Regular expressions. The re module is used for working with regular expressions, which are patterns for matching text within strings. It provides functions like re.search to find matches, re.match to match patterns at the start of a string, and r.sub to replace occurrences of a pattern with another string. Regular expressions are highly useful for validating, extracting, and manipulating mass strings based on complex patterns. JSON JavaScript object notation. The JSON module provides functions to parse JSON, JavaScript, or distance data and convert it into Python like dictionary. Using JSON.loads, it also allows converting Python objects into Gen format using Gen.dooms. This module is especially important for web and API development, where Gen is often the standard format for data exchange. Time-related functions. The time module offers functions to work with time-related tasks in Python. For example, time.sleep can pause the execution of the program for a specified number of seconds, and time.time returns the current time in seconds since the epoch, usually January 1st, 1970. is useful for measuring performance, implementing delays, or working with timestamps. Functools, higher order functions. The functools module provides higher order functions that operate on other functions. A notable example is functools.true underscore catch, which catch the results of function calls to improve performance by avoiding repeated computations. Another example is functools.reduce, which applies a function cumulatively to the items of an iterable, reducing it to a single value. Collections, specialized data structures. The collections module provides specialized container data types beyond the built-in types like lists and dictionaries. Examples include counter for counting hashable objects, decay, fast and flexible, double-ended queue, and OE. These data structures can be more efficient or convenient than the basic data types in specific use cases. Iter tools, efficient iterators. The iter-tools module contains functions for efficient looping, especially for creating iterators that work on sequences of data. Functions like iter-tools.permutations, iter-tools.combinations, and iter-tools.chain allow for advanced iteration techniques. This module is particularly useful for working with large data sets, enabling memory efficient algorithms for handling combinations, permutations, and Cartesian products, socket networking, and communication. The socket module enables networking and communication between computers by providing low-level network interfaces. It allows Python programs to create and connect to network sockets, which facilitate communication over TCP, UDP, and other protocols. Functions like socket.connect and socket.send allow programs to send and receive data across networks, making it crucial for network programming, web servers, and distributed systems. Logging, and monitoring. The logging mode offers a flexible system for emitting log messages from Python programs. Developers can create logs for debugging or monitoring purposes using logging.backend to configure the logging ecosystem. With levels like debug info, warning, error, and critical, developers can control the granularity and importance of the messages. The logging module is essential for keeping track of events during execution, making debugging and performance monitoring easier. Subprocess, process creation and management. The subprocess module allows Python programs to run new processes and connect to see input, output, and error streams. It is a more powerful and flexible replacement for older modules like os.system. For example, subprocess.run can be used to execute shell commands and interact with other programs directly from within a Python script, enabling the integration of external processes into Python workflows. Threading, multithreading. The threading module provides the ability to run multiple threads concurrently within a program. Functions like threading.thread allow the creation of new threads which can execute tasks simultaneously. This is particularly useful for I/O bound tasks like file reading or web requests, where you want to keep the program responsive while waiting for external resources. Unit test testing framework. The unit test module provides a testing framework for writing and running tests in Python. It supports test automation, aggregation of tests into collections, and independent tests for checking specific pieces of code. With Unitest, you can define test cases using test case classes, which provide methods like a true, and others to check whether your code is working as expected. It's a crucial tool for maintaining code quality through automated testing. Multiprocess parallel processing. The multiprocessing module allows the creation and management of processes, enabling Python programs to perform tasks in parallel. Unlike threading, which is limited by the global interpreter lock, GIL multiprocessing creates separate memory spaces for each process, allowing true parallelism. With functions like multiprocessing.pool, developers can distribute tasks across multiple processors, improving performance in CPU-bound tasks. Its built-in modules provide essential tools and functionality that cover a wide range of programming needs, from system-level operations to advanced data structures, networking, and parallel processing. Question 73. How do you use the OS and sys modules in Python? 1. OS module. The OS module in Python is a powerful tool for interacting with the underlying operating system. It provides us a wide range of functions that enable Python programs to perform system level tasks such as handling file and directory operations, interacting with environment variables, and executing system commands. For example, you can use os.list here to list files and directories in a specified path, os.remove to delete files, and os.mintier to create directories. Practical implementation. This code demonstrates how to effectively use Python's OS module to interact with the operating system for file and directory. But those module provides several useful functions that allow you to perform common system level tasks such as retrieving the current working directory, creating and removing directories, deleting files, and handling file paths in a cross-platform way. For example, the os.getQuad function returns the current working directory where the script is executed, which can help understand the context in which the script is running. So s.lister lists all files and directories in the current directory or a specified path, enabling file and directory inspection. You can also create directories using os.mindir and delete files with oss.remove. In the case of removing directories, os.render ensures that empty directories can be removed safely. The os.path.join function is particularly useful because it allows you to create file paths that are compatible with different operating systems. This ensures that your script will work consistently on both Unix-based systems and Windows by using the appropriate file separator file a separator for a system. Lastly, os.environment provides access to environment variables such as user's home directory, home on Unix-like systems, which can be useful for configuring scripts based on the environment they run in. By using these functions, developers can write platform-independent code that seamlessly interacts with the file system and environment variables, making it easier to manage files and directories, handle paths, and integrate with system-level configurations. We makes the OS module a vital tool for system administrators and developers alike who need to build robust, adaptable Python scripts to sys module. The sys module in Python provides the essential functions and variables that interact directly with the Python interpreter, enabling developers to control and manage various aspects of the runtime environment. It allows you to handle command line arguments passed to the script using size.rb, providing a way to input data when launching the program. Additionally, the sys.path variable manages the Python module search path, allowing to modify where Python looks for modules, which can be useful when importing custom modules from non-standard directories. The module also provides functions like size.exit to terminate a program and sys.getSizer to check the memory size of objects. By interacting with the interpreter, sys allows you to fine-tune the runtime environment, handle errors and exceptions, and access to specific information, making it a crucial module's cache practical implementation. This code demonstrates the powerful features of the sys module, which allows Python programs to interact with the Python interpreter and the system level tasks. One of the key features of the sys module is sys.arg, a list that stores the command line arguments passed to the script. This is useful for providing input directly to the script when executed from the command line, allowing for dynamic behavior based on the provided arguments. The sys.exit function is used to terminate the Python script, either indicating successful execution with the status of 0 or an error with an non-zero status. This is helpful for exiting the program gracefully or in response to an error condition. The sys.version function returns the Python version being used, which is important for compatibility checks, especially in environments where multiple Python versions might be installed. It provides detailed information about the Python version, built-in and compiler. sys.path is a list that contains the directories Python CS runs when importing modules. By printing or modifying this list, You can control where Python looks for modules, making it easier to include custom modules to libraries that aren't in the standard directories. Finally, sys.stud and sys.star manage the output streams for standard output and error messages respectively, while print automatically sends output to sys.stud. You can use sys.stud.write and sys.star.write to direct specific messages to the appropriate streams. So the extra treat is particularly useful for logging errors and separating normal output from error reporting. Overall, the sys module provides fine-grained control over how your Python program interacts with the interpreter, handles input and output, and manages runtime configuration. Cognizant a crucial tool for system-level programming. Yet, question 74: how does Python handle recursion? Recursion in Python allows a function to call itself to break down a problem into smaller manageable subproblems. Each recursive call processes a smaller part of the problem until a base condition is met, stops the recursion. Python handles recursion by maintaining a stack of function calls with each new call being added to the stack. Once the base case is reached, the stack unwinds, returning results from each call step by testing. However, Python has a recursion depth limit to prevent infinite recursions, ensuring the process doesn't overwhelm system resources. Key aspects of recursion in Python. In Python, recursion is a technique where a function calls itself to solve smaller instances of the same problem. The base case is the condition that stops the recursion, preventing it from running endlessly and causing an error. Without this, the function would continue indefinitely. The recursive case is where the function breaks the problem down into simpler parts, calling itself with a smaller input to what toward the base case. Each recursive call brings the function closer to completing the problem in steps, ensuring the recursion eventually ends. Practical implementation. This code demonstrates the concept of recursion by calculating the factorial of a given number using a recursive function. A factorial of a number n denoted as n is the product of all positive integers from 1 to n. For instance, 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 120. In this implementation, the factorial nan function uses a base case and a recursive case to break down the problem. The base case ensures that when the input is 0 or 1, the function simply returns 1 since both 0 and 1 are defined as 1. This base case is crucial because it prevents the function from calling itself indefinitely, which would lead to a stack overflow. The recursive case handles the main calculation by calling the function with a smaller argument n1 and multiplying the result by n. This creates a chain of function calls that progressively breaks the problem down into smaller parts until it reaches the base case. Once the base case is hit, the recursion unwinds and each function call returns a vertex which is multiplied to get the final result. Question 75: how do we work with giant data in Python? In Python, working with giant data is made easy with the built-in JSON module. You can use it to parse JSON data from a string or file and convert it into Python objects like dictionaries or lists. Similarly, you can take Python objects and convert them back into JSON format. This process is simple and allows seamless data exchange between Python programs and external systems such as APIs that rely on JSON. Key functions in the JSON module. The JSON module provides key functions for working with JSON data in Python. The JSON.loads function is used to parse a JSON string and convert it into a Python dictionary list depending on list structure. If you want to read a JSON file directly, the JSON.load function reads the file and parses its content into a Python dictionary or list. To convert a Python object like a dictionary or list into a JSON string, you can use JSON.do's. Finally, JSON.do allows you to write a Python object to and to see in JSON format, making it easy to store structured data. Practical implementation. Practical. This code demonstrates the essential operations for working with Gene JavaScript object notation. Data in Python is in the JSON module, which allows seamless conversion between JSON strings and objects like dictionaries. JSON is a popular data format used for exchanging data between a server and a web application, and it is widely used in APIs. First, the JSON.loads function is used to convert a JSON encoded string into a Python dictionary. This is helpful when you receive data in JSON format, such as from a web API, and need to manipulate or analyze it in Python. Next, the code demonstrates how to write this Python dictionary to a file in JSON format using JSON.do. This process allows you to save structured data in a human readable format, making it easy to store and retrieve later. For example, writing to data.json saves the dictionary into a JSON file that can be used by other systems or applications. After that, the JSON.load function reads the JSON data from the file and converts it back into a Python dictionary. This is useful when you need to read and work with the data stored in a JSON file, such as configuration settings, API responses, or structured data records. Finally, John.dumps converts the Python dictionary back into a JSON unformatted string. This function is often used when you need to transmit Python over the web, store it in a database, or prepare it for API requests. This conversion makes it possible to move data between different systems that communicate using JSON. Overall, the code illustrates how to handle the full cycle of JSON data processing, converting JSON strings to Python objects, writing them to files, reading from files, and converting back to JSON format. The JSON module simplifies the process of serializing and deserializing data between JSON and Python, making it a fundamental tool for handling data in web applications, APIs, and data exchange formats. Question 76. How do you manage Python dependencies with requirements.txt? A requirements.txt file is a simple text document that lists all the libraries and specific versions your Python project relies on. It ensures consistency across different environments, so whether someone is developing, testing, or deploying your project, they're using the same versions of all dependencies. By running pip install requirements.txt, the exact package versions are installed, preventing compatibility issues and making project setup smoother for everyone involved. Key features of requirements.txt. The requirements.txt file is a crucial component for managing dependencies in Python projects. It contains a list of required packages and their versions, allowing you to control exactly which versions of each package are installed. By specifying versions, you ensure consistency across different environments, making it easier to reproduce results and avoid unexpected issues due to changes in package version. This file simplifies setting up the project back by automating the installation of dependencies with just a single command. Common comments with requirements.txt. To create a requirements.txt file, simply run pip freeze requirements.txt, which lists all the packages installed in your current environment. This file is helpful when sharing your project, ensuring others can install the same dependencies. To install these dependencies, just use pip install requirements.txt, which will install all the packages listed in the file, making it easy to set up the environment for your project. Question 77. What is the difference between synchronous and asynchronous programming in Python? In synchronous programming, tasks are executed one at a time in a strictly sequential manner. Each task must complete before the next one begins, creating a linear flow of operations. This is the simplest form of execution where one action leads directly to the next. In contrast, asynchronous programming allows tasks to be executed concurrently, meaning multiple tasks can be in progress simultaneously. Asynchronous code doesn't wait for one task to finish before starting another, making it more stable and capable of handling tasks that may take a bit longer to complete. Synchronous programming is inherently blocking, meaning each operation must fully complete before moving on to the next. Can be inefficient, especially for tasks that involve waiting, such as word calls or reading from files. On the other hand, asynchronous programming is non-blocking, allowing the program to continue executing other tasks while waiting for time-consuming operations to complete. This results in better performance, especially in scenarios where multiple I/O-bound tasks need to be handled concurrently. In synchronous programming, tasks are executed in a sequential manner following the traditional function call structure. Asynchronous programming, however, introduces the use of async and await keywords to define tasks that may time to complete and enable concurrency. These keywords allow the program to manage multiple tasks effectively without having to wait for each one to finish before proceeding. Synchronous programming can be less efficient for I/O bound operations such as reading from files or making network requests because the program spends time waiting for these tasks to complete. By contrast, asynchronous programming is more efficient for such tasks as it can handle multiple operations at once, reducing wait time. This makes asynchronous programming ideal for I/O heavy applications like web servers or APIs. The use case for synchronous programming is best suited to CPU bound tasks where computations are done sequentially without involving much waiting time. On the other hand, asynchronous programming excels in I/O bound tasks like network communication, interacting with APIs, or file system operations, where multiple tasks can be handled at once. In synchronous programming, regular functions and loops are used without any special constructs, whereas asynchronous programming requires async functions and the white keyword to manage tasks. Additionally, synchronous programming does not require specific libraries. So while asynchronous programming relies on libraries like Essentio, IOP, or functions like the Fruit or Psych Jotran to manage synchronous tasks efficiently. Thus, while synchronous programming is easier to write and understand, and the synchronous programming provides graphic flexibility and performance for applications with multiple concurrencies with multiple concurrent tasks. Practical implementation for synchronous programming. This code demonstrates a typical example of synchronous programming where tasks are executed sequentially one after the other. The task function is defined to simulate a blocking operation such as file read or network request using time.sleep to introduce a that mimics its world task taking time to complete. In this case, each task waits for 2 seconds before finishing. When the code is executed, task 1 starts and the program pauses for 2 seconds before completing the task. Only after one finishes does task 2 begin, followed by another 2-second wait, and then finally task 3 continues waits for another 2 seconds. This behavior represents a blocking or sequential execution where each task must complete fully before the next one begins. This approach works well for simpler cases but can become inefficient in scenarios where tasks involve waiting, such as I/O bound operations, e.g., reading from a file or waiting for a network response. In such cases, the program sits idle while waiting for the task to complete, wasting time that could be spent executing other tasks concurrently. For tasks that involve a lot of waiting, asynchronous programming would be a more efficient approach that allows multiple tasks to progress simultaneously without waiting for each one to wait. Practical implementation for asynchronous programming. This code demonstrates the power of asynchronous programming in Python using the Asyncio module. Unlike the earlier synchronous example where tasks were executed one after the other, here the tasks run concurrently. The async underscore task function is an asynchronous coroutine that seeks the ASCII task using await asyncio dot sleep to introduce a non-blocking delay. By using await, the code allows other tasks to run while waiting, making it more efficient for handling multiple tasks simultaneously. The main function coordinates the execution of these tasks using asyncio.gather, which runs the task concurrently. In this example, all three tasks, task 1, task 2, and task 3 start at the same time and wait for 2 seconds simultaneously. Once the wait period is over, all tasks are finished together. This is in stark contrast to synchronous programming, where each task would have to wait for the previous one to complete, resulting in a total of 6 seconds for all three tasks. Here, with a synchronous execution, all tasks complete in just 2 seconds, showing the efficiency of non-blocking I/O operations. By running tasks concurrently, asynchronous programming improves performance, especially in I/O bound tasks such as waiting for network responses, file reading, or sleeping for a specified time. In this case, the use of async and await enables efficient multitasking, allowing Python to handle several operations at once without blocking the execution of other tasks. This example highlights the key advantage of asynchronous programming, maximizing efficiency when deal with operations that involve waiting without having to wait for each task to finish sequentially. Question 78. What is the purpose of async and await in Python? In Python, async and await are key components of asynchronous programming, allowing for efficient management of tasks that involve waiting, such as network requests or file IOI. The async keyword is used to define an asynchronous function or coroutine which can be paused and resumed. When you declare a function with async, it doesn't execute immediately upon being called. Instead, it returns a coroutine object that needs to be awaited for execution to proceed. This allows Python to handle other tasks while waiting for the coroutine to complete, leading to more efficient use of time, especially in IO bound or network bound operations. The await keyword is used within an async function to pause its execution at specific points, waiting for a non-blocking operation to complete. When the operation, such as file read or network request, is done, the function resumes from where it left off. This mechanism enables the program to run multiple tasks concurrently without blocking the entire process. For instance, in an IO bound operation, await can pause the function, allowing other tasks to run concurrently until the awaited task completes, thus improving overall program efficiency. In summary, async allows the definition of asynchronous functions while await pauses their execution to wait for non-blocking operations, enabling Python to handle tasks concurrently and maximize performance in IO-heavy or network-dependent applications. Practical implementation. This code illustrates the use of asynchronous programming in Python with the help of the async module. Unlike traditional synchronous programming where tasks are executed one after the other, this code allows multiple tasks to run concurrently, making it more efficient for scenarios that involve waiting, such as networks or time delays. In this example, the async underscore task function is an asynchronous coroutine, which means it can be paused and resumed. Inside this function, the await asyncio.sleep calls simulates a non-blocking delay, meaning the program doesn't freeze while waiting for the task to complete. Instead, it allows other tasks to run simultaneously. When async underscore task is called, the task start and immediately go into their respective delays without waiting for one another to finish. The main function orchestrates the concurrent execution of the tasks using asyncio.gather, which collects all the tasks and runs them in parallel. In this case, task 1, task 2, and task 3 all start at the same time and each waits for 2 seconds. Thanks to the non-blocking nature of asynchronous finish functions, all 3 tasks complete after the same 2 seconds rather than waiting for each one to finish before the next one starts. Finally, asyncio.run main kicks off the asynchronous event loop, which schedules and executes the tasks. This method ensures that the asynchronous tasks are managed and executed correctly, making it the ideal entry point for running asynchronous programs workflow. Overall, this code highlights how asynchronous programming improves performance when managing tasks that involve waiting, allowing them to run concurrently rather than sequentially. By using async await and essential, the program handles multiple tasks efficiently, reducing the total wait time and maximizing resource utilization. Question 79. How does Python's logging module work? Python's logging module provides a flexible system for tracking events and program execution. It allows you to log messages at different severity levels like debug info, warning, error, and critical, and output these logs to various destinations such as the console, files, or even external services. Instead of relying on print statements, logging gives you more control and structure over how messages are recorded and reported. You can customize the format, level, and handlers for different logs, making it easy to track issues or monitor the program's behavior in a more organized way. Key components of Python's logging module. In Python's logging module, a logger is used to generate log messages, and you create it with logging.getLogger. This logger then lets you log various messages like info, warnings, or errors. Handlers control where these log messages go, such as to the console using stream handler or to a file with file handler. Formatters define how the log messages will look, letting you include things like timestamp like timestamps or log levels using logging.formatter. Lastly, log levels indicate the severity of the logs, ranging from debug for detailed information up to critical for serious errors that may cause the program to crash. Practical implementation. This code demonstrates how to configure and use Python's built-in logging module to record log messages into a file. Logging is a critical tool in software development that helps track events, errors, or debugging information. Instead of using print statements, which are not suitable for production environments, the logging module is a more flexible way to record what's happening in an application. In this code, logging.basicconfig is used to set up the logging configuration. The filename app.log argument specifies that log messages will be written to a file called app.log. The level logging.debug setting means that all log messages with a severity level of debug or higher info warning error critical will be recorded. The format argument defines how each log message will look. It includes the timestamp, the log level such as debug or error, and the message itself. Once logging is configured, logging.debug and logging.error are used to log messages at different levels. The debug message is a lower priority message meant for detailed diagnostic information, while the error message indicates a significant problem in the application. Both messages are written to the app.file along with their respective timestamps and severity levels. This approach provides a robust way to track the behavior of an application over time, particularly for troubleshooting issues without cluttering the console in issues. Log files can be reviewed later to understand how the program was executed, identify problems, or monitor critical events. Question 80. Difference between error and warning Python. In Python, errors and warnings indicate potential issues, but they differ in their impact on the program. An error signals a critical issue that stops the execution of the program immediately, requiring you to fix it before proceeding. On the other hand, a warning alerts you to something that might cause problems later, but it doesn't stop the program from running. Warnings allow the program to continue executing while giving you a chance to address the potential issue. This distinction helps developers catch non-critical problems without disrupting the overall flow of the code. In programming, errors and warnings serve different purposes, and it's essential to understand the distinction between the two. An error is a serious issue that occurs during the execution of a program, causing it to stop on its handle. For example, dividing by 010 raises a zero division error, which will terminate the program unless caught with the try except block. On the other hand, a warning alerts you to potential problems that might not immediately stop the program but could cause issues in the future. For instance, using deprecate code might trigger a deprecation warning, but the program will continue running. Errors are more critical and need immediate attention, while warnings are like cautionary messages important but not urgent. You can control or suppress warnings using the warnings module if needed, but they don't require instant handling like errors do. Understanding the difference helps maintain smooth program execution and prevents future problems. Practical implementation. This code demonstrates the concept of exception handling in Python using the try except block. In Python, errors and exceptions can occur during program execution, which, if left unhandled, can cause the program to crash. To prevent this, the try except mechanism is used to catch errors and handle them gracefully. In the try block, the code attempts to divide 1 by 0, which is mathematically undefined. In Python, attempting this operation raises the zero division error exception. When an exception is raised in the try block, instead of crashing the program, the execution is immediately transferred to the corresponding except block. In the except block, the code is prepared to catch the specific zero division error. The variable captures the error message associated with the exception, and in this case, it contains the message division by 0. The program then prints a custom error message using an F string which includes the error message. This allows the program to provide informative feedback about what went wrong without terminating unexpectedly. This approach ensures that the program can handle specific errors in a controlled manner, improving its robustness and user experience by avoiding unhandled crashes and allowing for proper error reporting. Practical implementation for warnings. This code illustrates how to use the warnings modules in Python to notify users or developers about deprecated functions or other non-critical issues. Deprecation warnings are often used in software development when a function, feature, or method is still functional but will be removed or replaced in future versions of the software. In the code, the old underscore function contains a warnings.warn call. This function issues a warning mission issues specifically a deprecation warning to indicate that the old underscore function is outdated. The Instead of stopping program execution, this warning is simply logged, allowing developers or users to know that they should avoid using this function and switch and find new alternative in the future. The warnings model is particularly useful because it doesn't disrupt the program flow like exceptions do. Instead, it gives developers a heads up that certain parts of the code may require attention without causing immediate errors. In larger codebases, this approach helps facilitate smoother transitions when making changes or improvements by ensuring backward compatibility for a period while encouraging migration to new branches. Question 81. How do you implement serialization and deserialization in Python, e.g. with Pickle? Serialization in Python can be easily done using the Pickle module, which allows you to convert Python objects into a byte stream, making it easy to store or transmit them. Deserialization, on the other hand, is the reverse process where the byte stream is converted back into a Python object. This is particularly useful when you want to save complex Python data types like lists, dictionaries, or custom classes. To serialize an object, use pickle.doom or pickle.doom dumps, and for deserialization, use pickle.load or pickle.loads. Summary of pickle functions. The pickle module is used to serialize and deserialize Python objects, making it easier to save, and load complex data structures. The pickle.dump obj file function serializes an object and writes it to a file, while pickle.load file reads the serialized object from a file and reconstructs it. If you need to work with byte streams instead of files, pickle.doom's object converts an object into a byte stream, and pickle.load's bytes turns a byte stream back into an object. This makes it easy to save, share, and reuse Python objects between different environments or sessions. Practical implementation. This code demonstrates how to use Python's pickle module for object serialization and deserialization. Serialization, also known as pickling in Python, is the process of converting a Python object into a byte stream so that it can be saved to a file or transmitted over a network. Deserialization or unpickling is the reverse process where the byte stream is converted back into a Python object. The code begins by creating a sample Python dictionary containing some key value pairs. It then performs the following operations. 1. Saving serializing the object to a file using pickle.do. The dictionary is serialized and written to a file named data.pickle in binary mode. This file can now be shared or stored for later use. 2. Loading deserializing the object from the file. The code then reads the file using pickle.load, which deserializes the data back into the original Python dictionary. This shows how data can be saved in one instance and reloaded in another, retaining the original structure and values. 3. Serializing to a byte stream. The code demonstrates an alternative approach by using pickle.dooms to serialize the Python object into a byte stream rather than saving it to a file. This is useful when you want to send serialized data across a network or save it in memory without writing to a file. 4. Deserializing from a byte stream. Finally, the byte stream is converted back into a Python object using pickle.loads, showing that the original structure and data can be fully restored from the byte stream. In summary, this code illustrates how the pickle module allows Python objects to be easily stored, shared, or transmitted in a serialized form and later read in their original state. This is particularly helpful for saving program states, sharing data between applications, or transmitting objects across networks. However, it is important to be cautious when loading pickle data from untrusted sources, as it can potentially execute arbitrary code. Question 82. How do you handle dates and times in Python using datetime? The datetime module in Python is a powerful tool for working with dates and times. It allows you to manipulate date-time objects, perform arithmetic with time intervals, and format or parse date-time strings with ease. To begin using it, simply import the module by typing import datetime. This gives you access to various functions and classes that help manage everything from basic date calculations to handling time zones. With datetime, easily create, compare, and manipulate dates and times in your Python programs. Practical implementation. This code provides a comprehensive example of working with Python's datatime module, which is essential for handling dates, time show times, and timestamps. First, the code shows how to retrieve the current date and time using datetime.now, which returns both the date and time, and date.today, which returns just the current date. This is useful when you need to lock timestamps or work with date specific logic in an application. It then demonstrates how to create specific date, time, or that type objects by specifying the year, month, day, and even the exact hour, minute, and second. This can be helpful for scheduling tasks or creating reminders. The string function allows for formatting a datetime object into a human readable string, giving you control over the display format. Conversely, structime converts a string representation of a date at time into a datetime object, which is useful when parsing input from users or external systems. Additionally, the code introduces time delta, which makes it easy to calculate future or past dates by adding or subtracting days, hours, or minutes from a given date. This is crucial for applications that need to work with date ranges or deadlines. Lastly, the code touches on handling time zone with timezone.apath. This is especially important in applications that operate across different time zones, such as web servers or WebP that synchronize data globally. By working with ATCAT Coordinated Universal Time, you can ensure consistent time management across geographic regions. Overall, the code covers a wide range of use cases for the datetime module, from simple date formatting to handling time differences and time zones, making it a powerful tool for date and time manipulation in Python. Question 83: how do you optimize the performance of a Python script? Optimizing a Python script is all about improving speed and reducing memory usage. You can start by choosing the right data structures, such as using list dictionaries or sets where appropriate, since these can have a significant impact on performance. Also, use efficient algorithms to reduce time complexity. Leveraging Python's built-in functions like map, filter, or list comprehensions can further speed up execution. Profiling your code using tools like Profile helps identify bottlenecks. Lastly, consider external libraries like NumPy for numerical operations or multiprocessing for parallel execution to enhance performance. Techniques for optimization. Optimization techniques in Python are essential for improving the efficiency and performance of code. One of the primary recommendations is to use built-in functions and libraries, as they are written in optimized C code, providing significant performance benefits. Avoiding global variables is another important practice, as using local variables or passing arguments directly is faster and avoids potent side effects. Utilizing list comprehensions offers a more concise and efficient way to create lists compared to traditional loops. For memory efficiency, generators are preferred when handling large datasets, as they generate values lazily and avoid holding the entire dataset in memory at once. When checking membership, using a set is far more efficient than using lists, as sets provide a one time complexity for membership tests. Profiling your code using tools like SetProfile or TimeIt helps identify bottlenecks, allowing you to focus optimization efforts where they are most needed. In CPU-bound tasks, leveraging multiprocessing can speed up execution by utilizing multiple CPU cores. Additionally, optimizing loops by avoiding unnecessary calculations inside them and moving invariants outside can lead to performance gains. Choosing efficient data structures such as dec, default dict, or counter can also greatly improve performance based on specific use cases. For numerical operations, NumPy is highly recommended due to its optimized performance for handling large arrays and matrices. When dealing with strings, avoiding string concatenation in loops and using dot join instead provides faster string concatenation. Finally, using a true underscore catch from the functools library allows you to catch results of expensive or repeated function calls, reducing redundant computations and improving efficiency. Each of these techniques plays a crucial role in optimizing Python code for faster and more efficient execution. Question 84: implementing a custom descriptor in Python. Descriptors in Python allow you to control how attributes are accessed, modified, or deleted in a class by defining special methods like underscore underscore get, underscore underscore set, and underscore underscore delete. These methods provide custom behavior for managing attribute access, making descriptors powerful tools for things like property management or creating usable functionality. Essentially, descriptors give you control over attribute handling in a flexible and efficient way, which is widely used in Python's internal workings, e.g., property class method, static method. Steps to implement a custom descriptor. To implement a custom descriptor, start by creating a descriptor class that defines the underscore underscore get underscore underscore set and optionally underscore underscore elite methods, which control how the attribute is accessed and modified. Next, use the descriptor in another class by setting it as an attribute, allowing the descriptor to manage the behavior of that attribute. This setup helps you control and customize how attributes are handled within your class in a flexible and reusable way. Practical implementation. This code demonstrates the use of a custom descriptor in Python. A descriptor is a class that defines how attributes of another class are accessed, modified, or deleted. In this example, the Celsius class is a descriptor that controls the behavior of the Celsius attribute in the temperature class. The Celsius class implements three special methods underscore underscore get, underscore underscore set, and underscore underscore delete. Underscore underscore get is called whenever the Celsius attribute is accessed, returning the current temperature value. Underscore underscore set is called when the Celsius attribute is assigned a new value, ensuring that the temperature doesn't drop below dash 273.15°C, which is absolute zero in Celsius. If an invalid value is provided, it raises a value error. Underscore underscore delete is called when the attribute is deleted. In this case, it prints a message and deletes the stored value from the descriptor. The temperature class uses the Celsius descriptor to manage its Celsius attribute. When an instance of temperature interacts with Celsius, the respective descriptor methods are invoked automatically. For example, when temp.celsius25 is executed, the underscore underscore set method is called to validate and store the value. Similarly, accessing temp.celsius triggers underscore underscore get and deleting the attribute with the temp.celsius calls the underscore underscore delete method. This pattern is useful for managing complex attribute behaviors such as validation or automated calculations in a clean and reusable way. The descriptor abstracts this logic, allowing the temperature class to focus solely on its business logic without big chat business. Question 85. How do you profile Python code for performance bottlenecks? Profiling Python code helps identify slow or inefficient parts, enabling you to optimize performance. Python provides tools like profile, timeout, and line underscore profiler to analyze code performance. Profile gives detailed reports of function call times, time it measures execution time of small code snippets, and line underscore profiler shows time spent on each line. By using these tools, you can pinpoint bottlenecks and make informed decisions about optimizing specific sections of your code for improved speed and efficiency. 1. Using profile for comprehensive profiling. This profile module in Python is a powerful tool for analyzing the performance of your code. It helps you understand how much time each function in your program takes to execute and how many times each function is called. By tracking these details, Profile provides insights into which parts of your code are slowing down the program, allowing you to identify bottlenecks. It's easy to use and gives a comprehensive overview of your program's performance, making it a valuable tool for optimizing and improving the efficiency of your Python code. Practical implementation. The code provided demonstrates how to use Python's built-in profile module to profile a function's performance. Profiling is the process of measuring the time taken by each function call in a program, which helps identify bottlenecks and optimize performance. In this case, the function slow underscore function performs a simple summation of numbers from 1 to 1 billion, making it a good candidate for profiling because it involves a large number of iterations. When the lines profile.run slow underscore function is executed, the profile module tracks the function call, counting the total number of calls, the time spent in each call, and any other function calls made during the execution of slow underscore function. The output is detailed performance data showing where most of the processing time is spent. This is particularly useful when optimizing code as it helps pinpoint specific functions or operations that slow down execution, enabling developers to focus their optimization efforts where it matters most. 2. Using timeit for small code snippets. The timeit module is a handy tool for timing how long small code snippets or functions take to execute. It allows you to measure the performance of your code by running it multiple times and calculating the average execution time. This is especially useful when optimizing functions or comparing different approaches to a problem, as it helps identify which method is faster in a clear and reliable way. Key features Key features include the ability to measure execution time for small code snippets or functions, providing quick insights into performance. You can run the code multiple times to get more accurate timing results, which is especially useful for identifying micro optimizations. This helps in refining code performance without altering the core logic. Practical implementation. This code demonstrates how to measure the performance of a function in Python using the timeit module. The function slow underscore function performs a simple task of summing numbers from 0 to 199,999, which simulates a computational task that can be time consuming when executed multiple times. The timeit function is then used to calculate how long it takes to run this function 100 times. The timeit method works by executing the code passed as a string multiple times, in this case 100 times, and it calculates the total time taken for those executions. The globals function is passed to timeit so that the slow underscore function defined in the global scope is accessible within the timeit context. After running the function 100 times, the total time is divided by 100 to get the average time per execution, which is then printed. This approach is commonly used to benchmark code and compare the performance of different implementations, especially when optimizing for speed or efficiency in Python. 3. Using line underscore profiler for line by line profiling. The line underscore profiler package helps you identify performance bottlenecks by profiling each line of code in your functions. It highlights which specific lines take the most time, allowing you to optimize your code effectively. This tool is especially useful for pinpointing slow or inefficient lines in large complex functions, making performance tuning more focused and accurate. By running line by line profiling, you can easily spot areas that need improvement without needing to refactor entire functions or modules. Key features. So, Key features of this tool include profiling the execution time for each line of code within a function, which helps in identifying bottlenecks in specific lines. It provides detailed reports showing the time spent on every line, making it easier to optimize performance where needed. This is especially useful for improving code efficiency in critical sections. Practical implementation. This code demonstrates the use of the line underscore profiler modules to perform line by line performance analysis of a Python function. The function slow underscore function is designed to simulate a time consuming task by summing numbers from 0 to 999,990. This is a typical example of a computationally intensive process which we want to optimize or understand in terms of performance. To analyze the performance, we use line profiler, a tool that measures the time taken by each line of code to execute. The profiler is first instantiated by creating an object profiler of line profiler. We then add the function we wish to profile using profiler.add underscore function, slow underscore function, which tells the profiler to collect data specifically for that function. The profiler is run using profiler.run slow underscore function, where the function call is passed as a string. This allows the profiler to execute the function while simultaneously recording the time taken for each line of the function. After the function completes, the results are printed using profiler.print underscore stats, which shows detailed statistics without how much time each line of slow underscore function took to execute. This line by line profiling is especially useful for identifying performance bottlenecks, as it pinpoints exactly which lines of code are responsible for slow execution, helping developers optimize those specific lines for better efficiency. By using such profiling tools, developers can systematically improve the performance of their code. Question 86. How do you implement caching in Python? Caching is a performance optimization technique where the results of expensive function calls are stored so they can be reused when same inputs occur, avoiding redundant computations. In Python, caching can be easily implemented using the built-in functools.ru underscore cache decorator, which caches function results based on input arguments. This is particularly useful when dealing with functions that are called frequently with the same parameters. Additionally, Python supports caching via external libraries like cache tools or Redis for more complex scenarios, offering flexibility in how and where data is cached. Techniques to implement caching. In Python, there are several techniques and tools for caching that help improve performance by storing the results of expensive or frequently called functions. Here's a breakdown of some common caching techniques. Um, 1. functools.lu underscore cache. This is a built-in caching decorator in Python that follows the least recently used LRU eviction policy. It caches the results of a function and stores them in memory so that subsequent calls with the same arguments return the cached results without recomputing them. It's simple to use and effective for function level caching, especially when you have computationally expensive functions or recursive calls, such as calculating Fibonacci numbers. To Cache Tools library, this external library offers more advanced caching options compared to ru underscore cache. It supports multiple eviction strategies like LRU least recently used, LIFO least frequently used, and TTL time to live. This allows you to fine-tune your caching strategy based on the application's needs, giving more control over how long items stay in cache and how they are evicted. 3. Workspace library commonly used in web development, particularly with Flask. The Workspace library provides a release for caching at the request link. It allows caching responses in memory or using external services like Memcached or Redis. This is particularly useful in web frameworks for catching HTTP responses or parts of the application that don't change frequently, reducing load on the server and improving response times. 4. Redis is a distributed in-memory key value stored commonly used as a caching mechanism in large-scale applications. It supports advanced caching features like data expiration, eviction policies, and persistence, making it suitable for both small scale and enterprise level caching needs. Redis can handle complex data structures and is often used for caching database query results, session data, and real time analytics. 5. Manual dictionary caching. The simplest form of caching involves using a Python dictionary to store computed results. This approach is easy to implement but lacks advanced features like automatic expiration or eviction of stale data. You would have to manually manage the cache size and decide when to clear or update trees, which can be less efficient for larger applications. Each of these techniques has its use case depending on the complexity of your application and the level of control you need over the caching process. Simple applications may benefit from rule underscore cache or manual dictionary caching, while larger systems may require Redis or cache tools for more advanced and distributed caching strategies. Practical implementation. This code demonstrates two different caching strategies in Python: fintools.ru underscore cache and cachetools.lu cache. Caching is a technique used to store the results of expensive function calls, allowing subsequent calls with the same inputs to return the cache results rather than recomputing them, improving performance. In the first example, the Fibonacci function is decorated with a lu underscore cache max size 100. The least recently used LRU cache mechanism stores up to 100 results of the Fibonacci sequence so that repeated calls to the function with the same argument reuse previously computed values. This approach is particularly beneficial for recursive functions like Fibonacci, where the same values are often recalculated many times. With caching, this redundancy is eliminated, leading to significant performance gains. In the second example, the square function uses cache tools with an explicit LRU cache. The @cache decorator is applied Specifying an LRU cache that is the results of the last 100 calls to the function. This allows the function to avoid recalculating square values that have already been computed, reducing the overall execution time when dealing with repeated or frequent calls. In both cases, the caches are limited to a maximum size of 100, meaning the oldest or least recently used results are discarded when the cache reaches capacity. This ensures that the cache remains memory efficient while still offering performance benefits by storing frequently used data. Question 87. How do you use Python's itertools library? The itertools library in Python is a powerful tool for creating efficient iterators designed to handle looping over large datasets without consuming excessive memory. It provides a range of functions that simplify complex iteration patterns such as combinations, permutations, product, and cycle. With itertools, you can chain, group, and filter data, making your code cleaner and more efficient when dealing with repetitive, large datasets or custom iteration logic. Is especially useful for working with large or infinite sequences, ensuring minimal memory usage and maximum performance. The itertools module in Python is a powerful tool for working with iterators and can handle various tasks efficiently. It provides infinite iterators which can generate values indefinitely, making it useful when you don't know how many values you need upfront. It also offers iterators that terminate based on the shortest input, generating sequences that stop when the shortest input is exhausted, which is great for tasks like pairing or combining lists. Finally, combinatoric generators allow you to easily create permutations, combinations, and product of iterables, making it perfect for solving problems that involve multiple possibilities or arrangements. Summary of common itertools functions with examples. The itertools module in Python provides a collection of fast, memory-efficient tools for working with iterators, allowing developers to efficiently loop through data. Each function in itertools is designed to simplify common iteration patterns. Here's a detailed explanation most commonly used functions. 1. itertools.count start step. This function generates an infinite sequence starting from start, with each subsequent value incremented by step. For instance, itertools.count 52 produces 579 and so on indefinitely, making it useful in scenarios where you need continuous counting without stopping. 2. itertools.cycle iterable. This function continuously loops through the elements of an iterable. For example, itertools.cycle ABC will yield ABC, then start over with A again indefinitely. 3. itertools.repeat object times. It repeats an object a specified number of times or indefinitely if times is not provided. For example, itertools.repeat 10 3 produces 3 instances of the number 10. 4. itertools.accumulate iterable. This function returns accumulate sums by default or results of other binary functions. For example, itertools.accumulate 1, 2, 3, 4 returns the cumulative sums 1, 3, 6, and 10. 5. itertools.chain iterables. It combines multiple iterables into a single iterator. For example, itertools.chain 1 to a b produces a combined iterator that yields 1, 2a and b. 6. itertools.compress data selectors. This filters elements from data based on the truth values in selectors. For example, itertools.compress ABC101 filters out B, resulting in a C. 7. itertools.product iterables. It computes the Cartesian product of input iterables, meaning every possible combination of elements. For instance, itertools.product 1 to AB returns 1A1, B2A, 2B. 8. itertools.permutations iterable. This function returns all possible permutations ordered arrangements of an iterable. For example, itertools.permutations 1 2 3 2 generates 1 2 1 3 2 1 2 3 3 1 3 2. 9. itertools.combinations iterable R. It returns combinations of length half from an iterable without repeating elements. For instance, itertools.combinations 1 2 3 2 gives 1 2 1 3 2 3. 10. Itertools dot combinations underscore with underscore replacement. This function works like combinations but allows repeater elements. For example, itertools dot combinations underscore with underscore replacement 122 produces 111222. 11. Itertools dot filter false predicate a iterable. It returns elements of an iterable for which the predicate is false. For instance, itertools dot filter false lambda x x percent 201 234 returns 13. 12. Itertools.takeWhile predicate iterable. This function returns elements from an iterable as long as the predicate is true. For example, itertools.takeWhile lambda xx3 1234 returns 12. 13. Itertools.dropWhile predicate iterable. It skips elements while the predicate is true and returns the remaining elements. For example, itertools.dropWhile lambda xx3 1234 drops 1 and 2, returning 3 4. These tools enable highly efficient iteration and manipulation of data, making them invaluable for handling complex iteration patterns in a memory conscious manner. Each function is designed to simplify specific tasks such as counting, filtering, combining, and manipulating data. Question 88. What are the best practices for structuring Python projects? So, when structuring a Python project, following best practices ensures your project remains organized, scalable, and easy to maintain. One of the foundational steps is to use a standard directory layout, organizing files into directories like my underscore project, tests, and setup.py, which provides clarity and helps others navigate the project. It's essential to create a virtual environment using tools like venv or virtualnem for revive dependencies, preventing conflicts with system-wide packages. Managing dependencies effectively is also crucial. Use a requirements.txt.pip field to keep track of packages used in the project, allowing for easy installation and consistent environments across different machines. To keep the codebase clean and maintainable, you should write modular code by organizing functionality into modules and packages, ensuring usability separation of concerns. Configuration details such as API keys or database credentials should not be hard-coded, but instead stored separately using environment variables or configuration files to avoid security risks and improve flexibility. Testing is equally important, and you should write tests by create spell both unit or reactive unit tests that ensure good functions as expected using frameworks like ptest or unitest. For ease of installation and distribution, it's a good practice to include a setup.p file which defines the project's metadata and dependencies. This helps in packaging your project for reuse or sharing with others. Comprehensive documentation should also be provided in a read.md explaining the purpose of the project, installation instructions, and usage examples, making it easier for new developers or collaborators to understand the project. Including a .file file ensures that unnecessary files like temporary logs or virtual environments are excluded for version control, keeping the repository clean. Version control with systems like Git is essential for tracking changes, collaborating with others, and maintaining a history of your project's development. Following PEP guidelines ensures your code is readable and adheres to Python standard practices, which improves collaboration and reduces technical debt. Tools like Flake 8 or Black can automate code style checks. Lastly, for repetitive tasks like running tests or setting up environments, consider using a Payfill or Tail task runners like Invite to automate flows and save time. By adhering to these best practices, you create a project structure that is efficient, scalable, and easy to maintain. Question 89. What are the best practices for structuring Python projects? In Python, you can easily read and write files using built-in functions. To work with a file, you first need to open it using the open function, which allows you to specify the mode like R for reading or W for writing. Once opened, you can read the file's contents using methods like read or readlines and write to the file using write or writelines. After you're done, it's important to close the file using the close method to ensure all changes are saved and resources are freed. Common file operations. When working with files in Python, there are several common operations you'll need to perform. First, opening a file is done using the open function where you specify the file name and mode such as read, R or write, W. To read the contents of file, you can use methods like read to get the whole file, readline for a single line or read lines to retrieve all lines as a read. For writing to a file, write is used to overwrite content if the file is opened in write mode. If you want to append data without overwriting existing content, the same write function is used, but the file must be opened in append mode by it. Finally, always remember to close the file with close to free up system resources and prevent potential issues. Practical implementation. Okay, this code demonstrates a simple example of both writing to and reading from a file in Python using the with statement. In step 1, the file example.txt is opened in write mode. If the file doesn't exist, it is created. If it already exists, its contents are cleared. The program then writes 2 lines of text into the file using the write method. After writing the content, the file is automatically closed when a with block ends, ensuring proper resource management. In step 2, the file is reopened, this time in read mode, or the content written earlier is then read using the read, missing the variable and stored in the variable content. Finally, the program prints the file's content to the console. By using with, the script ensures that the file is properly closed after each operation, which is a good practice for handling file I/O in Python. The code efficiently manages file access and helps avoid issues like resource leaks or file locks, making it more robust and easy to maintain. Question 90. Can you sort list using bubble sort? The bubble sort algorithm is a simple comparison-based sorting technique used to arrange elements in ascending order. In this practical example, the goal is to sort an array of integers using bubble sort. Here's how it works step by step. The function bubble underscore sort r takes an input array r and begins by determining its length n. The sorting process occurs by repeatedly traversing the array and comparing adjacent elements. The outer loop for in range, n controls the number of passes through the array, where each pass ensures that the largest unsorted element bubbles up to its correct position at the end of the array. Within the outer loop, the inner loop for j in range 0 ni1 is responsible for the comparison of adjacent elements. If an element is greater than the one next to it, they are swapped to maintain ascending order. This process is repeated until the array is fully sorted. As the larger elements gradually move to their final positions with each pass, the inner loop reduces the range it needs to compare ni1 as the last few elements are already sorted. At the end of the sorting process, the array 64, 34, 25, 12, 22, 11, 90 becomes 11, 12, 22, 25, 34, 64, 90, and this sorted array is printed as the output. Bubble sort is intuitive but not very efficient for large datasets due to its time complexity of ON2, where n is the number of elements in the array. Question 91. Can you provide an example of a stack implementation in Python? This code implements a basic stack data structure in Python using a class called stack. A stack follows the LIFO last in first out principle, meaning the last element added to the stack will be the first one removed. The class includes several methods to perform common stack operations. Underscore underscore init. This is the constructor method which initializes an empty list by a one dish inify to stock elements. To push item, this method adds an item to the top of the stack by appending it to the end of the list. 3 pop, this method removes and returns the top element from the stack, which is the last element added. If the stack is empty, it returns a message indicating that the stack is empty. 4p, this method allows viewing the top element of the stack without removing it. If the stack is empty, it returns a message saying the stack is empty. 5 is underscore empty. This method checks whether the stack is empty by verifying if the length of the list is 0. 6 size I, this method returns the total number of elements currently in the stack. The example usage demonstrates how to push elements onto the stack, peek at the top element, pop elements from the stack and check whether the stack is empty. For instance, when you push elements like 10, 20 and 30 onto the stack, the peek function will show that 30 is at the top, and calling pop will remove 30, then 20, and finally 10. Once all elements are popped, the stack becomes empty. Question 92. Can you provide an example implementation of a singly linked list in Python, including basic operations such as insertion, deletion, and traversal? This code demonstrates the basic functionality of a singly linked list in Python, showcasing how to manage nodes in a linear schema. The linked list is implemented with two main components, the node class and the linked@list class. The node class represents the building block of the linked list where each node holds two key attributes, the data that stores the value of the node, and next, which is a pointer to the subsequent node in the list. Initially, the next pointer is set to none, indicating that the node does not yet link to any other node. The linked list class is responsible for managing the overall structure of the list. It starts with an empty list, head is none, and various methods allow us to interact with the list. 1. Append method new node to the end of the list. If the list is empty, the new node becomes the head, otherwise the method bases to the last node and attaches the new node at the end. 2. Prepend method inserts a new node at the beginning of the list by making the new node the head and pointing it to the previous head node. 3. Delete underscore node method removes a node that matches a specified value. If the node to delete is the head pointer is updated. If the node is in the middle or end, the previous node's next pointer bypasses the deleted node, thus removing it from the chain. 4. Print underscore list method traverses the entire list, printing the data of each node secretly to visually see the current state of the linked list. The code demonstrates adding nodes both at beginning and the end, deleting nodes by value, and printing the list at various active array stages. It efficiently handles dynamic operations like insertion and deletion without the need for contiguous memory allocation, which is a key advantage of linked lists over arrays. However, traversal in a linked list is slower compared to arrays, as accessing an element requires sequential traversal from the head. Question 93. Can you provide a binary tree implementation in Python with insertion, traversal, and search operations? This code demonstrates the implementation of a binary tree data structure using two classes, Nodian and binary tree. The node class represents an individual node in the binary tree, with each node storing some data, a reference to the left child and a reference to the right child. The binary tree class manages the overall structure of the tree, including the root node operations such as insertion, traversal, and searching. When inserting a node, the insert method first checks if the root end is empty. If so, the new node becomes the root. Otherwise, the tree is traversed recursively underscore insert helper method to place the new node in its show position, left of the current node if its value is smaller, or right if it's larger. The code supports three types of traversals. 1. In order traversal, left, root, right. This traversal prints the values of the tree in sorted order. The left subtree is visited first, then the root node, followed by the right subtree. 2. Pre-order traversal, root, left, right. This traversal visits the root first, then the left subtree, and finally the right subtree. 3. Post-order traversal, left, right, root. In this method, the left subtree is visited first, followed by the right subtree and the root node row. The tree also has a search function that checks whether a specific value exists within the tree. This is done by recursively comparing the target value to the current node's value and traversing either left or right based on the comparison. The example usage demonstrates how the binary tree is constructed by inserting values and how traversals are used to print the values in different sequences. Additionally, the search method is used to find specific values in the tree, with the output indicating whether the value is present. Overall, this code provides a clear example of how binary trees work and how they can be traversed and searched effectively. Question 94. Write a Python program to implement a breadth first search beefs on a graph. In the above code, we are implementing the breadth first search BF's algorithm to traverse a graph, which is represented as an adjacency list. BFC is a graph traversal technique where we start from a selected node, in this case node A, and visit all its immediate neighbors first before moving on to their neighbors. It explores the graph level by level, which means it visits all nodes at a certain depth from the start node before going deeper. The adjacency list graph describes the connections between nodes where each key is a node and the value is a list of neighboring nodes. For instance, A is connected to B and C, B is connected to D and E, and so on. The beast function starts by initializing a set called visited to keep track of nodes that have been visited, ensuring each node is processed only once. It also uses a queue to manage the nodes to be processed in a first in, first out FIFO manner, which is key to ensuring beast explores nodes level by. In the base loop, we dequeue a node, print it, and mark it as visited. Then we examine its neighbor nodes connected to the current node look harem. This process continues until there are no more nodes left in the queue, ensuring all reachable nodes from the starting node have been explored. For example, when starting from A, beefs will first visit A, then B and C, its immediate neighbors, and then E and F, exploring each level of the graph before moving on to the next. This algorithm is efficient for finding the shortest path in an unweighted graph and is widely used in network analysis, web crawling, and other applications where complete traversal of a graph is required. Question 95. Write a Python program to implement a depth first search DFs on a graph. This code demonstrates the depth first search DFs algorithm, which is a graph traversal technique that explores a graph by visiting nodes as far as possible along each branch vector for backtracking. The graph is represented as an adjacency list where each in the dictionary represents a node and its values a list of neighboring nodes. This algorithm starts at a given node, in this case node A, and visits all nodes by recursively following each unvisited neighbor until no more neighbors are left to explore that path. The df function takes three arguments: the graph, the current node vertex being processed, and an optional set called visited that tracks which nodes have already been visited. If the visited set is not provided, it is initialized at the start of the function. For each node, the function prints the node, marks it as visited, and then recursively calls itself for each unvisited neighbor of the current node. This process continues until all nodes connected to the start node are explored. Webs is particularly useful when you want to explore all possible paths in a graph, as it dives deep into one branch before moving to others. It can be used for tasks such as finding connected components, pathfinding, and solving puzzles where exploration of all possible options is required. The key feature of Beefs is that it goes deep into the graph first, exploring the farthest nodes before backtracking to explore other potential paths. Question 96. Write a Python program to solve the Tower of Hanoi problem using recursion. The Tower of Hanoi problem is a classic algorithmic puzzle that demonstrates the power of recursion. The objective of the puzzle is to move a stack of disks from one peg source to another peg target using a third peg auxiliary as an intermediary. The constraints are that only one disk can be moved at a time and a larger disk cannot be placed on top of a small disk. In this recursive solution, the base case is when there is only one disk N1. In this case, the disk is simply moved from the source peg to the target peg. For more than one disk, the function works by first moving in one disk from the source peg to the auxiliary peg, freeing up the largest disk to be moved directly to the target peg. After that, the N1 disks are moved from the auxiliary peg to the target peg. This process is repeated recursively, breaking the problem into smaller subproblems until all the disks are successfully transferred to the target peg. The recursive nature of the algorithm makes it efficient for solving the problem, as it systematically handles each disk in the correct order without violating the puzzle's constraints. The example in the code solves the problem for three disks, showing step by step how the algorithm handles each disk movement, and it can easily be extended to any number of disks. Question 97. How do you use Python's concurrent.futures module? Python's concurrent.futures module makes it easy to run tasks in parallel by providing a high-level interface for executing code asynchronously using either threads or processes. This is especially useful when you have I/O bound tasks like reading files or making network requests or CPU bound tasks that need heavy computation. Instead of manually manage threads or processes, you can use treat preset, kuto, or process pull executor to submit tasks, and the module handles scheduling and execution in the background, allowing you to retrieve results as they complete. It simplifies parallelism without needing to write complex code. Key components of concurrent dot futures. Key components of concurrent dot futures are crucial for managing parallel tasks efficiently. The thread pool executor runs tasks using threads, making it ideal for I/O bound operations like handling network requests. In contrast, the process pool executor executes tasks using separate processes, making it perfect for CPU bound tasks like heavy data processing. Both executors offer a flexible way to run multiple tasks concurrently, improving performance without requiring complex thread or process management from the developer. Common methods. The submit method schedules a function to run and gives you a future object, which allows you to track execution and get the result later. The map method works like Python's built-in map, but it runs the function on multiple items in parallel, making it faster for large datasets or tasks that can be done simultaneously. These methods are essential for optimizing performance when you need to execute functions concurrently across multiple threads or processes. Practical implementation. This code demonstrates how to use Python's concurrent.futures.threadpool executor to execute tasks concurrently using multiple threads. The purpose of the example is to simulate tasks that take time to complete, such as waiting for I/O operations, e.g., reading files or making network requests. In this case, the task is to simulate a delay using the time.sleep function, which pauses the execution for a given number of seconds. First, the delayed underscore task function is defined, which takes a norm of seconds as input and simulates a day by sleeping for that time. It then returns a message indicating the task is complete. Next, the thread pool executor is usually a pool of threads that will run this task concurrently. The executor dot submit method is used to schedule the delayed underscore task for execution, with each task receiving a different number of seconds to sleep. These tasks run in parallel, allowing multiple delays to occur simultaneously, significantly improving efficiency compared to running them sequentially. The concurrent.futures.as underscore completed method is used to monitor the tasks, returning each future representing the result of a task as it finishes. This way, the tasks can be processed in the order they complete, regardless of the order they were started. Finally, future.result retrieves and prints the result of each completed task. By using a thread pool, the program efficiently handles multiple tasks at once, demonstrating the power of concurrency for time-consuming operations. Question 98. What is design pattern and how you use in your development? Design patterns are reusable solutions to common problems in software design that help structure and organize code more efficiently. They're like blueprints for solving design challenges that developers face regularly, and they can be applied in any object-oriented programming writing language such as Python. Rather than reinventing the wheel each time, developers use design patterns to handle things like object segregation, data flow, and interaction between components. These patterns refined over time promote cleaner, more maintainable, and scalable code in software development. Categories of design patterns. Design patterns are categorized into three main types based on their purpose. Creational patterns focus on how objects are created, ensuring flexibility and efficiency. Examples include singleton factory, abstract factory, and builder, each handling already. Structural patterns deal with how objects are composed or structured, allowing for more flexible and efficient designs. Examples are adapter, bucket, decorator, term composite, which simplify object relationships. Lastly, behavioral patterns focus on communication and interaction between objects. Examples include observer, strategy, command, and iterator, each proving how objects collaborate and share information in a system. Practical implementation. The provided code demonstrates the factory design pattern in object-oriented programming. This pattern allows the creation of objects without specifying the exact class of object that will be created, making it particularly useful when dealing with multiple classes sharing similar interfaces or methods. In this code, the animal factory class serves as the factory that generates object input parameter animal underscore type. The create underscore animal method checks if the requested type is either dog or cat and returns an object of the respective class, dog or cat. The benefit of this approach is that the code outside the factory, does not need to know the details of object creation, reducing coupling and increasing flexibility. The dog and cat classes define how each type of animal behaves. Specifically, both classes have a speak method, but the behavior of that method differs depending on the animal. For example, dog returns woof while cat returns mew. The factory encapsulates the decision making process for which object to create, abstracting this complexity away from the client. This design pattern makes it easy to introduce new types of animals in the future simply by adding a new class and extending the factory logic without modifying the client code. It promotes code reusability and maintainability, especially when managing a large number of object types, as the object creation logic centralized in the factory rather than scattered throughout the code address. Question 99, designing and implementing your own decorators with arguments in Python. In Python, decorators allow you to modify or enhance the behavior of a function without changing its code directly. By adding arguments to decorators, you make them even more flexible as they can adapt to different use cases based on the inputs. This allows you to create reusable decorators that can apply different behaviors to multiple functions depending on the argument passed. Designing decorators with arguments involves nesting functions where the outer function takes the decorator argument and the inner function wraps the target function, making it both powerful and customizable. Key concepts: a basic decorator is a function that takes another function as input, adds some extra functionality, and returns the enhanced version without modifying the original function structure. It's like adding extra layers of behavior to a function in a clean and reusable way. A decorator with arguments, on the other hand, is an advanced decorator that allows passing additional parameters to customize its behavior. This makes it even more flexible, letting you tailor the extra functionality based on specific inputs or conditions while still maintaining the simplicity of the original function. Steps to implement a decorator with arguments. To implement a decorator with arguments, start by defining outer decorator function that accepts the arguments. Inside this outer function, create the actual decorator function that takes the original function to be decorated. Next, define a wrapper function within the decorator that will modify the behavior of the original function as needed. We finally return this wrapper function to apply the decorator's logic to the original function, incorporating the provider arguments and ensuring flexibility in how the decorated function behaves. Practical implementation. Feed this code demonstrates a logging decorator in Python that allows for customized logging messages when functions are called. Feed the primary function log underscore with underscore prefix is responsible for generating the decorator. It takes a string argument prefix which is used to add context to the log text to the logging messages such as a log level or description. Inside this function, the actual decorator func is defined which takes the target function as an argument and wraps it in a was. The wrapper function contains the logic to print the logging messages before and after the execution of the original function. When the function is called, it logs the message calling func dot underscore underscore name underscore underscore, indicating the start of the function call, and after the function execution, it logs return result, showing the return value of the function. The key part of this code is how the decorator is applied using a log underscore with underscore prefix debug, which passes debug as the log prefix, showing that this log is for debugging purposes. When add 510 is executed, it logs the function's name and its result, giving you a trace of the execution flow. This design is especially useful for debugging or monitoring function calls without altering their internal behavior, keeping the code clean and maintainable. Question 100, what are Python's built-in data structures and how do they differ in terms of performance? Python offers four primary built-in data structures: list, tuple, sets, and dictionaries. Each serves a specific purpose and performs differently depending on the operation. Lists are dynamic arrays that allow indexing, slicing, and appending, making them great for storing ordered data, but inserting or deleting items can be slow in large lists. Tuples are similar to lists but are immutable, which means their values cannot be changed after value. They are faster than lists for lookups since they are immutable, but you lose the ability to modify them. Sets store unordered unique elements and are highly efficient for membership checks or removing duplicates, but they don't support indexing or slicing. Dictionaries map keys to values, providing fast lookups, insertions, and deletions based on unique keys. They are optimal for situations requiring key value pairs, but the order of items is preserved only in Python 3.7 and later. 1. List. A list in Python is a versatile data structure that can hold elements of different types like numbers, strings, or even other lists. Lists are ordered, meaning elements maintain their position and they are mutable, allowing you to easily modify, add, or remove items. You can think of a list like a flexible container where you can change, resize, or reorder the contents as needed. Key features. Lists in Python are ordered, meaning elements maintain the order in which they are inserted, so you can rely on their position. They are mutable, allowing you to change, add, or remove elements after the list is created. Lists are also dynamic, meaning they can grow or shrink in size as needed, making them highly flexible for various data manipulation tasks. This table outlines the performance of common list operations in terms of time complexity. Accessing an element by index takes constant time, O1, as does appending an element or popping the last one. However, inserting or deleting an element at any position other than the end requires linear time, ON, because the list needs to shift elements. Similarly, searching for an element also takes ON, as each item may need to be checked. This demonstrates how efficient appending and accessing elements are compared to more time consuming operations like inserting operation. 2. Tuples. A tuple is like a list, but once it's created, you cannot change its elements. This immutability makes tuples useful when you need to ensure data remains constant. Additionally, because tuples are hashable, they can be used as keys in dictionaries or stored as elements in sets, unlike lists which are mutable and non-hashable. This makes tuples ideal for storing fixed counts of items. Key features. Uh, Key features of this concept include add elements, meaning they maintain the sequence in which they were added. Once created, elements are immutable so their values cannot be altered. Additionally, they are hashable, allowing them to be used as keys in dictionaries, which enhances flexibility in data handling. Performance. Tuples and lists both provide fast access to elements by index with a time complexity of O1. Searching through elements in either a tuple or list has an average time complexity of O, n, meaning the time increases linearly with the number of elements. While tuples cannot be modified after creation, making them immutable, they are slightly more memory efficient than lists. This immutability contributes to improved performance in certain use cases where data doesn't need to change. 3. Sets. A set is an unordered collection where each element is unique, meaning no duplicates are allowed. Sets are mutable, allowing elements to be added or removed as needed. They are implemented using a hash table, which makes checking if an item is in the set very efficient. This structure is ideal for scenarios where you need to store distinct elements and perform quick membership tests. Key features. Sets are unordered collections, meaning the elements don't follow a specific order. They are mutable, so you can easily add or remove elements as needed. Sets enforce uniqueness, which ensures no duplicate elements are allowed, making them ideal for storing distinct values. Performance. Sets are incredibly efficient for operations like insertion, deletion, and membership testing, each with an average time complexity of 1. This speed comes from their underlying hash table implementation, making sets ideal when you reach a crucial release or perform set operations like union and intersection. For set operations such as finding the union or intersection of two sets, the time complexity is determined by the smaller set O mean len S len T. Sets are particularly useful when working with data that requires fast lookups or uniqueness guarantees. 4. Dictionaries. A dictionary is a data structure that stores key value pairs where each key is unique and associated with a value. It uses a hash table under the hood, making operations like accessing, adding, or removing elements quick and efficient. Keys must be immutable types like strings or tuples, while the values can be of any type, providing flexibility for different use cases. Key features. So, a key feature of dictionaries is that they are unordered, meaning keys don't follow a specific order, though from Python 3.7 onwards, insertion order is preserved. Dictionaries are mutable, allowing you to add, modify, or remove key value pairs as needed. Keys in a dictionary must be hashable, which means they must be of an immutable type like strings, numbers, or tuples. This ensures that each key is unique and identifiable in the dictionary. Performance. Dictionaries offer excellent performance for key-based operations like lookups, insertions, and deletions, all of which have an average chain complexity above 1. This makes them highly efficient for fast data retrieval when dealing with key value pairs. Whether you're accessing a value by its key, adding a new entry, or removing one, dictionaries ensure optimal performance. Even checking if a key exists, known as a membership test, also runs in one time, making dictionaries an ideal choice for scenarios where key data access is essential. Comparison of built-in data structures. This table provides a comparison of Python's 4 key built-in data structures, list, tuple, set, and dictionary, outlining their properties and best use cases. A list is an ordered mutable sequence that allows duplicates. It supports fast access to elements by index and efficient appending, making it ideal for managing dynamic arrays where you need to maintain element and perform frequent additions or deletions. A tuple is similar to a list but is immutable, meaning its elements cannot be modified after creation. This immutability makes tuples more memory efficient and allows them to be used as hashable keys in dictionaries or sets. Tuples are best used when you need a fixed collection of items that shouldn't change over time. A set is an unordered collection of unique mutable elements. It disallows duplicates and provides fast membership tests, which makes it particularly useful for tasks like removing duplicates from a list or checking whether an element exists in a collection. A dictionary is a collection of key value pairs where keys must be unique. Starting from Python 3.7, dictionaries maintain insertion order. They are mutable and allow fast lookups, insertions, and deletions by key. This makes them ideal for use cases where data needs to be associated with a specific word identifier, the key, and you need to retrieve values efficiently. Each structure is optimized for different use cases, with lists and tuples offering fast access, sets providing efficient membership checks, and dictionaries excelling at key-based lookups. And that's a wrap on the top 100 most frequently asked beyond interview questions. I hope this video has helped you feel more confident and prepared for your interview. If you found this useful, don't forget to like and subscribe for more Python interview tips and tutorials. And remember, practice is key. Thanks for watching, and I'll see you in the next video.